in the year. Right. ठीक है. How many are there? 70.
Can you note? Yes. Yeah.
In the year. Right. ठीक है. How many are there? 70.
Can you note? Yes. Yeah.
In the year. Right. ठीक है. How many are there? 70.
Can you note? Yes. Yeah.
In the year. Right. ठीक है. How many are there? 70.
Can you note? Yes. Yeah.
In the year. Right. ठीक है. How many are there? 70.
Can you note? Yes. Yeah. Good morning, everyone. I am Nilanjana Medhi.
And I am Gopal Rizal.
We welcome you to the second day of the familiarization workshop on nano and biomaterials and devices of Indian Nanoelectronics Users Program Idea to Innovation 2022, organized by Center for Nanotechnology, Iitg Guwahati.
Today with us, Professor Parmeshwar Krishna Iyer, Professor Uday Narayan Maiti, and Professor Nageshwara Rao Pila as our
Good morning,
speakers.
everyone. I am
The theme
Nilanjana
of the
Medhi.
first session is energy generation and
We
storage.
welcome you to the
Our
second
first
day of
topic
the
is
familiarization
hybrid
workshop on
photovoltaics by
nano
Professor
and
Parmeshwar
biomaterials
Krishna
and
Iyer.
devices of
Professor
Indian
Parmeshwar Krishna
Nanoelectronics
Iyer
Users
is the
Program Idea to
PhD
Innovation
in chemistry from
2022, organized by Center for Nanotechnology, Iitg Guwahati.
Bhavnagar, India. Today with us, Professor postdoctoral researcher subsequently from Professor Israel, University of California at Santa Barbara.
Good morning, everyone.
And
I am Nilanjana Medhi.
first session is energy generation and
We
storage.
welcome you to the second day of the familiarization workshop on nano and biomaterials and devices of Indian Nanoelectronics Users Program Idea to Innovation 2022, organized by Center for Nanotechnology, Iitg Guwahati.
Today with us, Professor the design and development of functional materials and their application in photovoltaics, elimination of transistors, memory,
Good morning, everyone. I am Nilanjana Medhi. We welcome you to the second day of the familiarization workshop on nano and biomaterials and devices of Indian Nanoelectronics Users Program Idea to Innovation 2022,
is primarily the Department of Science and Technology, the Max Planck, the institute, which is really funding us over in the past almost a decade for our research. And the MIT has funded a very big project in the Center for Nanotechnology. We have been able to establish the clean room and all other fabrication facilities in one of the largest centers in the country. So all the users, other than people from IIT Guwahati, are really welcome to avail this facility and see what kind of devices, what kind of applications they can realize by using these facilities, and also collaborating with the scientists and the other staff at the center. Definitely, I'll be talking about perovskite mainly today, but I'll also be touching upon the applications of conjugated polymers and smaller molecules, how they are revolutionizing the electronic industry. My collaborators, without whom this work is not possible, Professor Siddharth Shankar Ghosh, you all would have heard his talk yesterday. He is from the BSB department, but again he has the same affiliation like me. He is from he also affiliated at the center and also from the school of SHST, the School for Health Science and Technology. We do a lot of collaboration with Professor Qureshi, who is instrumental in setting up the lab also, the device fabrication lab. Dr. Arun Tej, he is also part of our laboratory. And Dr. Professor Roy Paili, he was the former head of the Nanotechnology Center, presently the head of the AAA department. Similarly, Professor Harshal Lemade, also from AAA department. We have joint students with almost all of these people. All of these faculty members, and Dr. Sachin Kumar again from the BSB department. He's not affiliated to the center, but he helps us a lot in several of the biological work that we carry out. I'll be not showing any of the biological work that we do, but definitely their help in taking the molecules, taking the hybrid systems that we prepare, and studying their biological activity has been very helpful in our growth process. So I really thank all the collaborators and the funding agencies as we move forward. So, the area of this photovoltaics or this perovskite in photovoltaics has been growing rapidly, not just in our country. In fact, we are slightly late, almost half decade late as compared to the other countries. The main reason is, the demand to have or move towards the sustainable, goals or implement sustainable goals that were brought out by the United Nations. So if you see the 17 goals, and there are a lot of targets. There are 163 targets. In fact, I'll not go into the details of all this thing, but the goal number 7 is right now very relevant to what we are going to study here. So in this goal number 7, you see this. You need this clean energy, and not only clean, it should also be affordable. But the major challenge, as a nation, or not just in India, but in most of the developing countries, is that we really are dependent on sources of energy which are not renewable. And that definitely adds to a lot of other aspects, or damaging aspects which we are trying to overcome. Okay, so that is where a lot of other aspects in the sustainable development goal comes in, the clean air, the clean water, and a lot of other aspects. Okay, so though we think that there are 17 goals, if we go into detail, a lot of these goals, a lot of the targets are interrelated to each other. Now, this specific part, the right part of this slide, it is India specific targets or India specific goal, but it is not different for most of the developing countries. Okay, in this case, the affordable and the clean energy, definitely, it is necessary for the growth of any country or any economy, and it is necessary for the governments to ensure that the masses of the country, the countries with very large populations, they have access to this affordable, reliable. Okay, that means uninterrupted the energy that should be sustainable. And definitely, it should have, they call it modern energy, or which is, not, responsible for damaging the environment or, generating a lot of pollution. So then these are some of the aspects that, we are going to see in the near future. Over the next decades, you will see a lot of change in the way we are likely to get energy or, generate energy. And the lower part of this slide, what we see is around 12.6%. They still lack access to modern electricity. So that is a very, very big thing. And 2/3 of the global greenhouses, it is generated usually by producing this means by which we produce electricity. So we need to have some sort of an intervention where we can definitely reduce this. So as a faculty in IIT Guwahati, I'm very happy to share with you that in IIT Guwahati, every year we are trying to introduce solar panels across the campus. Okay, most of the academic complex you see on the rooftops, are full of solar panels. Definitely they are silicon based solar panels. We are again trying to move away from that the technology which is close to 4 to 5 decades old, very robust technology, and trying to see how we can replace them the more efficient method. And in India, nearly, it is thought that close to 85% people have access to electricity, and the government claims that almost 100% electricity, all 100% villages are electrified. But the reality is, always, not what is shown on this slide. That there is a lot of practical issues, and as such, the ground reality, it seems that there are around 31 million houses, which still lack electricity, and per house, even if you count in 3 to 4 citizens, you can see that number goes to above 100 million. So that's a very large number, almost the size of some of the countries across the world. Okay, so this is a major issue, and government has decided to have a very ambitious target by the end of this year to generate 175 gigawatts of renewable energy capacity, and among this the 175,000 gigawatts of electricity that has to be generated, okay, the 100 gigawatts must come from solar. So that's a more than 50%. Whereas the other three that are shown here, the wind, the biomass, and the hydro, this constitute smaller percent, but definitely there is a contribution from other renewable energy source. So you can imagine now, if you want to move this, if you want to achieve this, the solar is likely to play a major role. Okay, so that is where the whole aspect of developing affordable materials, or materials which will be able to produce highly this or convert the solar energy or the sunlight into electricity, it comes into play, or it's a very important topic. I move to the next slide. So where are we, and what is the literature telling us? How do we move towards a cleaner or the renewable energy form? So you all are aware about various technologies, various solar devices that are already existing in the market. One of them I already mentioned previously about the silicon based solar cell, which are there existing over the past 4 to 5 decades, installed in most of the rooftops. You all would have seen definitely, and the current literature, various technologies are being developed parallelly. Okay, I'll start with the dye sensitized solar cells, and this technology started in the early 90s, and it had great promise initially, and it moved up to 13 to 14%, but later on, last close to a decade, we see that it's getting saturated. Okay, and this is where parallel a lot of other technologies started coming up. Along with the DSSC, the bulk heterojunction solar cells utilizing the small organic molecules or the conjugated polymers has also come up in a very big way. So in this case, up to close to 2019, the efficiencies, it was very difficult to cross more than 10%, and people thought that this area or this research area is likely to be saturated. But last 2 years we have seen very nice structures being developed, and all aspects of this polymer had improved, and we could people have reported efficiencies which is close to 90%, or by the end of this year it is likely to go to 21%. Now you can see the literature in advanced materials, it has come in 2021. So just last year we can see that it has gone to 19%, which is highly competitive and which is very attractive, because I'll be showing in the next few slides the processing parameters that are associated with these materials are are tremendously attractive to the industry. Now coming to what I will be discussing today about the metal halide perovskite. In this case also, this is almost just a decade old. The research in this area started only in 2009, but in the last 10 to 12 years, this efficiency in 2021 has gone beyond 25%. Okay, so this is not the simple perovskite that I will be showing. That there has been a structural modulation. There are multiple things that have been added to the basic structure, and these are really very excellent. And this has also been reported in Nature just last year. Okay, and parallelly along with this metal halide perovskite, and another technology which is coming up is the tandem solar cell. Now tandem, it uses when I tell tandem, it can be a mixture of two different technologies. The values that I report here, 29%, is along with the perovskite, the metal halide perovskite, and the silicon based solar cells. It's a combination of two very good technologies, and this area is also likely to see a good improvement by this year to around probably about 30%. If not by this year, at least in another 1 to 2 years, you will see that this will cross around 30%. So you see that there are multiple technologies which are coming up in a big way. Okay, tandem, of course, there is a drawback that the silicon part of the solar cell that has to be fabricated. The fabrication steps are slightly tedious compared to the organic and the polymer solar cells and the hybrid perovskite solar cells. By that I mean the metal halide perovskite. The values that I have reported in the bracket, that are the values that we have achieved in our laboratory at Iitg Guwahati, and hopefully, Ritesh and Maimur will be able to highlight some of their results as we move forward. This is a typical architecture of this solar cell. Okay, so students, especially, you can see that there are multiple layers, and you can still keep adding layers, or you can remove layers as per the your requirement to improve the performance. When I tell improvement, that means I mean the improvement not only of the percentage, the power conversion efficiency, but also the stability aspect of these devices. Okay, so you can have just one layer, active layer, and then you have the two electrodes, or you can have the multiple layers, the whole transporting, the electron transporting, or you can have an additional buffer layer to improve the stability. You can have buffer layer on the top, at the bottom. So multiple aspects of the device physics or the device engineering plays a role in realizing the stability as well as the performance of the device. And there are a lot of advantages. I'll go into the detail in the next few slides. But most attractive are the low production cost. They are really transparent, making them available for installing in large buildings. In cities you have these transparent glass buildings where you can directly have rather than simple glass, we can have this solar cells on the as a wall. You can make them flexible, and you can make them they are definitely lightweight, so that's you can bend it, and you can install it in desired location. And definitely you have the ability to tune the color. I'll also be discussing about this slightly later. And these are a lot of advantages which you don't see in the earlier technology, and that is what is attracting people to pursue research in this area. This is another small device that we have fabricated at our lab. And as we move forward, a lot of newer technologies and newer aspects of science and technology are being incorporated. The main thing is industry is looking for automation in a very, very big way. You are looking to simulate each layer as well as the performance of the device. You have multiple device, you have the data that is being generated, a lot of data is being generated, and AI is likely to play a major role in the next few years on monitoring their performance, or even fabrication of the device, controlling the thickness. Every aspect of this is likely to be inspired by the positive aspects of this AI. And definitely when you have all these things, you are going to have feedback, and we will be able to generate any improved materials, or the process for developing the materials are likely to improve. And the characterization techniques are also, you all are aware now, we are having better tools to understand what is happening not only at the surface but also the interfaces of the device, which is also very, very important to understand why it is working, how we can improve, what are the defects, and what is happening exactly at each interface. So these are very important aspect that probably will be learning over the next few years with the improved characterization technology. Moving forward, I'll not spend time on this, but there are multiple technologies that have been developed, and we are right now somewhere here, and the organic solar cells and the perovskite solar cells, these are the two which are really very attractive. And definitely we will see tandem solar cells in a combination with this perovskite, or this this organic solar cell. This perovskite, when I write perovskite, it can be either hybrid, the organic inorganic hybrid perovskites, or they can be purely inorganic with various other metal salts. So it can be, you will see that a lot of development happening over the next few years in this area independently, or this area independently. And both these technologies along with this the silicon solar cell. So a lot of technologies are coming up. Probably we will also see some kind of improvement in the quantum dot based technology, and in their incorporation in with the silicon, or any of this organic and perovskite tandem solar cell. So there are a lot of possibilities. Students pursuing these materials or studying materials in any of this class of devices can think of collaborating and discussing among yourself how you can incorporate this into one device, or see how you can make a tandem not only solar cells but also tandem devices like LEDs, or any other technology where you will have the beneficial properties of two different class of materials, stability of one class, and the performance enhancement in the other class. So there are a lot of possibilities that can be pursued. So, this slide is slightly, crowded, but, this is one of the very important slides, why this technology has been quite interesting. So, when I talk about this organic solar cell, I keep telling about these organic materials because, the technology used for processing of these organic materials, it is exactly the same process or the same method that is now applicable to this hybrid, this solar cell. That is where, whatever knowledge we have gained, whatever instrumentation has been developed, has been customized for fabricating this organic and the polymer solar cells or any other devices. The same technology can be utilized now or extended to fabricating these, hybrid materials. So one of the prime reasons that, these materials have been attractive is, you can design them at a molecular level, or you can, choose, which molecule to introduce, how you can add that, and how you can replace these materials, functional group, and leading to, well-defined structures. And these structures will definitely, are you are able to tune the energy levels, and you can get a different band gap, which is a very important aspect for attaining or in choosing the different layers. I mentioned previously the thin, they can be thin, they can be lightweight as devices, and they can also be used for displays, and in small devices, or even very very large devices like large display panel. You can have very high brightness at very low operating voltages. These are really very low, around 2 to 6 volts, especially for the light emitting diodes. And you can have very high power conversion efficiencies. These values also I mentioned, more than 20-25% as photovoltaics. The processability is, when I mention easy processability, that means, they can be dissolved in organic solvents at room temperature. And there are multiple ways when you bring the material into solution, you can make the film. Okay, they can be simple drop casting. Okay, they can be used by fabricated into the film as a by this doctor blade technique, by printing, and by spray coating. So these are some of the techniques which are extensively used in the labs. We also use spin coating a lot, and this really helps in generating devices or films or any kind of surfaces at any given time. So that we are talking to industry, and they in this case they're sort of using drop casting technique, where there is a continuous flow of the substrate. Okay, and at one location it's like a waterfall. The solution, it drops on the like the there's a conveyor belt where the devices are placed, and you can directly fabricate devices. So it's like a waterfall, or the active layer, it just falls on the surface, and there is slow movement of this device, and you can make the film. So these are this aspect is specifically, the next aspect is specifically related, the fast response and no viewing angle limitation. That is a very important aspect related to the LED devices, which is a drawback in LCD and the other technologies. So I'll not go into the detail of this, since we are not discussing today about LEDs. But the color purity and the response time are very very good when you use these organic or these hybrid materials. And again, the next point, the flexible substrates is an area which is likely to be very very important. One aspect I don't see here is about the wearable devices. So these materials can also be made on devices which are not just flexible, but this can also be implanted on the skin or any parts of the body, and they are usually non-toxic. So as such, this is another very important aspect that has attracted the researchers. And I mentioned the earlier point, the fabrication on large area. So this is about that. It is not only large area flat panel displays, but you can also make now large modules for this photovoltaics. Definitely, it is not a very good idea to go to very large size. It's always, I always tell that it is preferable to have around 6-inch to 7-inch or 8-inch devices, and then go into assembling them, okay, and into larger modules. And for the work in biology that I mentioned, they are usually biocompatible, and that helps them also make them implantable. Their response is very very rapid, and by introducing specific functional groups, you can also make them selective and sensitive as sensor materials. So as such, a lot of applications towards and this is not just for the bioanalytes or biomarkers, but this can also be chemical analyte, sensors for gases, sensors for explosives, okay, and also a lot of other applications. So these are just not limited to specific areas of this optoelectronics, but definitely they have applications in a lot of other areas as well. And as the processing and everything is very very cheap, they are usually very very economical, and usually when you want to scale up, they are also quite reliable, and you don't need real expertise once the method is optimized. and you can take it to the mass production, which we are already seeing in the case of existing the organic LEDs and other technologies, and you can install them at desired location because of the lightweight and other applications. So you can see a series of applications, series of positive properties that these materials possess is the reason why they are very, very attractive, and why the interest has been generated to utilize them for also this renewable energy aspect. Moving forward, so this is one slide about the organic materials, or the top line shows the various class of heterocyclic structures, or the polymers, conjugated polymers having this heteroatom, sulfur and nitrogen. You also have substituents such as oxygen, you have the fluoride, and this is what I mentioned, that you can tune the structure. Okay, it's a simple structure. Previous generation of this conjugated polymer, they only had the thiophene structure. Okay, now you have these fused heterocycles, you have copolymer, and you have larger structures, you have multiple these monomers within a backbone structure, and you can see that as you keep moving from just 8% to 10%, 2021 you have gone close to 18%. So you can see there is a structural variation. You can tune the structure, and you have the functional group, which the alkyl chains, which help their solution processability, and this is what allows you to tune as well as go for variation in the structure and achieve higher performance. Similarly, so you have the donor acceptor systems. You also have the PCBM based system, but definitely the technology is moving away from this PCBM. You also have non-fullerene acceptors, which are processable, like these materials, or you have some organic molecules which are attached to this system itself. So multiple things are also being developed, not just on the conjugated polymer, but also in the PCBM or the non-fullerene acceptor based systems. Okay, I'll not go through the advantages. These are the same advantages what I showed in the previous slide, but definitely all of them are very, very interesting. The technology which is likely to come out in a very big way is the roll-to-roll printing. Okay, so this is one technology which is very, very attractive, and it is likely to come up in a very, very big way in most of the manufacturing of either this or the technology or the material in the next slide for this the perovskite. So very, very brief introduction to people who are not aware, compared to the previous materials, the slides in the details of the previous this thing, the perovskite material, as such, it's the CaTiO3, or they call it A, this B, and then you have the X, 3. Okay, so that is how it is made. This is how the mineral looks like. They were discovered by Lev Perovsky. That is how the name comes from in Russia. And you can see in 1839, that is almost 2 centuries ago, close to 2 centuries ago. Okay, and we have more than 2 centuries ago, and you have a lot of applications across the fields. These are some of the things which have been already reported in literature, and really very attractive material. Because replacing any of these ABX3 and introducing a newer cation or an anion or even an organic component in that, it's not very difficult. This is what I'll be showing in the next slide. And a lot of groups across the world have been pursuing not only the applications but also the variation, develop other materials, other structures, other incorporating other these atoms, and seeing what is the influence on the basic properties as well as their structures. So this is the typical crystal structure, that is reported in literature. You have this ABX3, as I mentioned in the previous slide, and the color, combination. It's very easy to identify. You have the large this cation in the center of this lattice structure. You have the B and the X here, the small red ones. So as such, it looks quite attractive. But studying and understanding this is very, very important to realize the stability aspect. Okay, so in addition to most of these material characteristic or the positive properties, I would like to draw your attention to the right side, this bottom thing. So these are some of the challenges which are facing not just the photovoltaic industries, but also the other devices. Okay, one of the biggest problem with this is the most of this the structure of this is not only unstable to this heat. Okay, whenever you have this crystalline state, these edges and all, they see a lot of changes as soon as you expose it to heat. Okay, and most of the solar panels are usually installed in at very harsh conditions. Some places it may be very hot, some places it may have high humidity, or some places you have both heat, humidity, and a lot of other problems. Okay, so it is necessary that we understand the crystal structure, the stability of these materials, unless we know that, it is very difficult to design efficient materials which will be able to resist the exposure to this water and oxygen, or the normal ambient conditions. Definitely, when you're placing it in on the rooftops, it is going to be exposed to sunlight, and you have a lot of UV rays coming in. So it's also, the material also degrades over time with this UV light. There is also a problem with heat, as I mentioned. The temperature in certain desert places, it can go up to 50 or 60 degrees. So that's too high for the structure to maintain the intactness or the performance level. Okay, so these are some of the aspects which have to be addressed as the world moves forward. A lot of aspects have been touched upon, but still that remains a challenge, and some of these challenges that we have been able to overcome will be discussed by the research scholars in the later part of the talk. The other aspect which is of concern is presently the use of this metal, the lead metal, which is we are aware is quite toxic, but you are also aware that there's already lead being used as batteries, as part of this car and a lot of other applications. So we already know, or there are already specific policies which have been drafted, framed in different parts of the world. Every country has their own policy of using this lead or other toxic metals in batteries and few other applications. And although everywhere it's mentioned that we need to replace lead because of the toxicity, the level, the quantity of this lead that is used in the solar cells, or this MAPBI3 or the FAPBI3, or as in the combination of these materials, it is not as high and as it is thought. So this is a typical structure or the typical composition that researchers have reported. As I mentioned, this ABX3 usually you have with the cesium, or this cesium is replaced by this rubidium also, and this A, and similarly you can also have this lead, the lead 2, it can be replaced with the tin or the germanium. Okay, the organic part, I would just again like to emphasize, this is the methylammonium or the formamidinium, the structure, the ethyl and the formamidinium amide. So these are the three which are used very extensively. And in the halides, you have the chloride, the bromide, or the iodide structures. And this is where you have the organic part, you have the metallic part, and you can also have the halides. Okay, you can have, instead of the organic, you can have the all metal also. And definitely there are a few other structures, few other compositions which are being tried. This is the combination that I reported. Based on the literature, you have the A1, you have the A2, or you can have two of these, or you can have one organic and one metal. Okay, as A, you can have then the B, any of this. You can have the X, it can be usually the chloride, the bromide, or even here you have a combination. Okay, similarly you can have just one A, and you can have B1 and B2. You can have two of this. This is another area which is coming up in a big way to reduce the toxicity. You have any of this, you can replace some amount of this lead with the tin or this germanium, or you can have the other structure where you have the A1, A2, and you can also have the B1 and the B2. Okay, so two of this, two of this, and then you have the halide. And similarly, you can have three here, the A1, A2. So this is a mixed halide where you have the two of these. You can have this B, and then you can have X3. So you can see lot of structures are possible, and a lot of this not only helps in tuning the properties of these materials, but it also helps a lot in stabilizing the device and to realize properties which have not been realized until now. Okay, so a lot of characterization is possible, a lot of things are possible, a lot of mixing and matching is available. And one very good thing is that unlike the organic and the polymer materials, okay, here the synthesis can also be achieved by you don't need to be really an expert. Okay, so non-experts can also be trained to do this. That is where the industry is very, very excited, that always you may not be having or access to highly experts in the industry to do the manufacturing. Okay, that is where if you are able to make an ink or make a solution of this, and if someone mix and develop this, it's going to be really, really very easy. And move on to the next slide. I'm running out of time, in fact, but I'll just go through this very, very quickly, and then I'll hand it over to Maimur or Ritesh, whoever wants to continue. Okay, so as such, what has happened over the years, we were looking into technology which was well established in the market, the silicon, and there is a very, very big push from the government of India, the Niti Aayog. They are having several rounds of meeting. How do we incorporate this technology, this material into practical technology platforms? So we had a few rounds of meetings, and a major decision has been in fact taken and being implemented across various funding agencies that we have to bring in this technology before the world takes over. They may start making devices and push it into India. Okay, India is a very, very large market, and definitely we should not always depend on getting this from outside. Sometimes there is a need that we also start developing on our own, because in another year or two probably we will be able to bring up to the manufacturing level. So there has been a major push both from the government as well as the industry side to develop these materials and bring them to the technology this forefront. And perovskite, as such, like unlike the other technology, it has become very, very disruptive. Nobody knew or nobody perceived that in just a decade their performances will go around 25%. Okay, so that has become a major source of excitement, definitely. But also now we have the lab level prototypes level ready. Whereas if you want to take it to the industry, you don't have now customized instrument to process them. Okay, so this is a major challenge where the industry has to play a major role now, because what has to be done in the lab, people are shown in the lab, and now when it has to be taken in the production level, a lot of customization, not only in the device engineering side, but also making the inks or making the solutions of this, taking it to a large level manufacturing. It's necessary. Okay, so as such, the positive things, as I mentioned, they exhibit very optimum and tunable properties. And as I mentioned in the previous slide, you can do the mix and matching, and still, you are, if you are able to optimize that, you can generate very broad range of optoelectronic properties. And that is where I told, it is, not limited. In my title, I mentioned not just photovoltaics, but beyond that also there is a possibility of extending it to so many applications. Okay, so that's a big area, nascent area lying where you can really think of using it. And most importantly, whenever you add these additives, you can not only control various parameter. Okay, definitely the chemical composition is changing, but by varying this, you are also able to reduce the toxicity, which is a concern, as I mentioned. But definitely, you don't have to be really worried, because the lead that is there in this, when you add these other components, that composition is also coming down. Okay. And as of now, we see that it's most promising for one technology, the photovoltaics. But definitely, there are other devices which are being fabricated in our device, in our laboratory. And you have this early report in 2015, where they showed this the simple structure of this methyl ammonium lead iodide. It's a direct band gap semiconductor, so that is one of the reasons very, very attractive. It is in the visible region, the band gap. They also show high carrier mobility. This is will definitely attract all the people working on transistors and other areas where mobility is an important factor. And you have the this you have a very long diffusion length. You have the excitonic binding energy. These again very important aspects of people working on device. And other potential applications which we are pursuing in our labs are listed here. And definitely, if somebody wants to look for collaboration or have some ideas on working on this aspect, please do write to us. My students are also there. Gopal is also sitting there. We can look into the materials and look into the device fabrication aspect. So with this slide, probably I'll end up. I wanted to talk about recycling, but probably I'll have to stop after this slide. So as such, these lead and the iodide ions, these are some of the important ions which form this three-dimensional network, and in the octahedra of the crystal structure, as I mentioned. And whenever you talk about stabilizing them or recycling these devices, if that is a challenge, only when this lead goes into the environment is a challenge. Okay, so till we have prospects of retaining them, recycling them, and reusing them, we don't have to worry about that. Okay, and similarly, we have the introduction of these organic materials. In this case, the methyl ammonium, that is that it occupies the center presently, but definitely, as I told, when we heat, when we use the solvent, the solution, we have the change in the structure. I'll discuss about this slightly later. And this presence of lead, as I mentioned, it has raised question on the environmental impact of this. But the presence of this lead by weight in these devices is so less that it is much lower than the limit set by most of the government agencies. So people who are really concerned, as such, you don't have to be really worried as such working in the lab. But definitely, whenever you're handling this metal, disposing it off and trying to recycle and reuse it, if you put that into practice, it's really going to be very, very good in helping developing this area. And there are prospects of developing this lead-free perovskite, which is an area which is coming up in a big way. But definitely the competition right now, or the performance that lead has given as a metal, it's not as good. The other metals are unable to give the similar level of performance. So with this, I would like to stop here. I request Ritesh or Maimur, whoever is there, please continue from here. The next few slides probably you can skip. This is about the stability. You can talk about this, the compositional engineering, and the cost aspect also. And I'll be happy to answer the questions. If there are any problems, at the later stage. And with this, I would like to really thank Gopal, Nilanjana, and all the organizers of INUP. I will have to log out now. I have a DST meeting, and already I'm getting phone calls to join in. So please excuse me. Once again, I thank you all. I thank the organizers for this wonderful organization of the event. So thank you very much, Gopal. Thank you very much, Nilanjana. Please continue.
Okay. Good morning, everyone. Am I audible? Am I audible?
Yes, sir. It's audible.
Okay, so today I'll discuss about polymer solar cells. So in our lab also we are developing different polymer materials which can be applied for photovoltaic applications. Here this is PTB7TH polymer structure. This can usually synthesized by thermal method, means heating in and doing still a polycondensation reaction to synthesize these polymers. But in that case, you need high energy, and also it may take around 15 to 20 hours to synthesize this kind of materials. So we thought we can develop another sustainable method to synthesize these polymers, and we need to optimize it. So we did it by microwave synthesis, and here we have mentioned the method that we have utilized, the 150 watt, and temperature was 150 degrees Celsius temperature. So you can see that we have varied the timing of the reaction and to control the polymer chain length. And ultimately, you can see here that we got this kind of pure polymers. So ultimately, after purification, we have utilized it for polymer fabrication, and results are summarized here. You can see it is an IV characteristic curve, from where you can say that the result that we got from the microwave synthesized polymer and PCBM blend and thermally synthesized polymer and PCBM blend is almost comparable, and the efficiency was around the range of 8%. So the microwave synthesized polymer by 35 minutes exhibited the efficiency of 8.09%, and for the thermal one it was around 7.91%. So you can say that the microwave wave synthesized polymer is more efficient, and at the same time it's easier method to synthesize this kind of polymers. So to understand that thing, we have also characterized it by GRX, and GRX you can see that for the 35-minute polymer blend, there the discrete line is there which indicate about the crystallinity of the material. So 35 minute based microwave synthesized polymer is more crystalline comparable compared to the other blend. So this is one of the factor which actually contributed to have the better efficiency. But why this is happening, to understand that thing, we also analyzed various other property. For example, one of the one of the thing was that when this kind of microwave based synthesize or we are doing, we found that this polymer units can undergo homocoupling, and that homocoupling may actually ultimately has an adverse impact on the overall efficiency and the quality of polymer property. So that actually impacted the efficiency of other polymers which were synthesized at the higher with a higher time. For example, 45 minutes, you can say efficiency was significantly lower. So this was the work that we done, and it was published in ACS Omega. And after that, in the next work, we have tried to develop a new coating method. Actually, we wanted to know that how morphology can impact the ultimately efficiency and other factors. So as you can see here, we have presented a method that how we have coated. So in this case, what we have done, we have actually heated the substrate at different temperature. You can see room temperature to 70 degrees Celsius temperature. And when you heat this substrate at different temperature and you coat the polymer blend on the top of that, so the film, when thin film is forming and the substrate is already heated, then it will have completely different kind of film formation. The film formation will have an impact of this heating will have impact on the thin film formation, and ultimately that will control the ultimate property of the photovoltaic property of the devices. So here you can see that we have calculated the mobility by SLC method, and also we have shown it here that how the roughness is also varying with temperature. So you can see here that at 40 degrees Celsius temperature, the roughness was low and the mobility was high. That ultimately contributed to higher efficiency in the case of 40 degrees Celsius temperature of the substrate, and you can see here the efficiency was around 9.13% in the case of this 40 degrees Celsius based device. So this hot cassette device was more efficient than the normal room temperature processed devices. So later on, we tried to develop new materials because we know that to design new materials based on this PTTT backbone is very difficult to design new building blocks, because all these steps are very tedious and very lengthy process to design these materials. And to tune the property, we need to every time we need to synthesize newer backbone, newer building blocks. So it's very difficult. So we thought that instead of that, if in the polymer synthesis we incorporate another third monomer, it can tune the property. To do so, we have incorporated here difluorophenyl moiety. So why difluorophenyl? Because this fluorine can interact with sulfur, and we have also exhibited that thing in the by this DFT analysis. You can see in DFT analysis the interaction actually reduced the dendral angle. In the case of PTB7T ideal backbone, the dendral angle was around 25 and 18, which was reduced to 13 and 11. So from the side view also, it is very evident that the backbone is being well organized in the case of this difluorophenyl incorporated backbone. We synthesized two polymers, M1PDB7TH and M2PDB7TH, and you can see the incorporation was around 5% and 10%. We replaced the septic unit with difluorophenyl unit, and ultimately when you see the TEM images, you can see the phase distribution was better in the case of M1PDB7TH. And also we studied other things like mobility and stability and other factors, which ultimately from where we understood that this kind of incorporation can improve the photovoltaic application, photovoltaic efficiency. And you can see here the efficiency was around 8.78% in comparison to 7.87% of PTB7TH. But as the incorporation rate was high in the case of this M2PTB7TH, you can see efficiency was significantly dropped, and that was due to the fill factor. Later on, also found that because of the mobility, whole mobility and equal mobility didn't have proper balance in this case, that also contributed in the lower fill factor, ultimately which impacted the efficiency. But the interesting part was that as the incorporation rate was going high, you can see the VOC was improving significantly. So that can be correlated with the lower homo level of this polymers, and that actually is, has a direct correlation with this VOC. So in the next work, we concentrate on same methodology, and we have actually incorporated other two fluorinated phenyl ring to understand that how this position and the number may have the impact on the different photovoltaic property. So here you can see here that this is the same architecture, that polymeric architecture that we have used, and you can see in the from the this DFT analysis that the dihedral angle has significant impact on dihedral angle was there after this incorporation. And in the case of tetrafluorophenyl ring, the angle was around 1.5 and 3, which shows that the backbone is almost planar. So here we have also presented some parameters like UV and the position of the energy band diagram to understand that how the energy level were tuned after this incorporation, and the deeper homo level also is was there for all the terpolymers. So when we fabricated the device by all these three terpolymers and PTB7T, the efficiency for the PTB7T, as I mentioned, was around 8%. But when we fabricated with the device with this polymer blend with PCBM, you can see the efficiency was around 9.48% for this difluorophenyl unit when we changed the architecture with BCP. And for the M2, it was around 8.8, and for M3, it was around 8.13. So we found that difluorophenyl has a better property, and we have tried to correlate it with other factor like mobility and also hole mobility, electron mobility, and also some other characterization also we have done related to that. And here you can see that in the AFM, the morphology, in the AFM morphology, you can see that though in all the cases we have find very interpenetrated nanomorphology, but you can see the roughness has a significant variation. You can see for the terpolymers there is a lower roughness was present, which was actually expected from the dihedral angle study. And after that, we started the ambient stability. In the case of ambient stability, you can see that as the time was progressing towards 1,000 hour ambient, after 1,000 hour ambient exposure, you can see the significant degradation was happened in the film. But as if you see for the terpolymers, degradation rate was quite low. And in the case of M1 PDB7, that's M1 polymer, the degradation was low. So it was due to the conformational log that is forming, and it has a very symmetrical structure, and that's why it is sustaining this morphology for the longer period of time. But in the case of this tetrafluorovinyl based polymer, means M31, you can see that after 1,000 hour the degradation is little bit comparatively high, and that was due to the, you can see here that the aggregation pattern is little bit different, and that has a key role in ultimately maintaining the morphology for the longer period of time, as we concluded in this article. So I am handing over the mic to Ritesh Kant Gupta for discussing about perovskite solar cell that we are working on.
Hello. Thank you, Mahmudda and sir, for giving the brief of perovskite and the polymer work that is going on in our laboratory. So I will be explaining about the perovskite solar cell work that has been carried out for the last couple of years in the lab. And first among them is the hot casted technique that we have used to develop this mixed halide perovskite. So why mixed halide? We already know about MAPBI3 perovskite solar cell, which are more frequently used uh, for the last decade to develop this solar cell. But the problem with this iodide is the iodide ions escape easily from the perovskite crystal lattice. So to control it, this mixed halide approach has been used. But if we are doing it with chloride, which are generally used for controlling the crystallinity as well, this non-conducting phase of this perovskite is being developed. So to reduce this non-conducting phase of perovskite, which is non-desirable for the solar cell, we have added MABR for incorporation of bromide in the perovskite lattice. We have added at various ratios. So we found that with the increase in this ratio from the XRD study, that this non-conducting phase of the chloride perovskite is decreasing significantly. Also, to confirm whether this bromide is actually incorporating in the perovskite crystal, unlike chloride which is not there, we found that at around 14 degree, 2 theta degree, there was a shift towards higher values, which confirmed that the MAPBI3 perovskite crystal is actually having this bromide. So it's a mixture of iodide bromide perovskite crystal in the perovskite. Further, we also checked what happened with the absorbance, and there was an increase in absorbance with this bromide incorporation, which was most likely to have better light harvesting property. And from this absorbance, they got the Staussy plot. So from this Staussy plot, we found that this band gap was increasing with this bromide incorporation. So as the band gap increases, what happens is for solar cell, if the band gap of the active layer increases, there is a trade-off between the current and the voltage, which is actually the product gives the power. So we found actually in our result that there was a trade-off which I will show later, and then a series of morphological study was done to to find that the grain size was in micrometer range, and the highest grain size was 45 micrometer, while the grain width reduced to nanometer range. So this helps in improving the charge transport property. So as I said that the charge transfer property improved, so we fabricated device for all types, and highest efficiency of 18% was obtained. With the same technique, we fabricated large area devices of around 2.5 centimeters square, and here also the efficiency was closer to 17%. And these devices showed lesser hysteresis as the ion migration was controlled with the bromide incorporation, and also the steady state analysis also showed stable result of 17% with light illumination. For the next work, instead of bromide, we tried this fluoride ion using this passivator in the perovskite precursor itself, and also this carboxylic acid group was there. So the effect of both were studied, and the interaction of the same was studied using this FTIR, and highest efficiency of 20% has been obtained with the incorporation of this trifluoroacetic acid passivator in the precursor solution. So for most of our work, we have fabricated PIN architecture, where nickel oxide has been used as hole transport layer and PCBM as electron transport layer, and rhodamine and silver towards the for the cathode side. And again, the morphology was being modulated. Large grains were formed with this passivating molecule incorporation, and even the crystallinity improved significantly. Thereafter, to further improve the efficiency of the device, we did dual passivation. So instead of this carboxylic acid group, we tried to see the effect of sulfonic acid group in the precursor solution, and we coated a very thin layer of this polystyrene, which is hydrophobic in nature, on top of the perovskite layer to form this perovskite. So here also we can see that there was a significant modulation in the morphology and the grain size of the perovskite, and the crystallinity was also affected. Series of these devices were made for all type of perovskite film, and the highest efficiency that we observed here was of 20.62%. And this device was significantly stable after 1,000 hour study without any encapsulation, and the modified device was almost 93% stable with respect to the initial.
Ritesh, I would like to remind you about the time. We have last 3 minutes. Could you please conclude quickly?
I will try to conclude. So other than that, I will just go briefly and say that we like to have this conjugated polyelectrolyte. Here also the effect was similar, and 20% efficiency was obtained. Then we tried to have this 2D graded structure. Yeah, this here the efficiency improved to around 21% modified difference. Finally, we tried to have this UV stability and use this BP molecule from both sides of the perovskite to protect it from the side where we are giving light, from the UV rays of the sun, and then from on top from moisture. So here also the result that we obtained were near about more than 20%, and as can be seen from the graph here, it was stable in not only in ambient condition but for various UV illumination also it was stable. And the reason for this UV stability is this absorbance in the UV range. So this is like cutting off that UV. This is trying to cut off that UV light and protect it from the from degradation. So all this work have been highlighted in various media recently of the perovskite that we are developing in the lab. Just to summarize that we have developed two techniques, the hot casting and the room temperature technique. Various organic molecules are being utilized for passivating and obtain crystalline grains. Till date we have achieved 21% efficiency in small area and 18% in large area. And as I mentioned, the device's stability that we have measured is unencapsulated, and which seems remarkable. So right now we are looking into multiple cation options to increase the efficiency further, and to have a more higher stability. We are also working on this 2D perovskite. Plus the lead-free double perovskite also we are trying to develop with the single crystal one, and also we are exploring the option of fabricating in large area module for large area module fabrication. Other than the solar cell, this perovskite material we are also developing for LED. So we have recently got this LED result which has a maximum luminescence in the same architecture EIN1 with perovskite of methyl ammonium lead bromide, and the maximum luminescence is of 27,000 candela per meter square. And other than this, we are also checking for the options of memory device and transistors that we have said. Thank you. Hello. Hello.
Thank you, Professor Iyer, Dr. Ritesh and Maimur for presenting such an illuminating talk. Now we'll have a question answer session. We'll take 2 questions due to the time constraint. The first question is asked by Ramesh Babu. What are the different techniques to minimize traps in perovskite layer?
As I was not able to explain it completely. So as I said, this can be done through this coating technique. The hot casting one is because we are getting large size grain in hot casting, so the traps are minimized. So these traps, as I said, is because of the grain boundary. So if we reduce the grain boundary, the size and the density of it, the traps can be minimized. Also, this can be minimized using the specification molecules and having this 2D, 3D perovskite layer.
Yeah.
Okay, the second question is being asked by Anvesha Chowdhury. Why GIWAX polymer film instead of XRD? What extra information can we obtain from GIWAX?
Already sent. See.
With this polymer, actually what happens, so these polymer films are very, very thin. So it's in the range of say 50 to 100 nanometers. So having an XRD data ISO for such thin film is very, very difficult. So getting incidence is used to have a scan on top surface of the active layer film. That's why this getting incidence. Extra information, of course, we can have this growth of in plane and out of plane. What is the growth? Whether the film is going in the plane, out of plane. That can be extra information that we have generally found from the GIS, among others.
Thank you, Dr. Ritesh, for answering the questions. I would also like to thank all the presenters here. Now we'll move to next session. Over to you, Nilanjana.
Thank you.
Thank you, Gopal. Our next speaker for the day is Professor Nageshwara Rao Pila, and the title of his talk is Optofluidic Device for the Green Hydrogen Production. Professor Nageshwara Rao Pila is currently an Associate Professor, Department of Chemical Engineering, Institute of Technology, Guwahati. He has obtained his BTech from the Department of Chemical Engineering, JNT University, Hyderabad, MTech and PhD from the Department of Chemical Engineering, Indian Institute of Technology, Kanpur. Professor Nageshwara worked as a lecturer in the Department of Chemical Engineering, National Institute of Technology, Warangal, as a postdoctoral researcher in the Department of Chemical and Biomolecular Engineering, University of Delaware, and as an assistant professor in the Department of Chemical Engineering, Iitg Guwahati, before he joined as an associate professor in the same. His key research areas include heterogeneous catalysis and reaction engineering, biomass conversion to value-added chemicals, bio-oil upgradation to transportation fuels, carbon dioxide activation to valuable chemicals, metal encapsulated zeolites. With this brief introduction, I would like to kindly request Sir to take over from here and elaborate the topic optofluidic devices for the green hydrogen production. Thank you, sir. Over to you, sir.
Okay, thank you very much, Nilanjana, for your kind introduction. And thank you very much to the committee for giving me this opportunity to share my thoughts on optofluidic devices for green hydrogen production. Okay. So basically, in this research area, in the previous work, Professor Iyer has very nicely presented about the photovoltaics, okay, and photovoltaic solar cells to convert the electrical energy, to convert the solar energy into electrical energy. So, in this particular research area, what I would like to discuss is the conversion of solar energy into chemical energy, that is hydrogen, particularly the green hydrogen, to have to have better storage and other opportunities through this technology. So I will explain what are the major advantages with this technology as compared to only up to electrical energy, and also I will explain what are the challenges that we need to address before we go for this technology. So hydrogen, if you look at the hydrogen, it has a huge market, that is 120 billion in 2020, and it is increasing at a rate of 6.7%. So the major advantages of this energy carrier as compared to electrical energy is the storage. Storage is better as compared to electrical energy, and energy efficiency is very high with hydrogen, because like if you use hydrogen in fuel cells, you will get more than 80% efficiency, conversion efficiency, as opposed to, let's say, if you use a thermal IC engine, its average efficiency is 20%. So in comparison to that, we have better efficiencies with hydrogen as a carrier. So it has no environmental impact, because the side products that we are going to get with hydrogen as a fuel is only water. Okay, when we use it in fuel cells. So in addition to the energy that we get, so these are the major advantages, and other advantages as compared to electric vehicles is the range. Like we can get a higher range, because whatever amount you can store, that you can use, and you can refill the fuel quickly as compared to electric charging. So these are the two major advantages as compared to electric vehicles, and there are no emissions as compared to gasoline and diesel vehicles. So there are various types of hydrogen. Green hydrogen, that is obtained from solar and wind. I will talk about this little bit more and in the next slide. And there is a blue hydrogen, which is obtained by steam reforming of hydrocarbons like natural gas or naphtha, and then capturing the carbon or like carbon dioxide particularly, and storing it. Okay, so like this is basically with zero footprint, but we are using the conventional feedstock for producing the hydrogen. The conventional feedstock is fossil fuels for hydrogen generation as of now. Like more than 95% hydrogen is being produced from the fossil fuels. Okay, particularly methane and natural gas. Sorry, methane and naphtha. So, but I mean, if you capture the carbon dioxide while producing hydrogen, then that is called the blue hydrogen. So this is like color coding people have given. This is nothing to do with the color of the chemical. Color of the chemical is colorless. Okay, there is no color for hydrogen, but this color coding is given just based on the technology that we use to produce the hydrogen. Okay, so the gray. The gray hydrogen is without capturing the carbon dioxide, producing hydrogen from naphtha or the natural gas, and then black or brown hydrogen, that is produced from coal without capturing the carbon. And so if it is based on the color of the coal, some coals are black, some coals are brown. For example, lignite coals are brown. So that is based on the the color is given based on the color of the coal. And then pink hydrogen, that is produced from the nuclear source. Okay, nuclear reactors. Like the major use of hydrogen is in the fertilizer, okay, to produce ammonia. and by that way we produce fertilizers worldwide. Okay, so that ammonia is the basic component required for producing the fertilizer. So that production of ammonia requires hydrogen, and then we can use it as a fuel, like in thermal engines also, and we can use it as a fuel in electric vehicles, like I mean by converting it to to electricity by fuel cells. Okay, and then by combining this with carbon dioxide, we can produce the synthetic fuels. So these are the various uses of hydrogen. And then like now, so like Professor Iyer has already explained like what is the worldwide production of renewable energy from solar, particularly from solar and wind. So we can see here, I mean, about 630 gigawatts of power is being generated from solar, and about 650 gigawatts of electricity is produced from the wind energy. So now, if you look at the time during which we in a day during which we produce this electricity, that is basically off time as compared to when we require the this electricity. Okay, for example, here like if you look at this bottom left plot, you can see here this evening time is the peak time when we require the highest electricity, and morning time is the peak time, okay, when we require the electricity, okay, electric power. But now this production from this solar energy is not matching with the demand, the time of demand. So what people do to, like I mean anyway, like electricity is not like I mean as soon as we produce the electricity, we should utilize it, or we need to store it in batteries or in other forms. Okay, so batteries as of now, like I mean storing such huge electric power in batteries is not a viable option. So what people do is that like it will be stored as a as a chemical energy. For example, this electricity will be converted to hydrogen by using electrolysis, and then it is stored in the form of chemical energy, and then whenever it is required, it will be converted back to electricity by using fuel cells, and then be used. Okay, so that is like I mean for converting in this way, like people have used two ways. One is like complete electrolysis. Second one is photo electrochemical cells. Okay, to combine the two like two things, like solar as well as the electric conversion to hydrogen. So this is basically like I mean we are first converting the electrical and solar energy to electrical energy, and then electrical energy to chemical energy, and then as per depending on the requirement, we need to convert that back to electricity. So instead of that, what we propose is that like if we utilize a photocatalyst to convert the solar energy directly into hydrogen, then we have no need to go for like combining two technologies to generate the hydrogen, but we can directly convert the solar energy into chemical energy. Okay, that is hydrogen. So with this idea, so this is basically like I mean if you convert the solar energy to electrical energy and then electrical to chemical energy, that hydrogen that we produce from the electrolysis process is also called the green energy, and that is what now people are looking at, and people are like installing various installations at various places in the world to convert the electrical energy that is produced from solar energy into hydrogen. Okay, So that is called the green energy. Now, if we produce this solar energy to chemical energy, that is also called the uh, uh, um, green hydrogen. Okay, because we are producing hydrogen without any carbon footprint. Okay, so like the hydrogen which is produced without any carbon footprint is called the green hydrogen, and which is produced particularly from the renewable resources. Okay, renewable resources and without any carbon footprint. That is called the green hydrogen. So now, so we can utilize this direct conversion, but the major challenge in this case is the efficiency. Okay, so the major challenge, like when we look at this solar to hydrogen conversion efficiency, for which I have given the formula here. So the major challenge is the lower efficiency of this particular process. Okay, so as of now, the reproducible efficiency that is reported in the literature is about 1%. Okay, but we need to have about 10% solar to hydrogen efficiency to be competitive with the solar cells. Okay, photovoltaic solar cells. So now, if we look at where we are lacking, so you can see here that this is the solar spectrum, and here you can see less than the solar energy which is having wavelength less than 400 nanometers, that is UV range, is about 4.6%, and which is in the visible range is about 50%, and which is up to 1000 wavelength in the up to IR range, it is 74%. So now, if we look at the energy conversion efficiency as a function of wavelength, so like at 100%, let's say at 100% quantum efficiency, okay, apparent quantum yield 100%, then we see that to achieve if we use only UV light, then the maximum achievable solar to hydrogen efficiency is 2%. Okay, but to achieve this 10% solar to hydrogen efficiency, we need to utilize light with wavelength up to 520 nanometer. That means we need to utilize the light which is in the visible range. So we need to find out catalysts, okay, photocatalysts which are favorable to absorb light up to 520 nanometer wavelength. Okay, and then it should be absorbed, and it should be completely converted to hydrogen. Okay, so then we can say our solar to hydrogen efficiency will be 10%. Okay, so for that, the band gap requirement is 2.4 electron volts. Now, if we look at the materials point of view, so we can see here that so this is the band gap, like easy, like if we shine the light whose wavelength is more than the band gap, then we can say the electron will be transferred to conduction band from the valence band, and then if this electron is having energy that is more than required for hydrogen reduction, then water reduction, then it will be converted to hydrogen, and and similarly for oxygen, the valence band energy should be more positive than the water oxidation. Then we can say the water oxidation will take place. So in terms of material challenge, so we need to have so this is kind of band structure, the minimum band structure that is required for hydrogen production from water. Okay, so like I mean finding out material which is having this kind of band properties is really a challenging task, and which is or even after finding such material like production of hydrogen under stable conditions with that material is a really big challenge. So now what I will do is I will first discuss briefly about the particulate photocatalyst that we are developing in a batch reactor, and then I will discuss about the optofluidic devices that we are developing in this like in this research area, and then I will briefly discuss about the scale up of these optofluidic devices to commercial scale. Okay. Um, okay. So okay. So what we have done is like we have prepared this BI Vivo 4 with like with different facets. So with the good property of this BI Vivo 4 is that it has different facets, and we can separate the charge on this BI Vivo 4 based on the facets. For example, here if we look at this 110 plane and 1010 plane, so the electrons that are like when we shine the light on this BI Vivo 4, the electrons that are produced will be migrated to this 010 plane, and the holes produced will be migrated to 110 plane. So using this possibility on this photocatalyst, like we can synthesize the better photocatalyst by doping this material with required co-catalyst. For example, here we dope the like 110 plane with manganese oxide, and the other plane with CDS nanowires. Okay, so this CDS nanowires we have, CDS is cadmium sulfide. So these cadmium nanowires we have synthesized by using the hydrothermal method, and this BI Vivo 4 is synthesized using the again hydrothermal method, and this like we have incorporated this predominantly onto 010 plane on this BI Vivo 4, and this manganese oxide is deposited onto the 110 plane. So this is basically to I mean we like we can separate the charges, and if we like this manganese oxide helps in capturing the holes and helping the oxidation reaction, and CDS nanowires helps in taking out the electrons and reducing the water. So here these are some FESEM images. We can see the formation of BI Vivo 4 with required facets, and these are the nanowires, the cadmium sulfide nanowires. And then here we can see the after doping with manganese oxide, we can see the manganese oxide is predominantly depositing onto the 110 plane. Okay, and then this CDS nanowires are predominantly depositing onto the 010 plane. So we can we have done some electrical characterizations. Here we can see the chronoamperometry. So with this, we get about 2 milliamp per centimeter square current density with CDS and MN co-catalyst. Okay, so and that is the highest as compared to other materials that we have synthesized here. And then if we look at the Nyquist plot, we can also see the charge transfer resistance is the lowest with CDS, MN, BiO4. So if we look at the binding energy, I mean the XPS data, XPS analysis, we can see that the binding energy is redshifted when we incorporate the Mn and CDS onto BiVO4. Here we can see it is slightly, the binding energy is slightly reduced, and that of CDS it is slightly increased. So what it basically tells us is that like the interaction between BiVO4 and CDS is strong, and also like there is a electron transfer from CDS to BiVO4. Okay, so that basically ensures that there is a internal electric field formation between these two materials, and then we form heterojunction between these two materials. Okay, so and then so these are some results. Like we can see the effect of photocatalyst loading. So here, like I mean, we need to check the photocatalyst loading very carefully, because like there are two things. Like if we have a very low photocatalyst loading, then the amount is not sufficient to absorb enough light. If it is too high, then it will increase the turbidity, and like the inner part of the catalyst cannot receive the light. So because of that, if you see here, the optimum amount of photocatalyst that we can use is 100 milligram per liter. Okay, so with that we got 0.64 millimole per hour per gram catalyst efficiency, that is hydrogen production rate. And and we can see with this heterojunction we achieve the overall water splitting reaction. Okay, and like with 1:2 oxygen to hydrogen molar ratio. Okay, so like these are various catalysts, and here we can also see that the photocatalyst is highly stable with only about 13% efficiency loss after 3 runs. Okay, but I mean it should be improved little bit, so we are working on that. And then we can see this is the mechanism here. So there is a like I mean like when this heterojunction forms, there is a formation of internal electric field, and because of that there will be movement of electrons from CDS to BiVO4, and after shining with light, okay, after shining with light, there is a transfer of electrons from valence band to conduction band in both the materials, and then these electrons that are formed in BiVO4 will be combined with holes in the CDS. Okay, so by that way, like we can utilize the electrons that are formed in CDS to convert the water into hydrogen, that is water reduction, and the holes that are present in BiVO4 will be utilized for the oxygen generation. Okay, so so this is another material that we have developed, that is ternary heterojunction. So you know this graphitic carbon nitride is very interesting material, which is like metal free photocatalyst. Okay, so we synthesized this by using polycondensation method, thermal polycondensation method at high temperature, that is 550 degrees centigrade, and then we doped the silver by using photodeposition method. So here we can see a good improvement in the activity as compared to other photocatalysts. So this is basically because of two things. One is the SPR, okay, that is surface plasmon resonance of silver under UV light, under visible light, and also silver acts as a co-catalyst to take out the electrons that are formed in the in the photocatalyst because of the high Schottky barrier. And here, here, if we look at the stability of the material, that is very high. So you can see here there is only 3% loss in the activity after 3 runs. Okay, so these are also some co-catalysts that we have. I mean, co-catalyst assisted materials that we have developed in our research. And now I will discuss briefly about the thin film photocatalyst for water splitting reaction. Okay, by using optofluidic microreactor. Okay, so I will abbreviate it as OFMR. Okay, optofluidic microreactor. So, so these optofluidic device we have fabricated by using a simple technique. Okay, that is adhesive tape. We use adhesive tape as a mask. Okay, and then we utilized the like wet chemical etching method to remove the unwanted parts from the glass substrate. Okay, so and then we also used maskless lithography, where like we first clean the substrate and then we apply the photoresist, and then by using spin coating, and then we remove the unwanted parts by using the laser. That is, I mean, this technique, this instrument is present in our nano lab, so we used that, and then finally we etched the unwanted parts by using the wet chemical etching method. Okay, so for like as an alternative method, we can also use the PDMS replica molding. Okay, so these are some features that we got by using this maskless lithography. So you can see here, like we can obtain very nice micron level features by using the maskless lithography, and this is the like our optofluidic micro device that we have developed by using this maskless lithography. Okay, so we use two techniques. One is simple adhesive tape as a mask. Second one is maskless lithography technique. Okay, to produce the channels, and then after making the channels, we have immobilized the photocatalyst by using like I mean two techniques. But like we can, as you can see on this left hand side top, like we can use various techniques: drop casting, spin coating, dip coating, screen printing, okay, spray coating. So here I have shown the spray coating technique. So here spray coating is very interesting technique, and it is simpler, cheaper, as well as it can be scalable. Okay, and this can be utilized for any type of geometries. Okay, without much non-uniformity. Okay, and so that is that technique we use to coat this strontium titanate and strontium titanate. Okay, molybdenum BiVO4. So these are the steps that we use, and also we utilize the spin coating technique. Okay, spin coating technique generally we can use for the planar substrates. Like here you can see this is the planar substrate which we utilized for this coating. And we have also used the same technique, spin coating technique, for coating of the sol gel, CDS sol gel onto this kind of serpentine channels. And you can see here we have good uniform coating onto the microchannel, and also this coating is stable, quite stable during the reaction. Okay, so here, so this is after fabrication and coating, we like we make the complete device, complete optofluidic micro device. That is, like you can see, this is the catalyst coated plate, and this is the covering plate. in which like we have etched out some portion to allow the fluid to flow through the channel. Okay, so this is a planar channel. Okay, you can see the height of this groove is about 150 micrometers. So this is a planar micro channel in which like the liquid will be seems someone muted. Okay, so am I audible now?
Yes, sir, you're audible.
Thank you. Right. So so then like through that micro channel, like we flow the liquid, and here you see like this is these are the inlet and outlet tubing, okay, through which the liquid will be entered and come out of the reactor. So this is another view, like I mean, so this is the like I mean so this is the complete top plate, and this is the complete device after incorporating the catalyst plate. So here you can see this complete assembly is put together by using the UV glue, and so here you can see this is during the reaction. Okay, so the water is flowing through, and then like there is formation of hydrogen. So these bubbles you can see here, and from the other side it is coming out. So this is these are the steps. Okay, yeah. So this is the kind of experimental setup that we used. Okay, so here there is a syringe pump to pass the liquid through the microreactor. So if we want, we can pass the liquid through two channels, so that like we can adjust the flow rate, or the other inlet we can utilize to have the gas through the reactor. Okay, so that like we can have some kind of multi-phase flow in the reactor, multi-phase what you call slug flow, so that the mass transfer kinetics will be much faster. Okay, that also we have tried, but those details I'm not giving here. So here these are some results with this optofluidic device. So you can see that by increasing the thickness of the film, like up to 1.6 micrometer, the the uh, the activity is increasing. Okay, and then like we have like we are also now we are testing up to 25 times coating. This coating basically like we have coated this using the what you call spin coating. So the thickness of the coating after each step, after each iteration is very low. Okay, so the after 8 times coating, it is only 1.6 micrometers. So okay, so we are inventing other techniques to avoid this issue, because like one issue is very low thickness, and also it is very time consuming. So as an alternative, we can utilize the spray coating method, but with that spray coating method there are some other issues. So we are at present we are utilizing only spin coating method to do the coatings. Okay, so here we can see uh, so the hydrogen production rate, the maximum hydrogen production rate that we achieved is 2.2 millimole per hour per meter square. Okay, so here also like we tested at different flow rates. So we can see that the maximum hydrogen production rate is 2.46 micromole per hour per centimeter square, and it is increasing with the increase of flow rate. Because of the other issues, we could not be able to increase the flow rate further, but we have I mean, the activity, we have seen the activity increasing with further increase of the flow rate. And we also tested various geometries, channel geometries like serpentine channels, this planar reactor with posts or pillars in the channel, and planar, only planar reactor. So here we can see there is a good activity with serpentine channels. That may be because of the good mass transport with such channels. So here, the major difference that we get, is that when we use when we use flow through the channel, in the case of batch reactor, we are keeping the water stagnant, so we have we don't need any pumping of the fluid. But in the case of optofluidic devices, we need to pump the fluid continuously through the channel, so that basically consumes some energy. So that is basically people say that is one considerable factor because of the considerable amount of energy that we consume in this pumping of the fluid. So we calculated that power consumption by using the Huygens-Poiseuille equation for calculating the pressure drop. And if we look at based on our production rates, the amount of power that is consumed is about 31%. Okay, which is very significant as compared to what we are producing now. But as I mentioned earlier, for this technology to be economical, the production rate of hydrogen should be 130 micromole per hour per centimeter square. So at that production rate, the power produced is 77.5 milliwatt, and the power consumption for the pump is the same. Okay, so we use the same flow rate, everything same, but only we need to change the material to increase the efficiency, so as to obtain a production rate of 130 micromole per hour per centimeter square. So with that production rate, we use only 1%, about 1% of the power for pumping the fluid, which is quite okay. So now coming to the numbering up, so far I discussed about only a single reactor, a small reactor, which is producing only very small amount of hydrogen. Okay, in the scale of micromoles. Okay, like 2-3 micromoles in one single unit. So now you may be skeptical that how this is sufficient to be economical. So now I'll show you a few slides through which you can see how this numbering up of the small reactor that we have developed will be sufficient to produce hydrogen at a larger scale. So there are if you look at this scaling up versus numbering up, there if we use the conventional way of transforming the small reactor to bigger reactor, that is called the scaling up. So there what we do is we increase the volume of the reactor, keeping only a single reactor. But in the case of numbering up, the volume of the reactor is the same. The volume, shape, geometry, everything will be same. But we increase the number of the reactors to increase the production capacity. So here you can see this is the scale up strategy. So we are increasing the size of the reactor, volume of the reactor with single reactor. But this you can see here, this is the numbering up of the reactor. So here we have this is the single reactor. Let's say that is what we tested in our laboratory. Now we increase the number of such reactors, okay, for numbering up, and then by that way we increase the capacity to commercial scale. Okay, so the numbering up having different ways. Like here we can see external numbering up and internal numbering up. So external numbering up means like we increase the number of such reactors, okay, externally, like we increase the number and then we connect these reactors by using the tubing, just like you see here in the figure B here. Okay, so we connect the individual reactors through tubing so that we pass the liquid and we take out the liquid and the product. And in the case of in the case of uh, internal internal numbering up, what we do is we increase the number in the reactor itself. Okay, within the reactor we increase the number. So again this numbering up is of two types. One is parallel and another one is series. Like you can see here, this is numbering up in series, and here you can see this is numbering up in series. Okay, this is in parallel and this is in series. So like that we can take the capacity to commercial scale. So there is one example, like already people have done that. So here we can see like first there is one small module, and that small module is numbered up to increase the capacity. So here this entire module is of 1 meter square. Okay, and individual one is about like one tenth of the meter square. Okay, so that way we can have numbered up system which will give us the required capacity of hydrogen. So here this is one example from Professor Domen's group in Japan. So they have increased the capacity to up to 100 meter square scale. Okay, and by that way they produced a good amount of hydrogen using such system. But still actually this is not yet economical, as I told you in the beginning. So this is not yet economical because of the lower efficiency of the catalyst. Okay, so there is no problem with the device integration, but there is a issue with the material. Okay, which needs to be whose efficiency needs to be improved. And then like we need to test various devices. Okay, various configurations to improve the efficiency in terms of mass transfer. Okay, for example, mass transfer as well as in terms of removing the gas without any obstacles. So here we so these are some kind of proposed designs. So you can see here, this is the parallel, these are the parallel channels with with inlets and outlets, and here these are the staggered micro channels with small micro channels and in a staggered way. So here this is another type of design, that is with micro pillars. Okay, and then these are the staggered micro pillars. And then so like after making this one device, after finalizing this one reactor, we can integrate these reactors to make one module of the micro reactor. Okay, micro reactor array or network we can call it. And then we can make this like I mean into a complete system. Okay, where we pass the liquid through the sun. So if you look at here, this is something similar to the photovoltaic cell. Okay, so this is exposed to sunlight, solar energy, and then this converts the solar energy directly into hydrogen. So that is the major advantage of this device as compared to photovoltaics followed by electrolysis. Okay, so there we are using two different devices, but here we are using only one device for the entire conversion of solar energy to chemical energy, that is hydrogen. So after converting that chemical energy, so we we separate the oxygen and hydrogen by using polymeric membranes, and then we store them. So this is another view of this proposed design. Okay, so with that I would like to conclude. So here we developed phase-set selective photocatalysts, and then we also developed optofluidic devices using various techniques, and so these optofluidic devices are easily scalable. Okay, so with that I would like to thank my students, Amir is the one who is presently working on this, and Devipriya recently graduated, and she worked on particulate photocatalytic system, and then Prasad is also working on optofluidic devices, and then there is one more student, okay, Rambabu, Ponnala Rambabu. He is also working on the optofluidic devices. So with that, I would like to thank the committee once again, and I will take any questions you have. Thank you very much.
Thank you, sir.
Thank you so much, sir, for your valuable talk. We'll now take questions from the chat box. So our first question is from Ramesh Babu. He says, what are the different fluid specifications? What are the different fluid specifications are required for hydrogen evolution?
So basically here we need pure water. Okay, that is the only specification. Like there should not be any contamination. For example, there should not be any kind of any particulate matter in water, so that like if there is any particulate matter that may contaminate our reactor, like because our reactor is very small, so that may clog the reactor. That is one thing. And second thing is this particulate matter may absorb onto the photocatalyst and may reduce the efficiency of the photocatalyst. I think that is the only requirement is it should be pure water. Yeah. So I think, is that the question that he asked? Did I answer the question?
Yes, sir. Thank you so much. So our next question is from him again. So he wants to know these microfluidic outputs can interface to. Sorry about that, sir. These microfluidic outputs can interface to any digital control systems.
Yes, of course. Like why not? We can very easily interface with the digital systems. Like we need to do that. Because there are various challenges in this optofluidic devices. For example, we need to the first challenge is how to separate the water and gas efficiently. Okay, like water and gas are coming out, like let's say from the outlet of the reactor. So we need to, first thing is we need to separate these by using a good control. Like for example, we need to look at the we need to have a hydrophobic material coated tube at the outlet, and then we need to have a two outlets. Like one will be taking out the gas, okay, that is having hydrophobic coating, and second one is having liquid. So we can see, like by controlling or by using the some kind of sensors, for example humidity sensor or some gas sensors, we can see what is the amount of moisture that is still going into the gas phase. Okay, that is one thing. And second thing is we can control the flow of water based on the required amount and pressure drop. Okay, and then we have to have hydrogen sensors, because this hydrogen is very light and also this is very hazardous. So we need to have sensors at each and every place in the system in order to detect the leaks of this hydrogen and take preventive action like through these sensors. Okay, so there is a huge scope to integrate this kind of sensors and controls. Okay, for this system. Yes.
Thank you, sir. We have two more questions from Professor Arun Tej. So he would like to know, could you elaborate more on the origin and the role of surface plasmon resonance in ternary heterojunction method?
Yeah, so this is basically, so surface plasmon basically, let me go to that slide. It's taking a long time. Um, uh, so this surface plasmon is due to vibration of the electrons. I I forgot. This is. Uh, okay, I will discuss this with Arun. Okay. Next question, please.
Definitely. Question is, yeah. So the next question is it possible to scale up the OFMR production for practical application? If so, please elaborate.
Yeah, I think I elaborated a lot on this. Basically, as I have elaborated on the scale up techniques and our proposed designs. I hope like it is clear. But yeah, but only major hurdle is the efficiency of the photocatalyst. Like if we get the photocatalyst efficiency up to 10%, then this can be economically done. Okay, this like what you call this scale up can be economically done by using our optofluidic device. But we need to, meanwhile we need to address some of the challenges that I discussed just now. Like we need to, for example, we need to have we need to integrate different sensors and different controls into the system, so as to have a better efficiency, like better overall efficiency and better capture of the hydrogen and oxygen. Okay, so I think that is.
Thank you, sir. We have a last question from Gopal Rizal. Sir, he was asking, could you please elaborate how SPR enhances photocatalysis?
Okay, so basically SPR enhances photocatalysis because it is it is okay, I don't have that slide, but when we see the light absorption, so the SPR basically, because of the SPR of silver, we we have absorption of light in the visible light range. Okay, so because of that, the overall absorption of light increases, and that helps in generating more electrons in the system. So that more electrons will help us in increasing the hydrogen production by reduction of water.
No, that's.
Thank you so much, sir, on behalf of all the participants for answering all the questions and for the enriching talk. We'll now move on to the next speaker.
Okay, thank you very much.
Our next speaker for the day is Professor Uday Narayan Mehti, and the title for his talk is Surface Modification of Nanostructures for Efficient Electrocatalytic Water Splitting. Professor Uday Narayan Mehti is currently an assistant professor, Department of Physics at IIT Guwahati. He has obtained his bachelor's from Vidyasagar University, master degree from Jadavpur University, and PhD from Jadavpur University. He is currently serving as an assistant professor in the Department of Physics at IIT Guwahati. He worked as a D.S. Kothari postdoctoral fellow jointly with Jadavpur University and Kalyani University, as a postdoctoral researcher in the Department of Materials Science and Engineering in Korea Advanced Institute of Science and Technology, South Korea, and as a research fellow in the Institute of Basic Science in South Korea. Of all the numerous awards awarded to him, a few recent ones include the IBS Outstanding Researcher Award 2013, awarded by the Institute of Basic Science, Republic of Korea, and the Young Scientist Award 2010 was awarded to him by the Material Research Society of India. His research emphasis involves cutting-edge nanomaterial research for real practical application that includes energy storage and conversion, catalysis for environmental remediation, nanomaterial-based modern electronics. With this brief introduction, I would kindly request Sir to elaborate the topic, surface modification of nanostructures for efficient electrocatalytic water splitting. Over to you, Sir.
So thank you very much for your introduction. So let me share my slides without spending much of time. So, so, so is it necessary to upload it in a share option? I could not share my screen directly.
So you can share your screen.
Yeah, but
Yes, sir, it's visible.
It's visible. Sir.
Yes, sir.
it's visible.
Yes, sir.
So thank you for the your introduction. So myself, Uday Narayan Mehti, I belong to Department of Physics, and today I shall be discussing on surface modification of nanostructures for efficient electrocatalytic water splitting. Already you have seen that electrosplitting by already Professor Pilla has discussed the electrosplitting by the photocatalytic effect, but I shall be discussing on electrocatalytic effect. So before I start, I would like to take this opportunity to introduce my group here. My group consists of 8 PhD students, 6 are listed over here and 2 have recently joined. And these are my collaborators from India and abroad. Here is our focus of our research group. We mainly work on energy storage and catalysis. For that, we develop the advanced nanomaterials and also the self-assembly of the nanomaterials in the macroscopic scale, because the nanomaterials, I mean, it's hard to use the single nanomaterials or the bulk nanomaterials. Assembling them in a macroscopic scale is always important. So we do work on the assembly of the 2D materials like graphene, and also 2D materials based on the carbide materials like titanium carbides, the hydrogels, and these hydrogels are mainly used for the energy storage application. We also do work on the electronic tuning by designing of advanced nanomaterials by heterostructures and single atom electrocatalyst. For the these are mainly for the catalytic application, and we also employ the density functional theory to understand that what is going on at the atomistic level. So in this talk, I shall be mainly discussing on the electrocatalysis based on the single atom as well as the heterostructures. Here is the layout of my presentation. So first, I shall be discussing on that what is the need of catalytic water splitting, and particularly hydrogen and oxygen evolution reactions, the two half reactions. I shall elaborate a bit, and then I shall show that there are a couple of advanced nanomaterials which have been used for the HER and OER catalysis, which I shall introduce in one by one, and also discuss their merits and I mean how their efficiency can be improved. And finally, I shall conclude. Now the question is that why we need the water electrolysis. The important thing is that because of depletion of the fossil fuel, we are heading towards the renewable energy technology like solar, hydropower, and wind power. But the thing is that these are intermittent in nature. You cannot blow the wind on demand, and sun is not there in night. So you have to store the converted energy in terms of something, either in a energy backup or in terms of some fuel. So in this case, we can actually convert this converted energy to break the water molecule into hydrogen and oxygen, and this hydrogen actually could serve as the energy carrier, so that we can use this hydrogen fuel in different purpose, like the fuel cell, aerospace industry, or chemical industry. Another important thing of making this hydrogen as a fuel is that it is a green fuel, so that whenever it is used as a fuel, it does not produce a carbon dioxide like a combustion of the fossil fuels. They just produce the water molecule. And also another important thing is that when the hydrogen is burned or just combusted to get the water molecule, it generates a lot of energy within a short time. That means the power is very high, which you cannot achieve that high power with these energy conversion devices. So whenever you need a large amount of energy within a shorter time, so the solar and the wind power, they cannot give you the high power density, so you must go to the other technique. So here is a possible technique, and the coupling the solar with the electrolyzer actually can gives you a sustainable energy solution for our sustainable future. This, to split the water molecule, there are two reactions involved. Here I have mentioned that the splitting of water molecule can produce the hydrogen and oxygen, and this production of hydrogen is known as, this reaction is known as the hydrogen evolution reaction, whereas the oxygen evolution reaction happens at the other electrode whenever a voltage is applied to break the water molecule. So the necessary energy to break the water molecule is actually so just I am presenting, okay? Yeah. So here the HER and the OER, there are two half reactions involved. So the water molecule can be broken if energy is supplied. So energy is supplied by the battery, and thermodynamically to break the water molecule it requires 1.23 electron volt, 23 volt, and practically it requires more than 1.23 volt, like the 2 volt or more, because there are some energy barriers involved at the surface of this catalyst. So for example, for hydrogen evolution reactions, there are certain elementary steps involved for the hydrogen evolution reaction. It's not just breaking of the water and to get the hydrogen. So in an acidic electrolyte, this H plus ion first needs to adsorb over the surface of your catalyst. So this is the catalyst surface, and hydrogen adsorbed over it. And then in the second step, there are two possibilities can happen. Either another hydrogen adsorbed, and these two nearby hydrogen actually bind together to give you the water molecule. This is one possibility. And another possibility is that one hydrogen adsorbed is there, and it takes H plus ions without adsorbing this H plus ion, and gives you the hydrogen, gives you the hydrogen molecule. So these are the two different steps. This is known as the Tafel steps, and this the lower one is known as the Herovsky steps. But Tafel step, this is the kinetically this is more faster. So always people want that the electrocatalytic reaction should happen with the Tafel slope, so that the larger kinetics or the high rate of generation of hydrogen can be obtained. and also the energy cost for this extra energy cost for this surface reactions to happen should be minimum for this Tafels kind of reaction mechanism. And on the other hand, for oxygen evolution reactions, this is more complicated. It involves the several possible steps. Like for this one is an example in the alkaline medium. So this is our catalyst surface, and whenever in the alkaline media there are OH ions are there, and these OH ions get adsorbed over the the surface of the catalyst, and once it is adsorbed, then it takes, it removes one electron from it, and then there are successive steps like another adsorption of the OH, this dehydration of this OH to the O atoms, and then it also again combines with another OH to make OOH, and finally it actually releases one oxygen molecule to come back to the initial stage. So all these processes, successive steps, actually involve some energy barriers to cross. Okay, so these energy barriers we can easily calculate it by the change in Gibbs free energy for this particular system. And lower the Gibbs free energy, it is better because that means it requires a lot less energy for this catalysis process to happen. So here first I am going to introduce one important catalyst for the oxygen evolution reaction, because I have discussed the hydrogen evolution and oxygen evolution reactions. But out of these two reactions, oxygen evolution is the more energetically demanding. So the development the OER catalyst is more necessary than the HER catalyst. Definitely there is a lot of development has already been done in HER catalyst, and there is also a room to develop high performance HER catalyst, but the OER process, it is much more challenging. So here I am first introducing the one kind of such OER catalysis which we designed from the metal organic framework based nanostructures. And for this one, why we have chosen the MOF and the nanostructures of MOF, the answer is here. First of all, as you can see in my previous example, that all the surface adsorption happens on the surface. So if you make a high specific surface area catalyst, like instead of this bigger cubic, you could make some thinner nanowire kind of things, then you can have within the same volume, similar volume, you can have a large surface area. So you are allowing the reactant molecules to adsorb over the surface. So the high surface area is much more important, and not only that, these nanocatalysts cannot always have a high conductivity, because whenever there is an electron flow through this catalyst, there will always be some resistive drop through this. So how to minimize this resistive drop so that the energy consumption is less? So these nanostructures can be actually added or coupled with some conducting backbone. For example, in this case, we have used the graphene as a two-dimensional sheet, which is a conducting backbone, and we did actually use the nanostructures of the metal organic framework. But instead of any other nanostructures which is being used for the electrocatalyst, we have chosen the metal organic framework for the following reason. Because this particular structure is actually having the mesopores, like not only this rod-like structure, it can have some pores within its surface. So you can actually maximize the surface area to have the electrocatalytic application for this kind of systems, and these MOFs actually also can go some in situ reconstruction during the catalytic application, which I am going to discuss in a coming slides. But the obtaining this kind of metal organic framework with some desired anisotropic structure is highly challenging. People use the different surfactants to block the surfaces, some surfaces of the ingrowing nanocrystals, so that there is some anisotropic growth of the nanocrystal. But in this case, we have used some technique where without using any surfactant, just using a hydrogel, the graphene based hydrogel as a reaction media, we can control the growth kinetics, so that we can get some MOF nanostructures, and those MOF nanostructures connected with the graphene can be used for the high OER catalysis. So let me just discuss that briefly, that how we have obtained these MOF nanostructures, which is otherwise challenging in certain reaction steps. So for this, we first relooked that what is the mechanism by which this metal organic framework actually get developed. So in this case, we have found that whenever it is any reaction happens for any nanocrystal development, the reactant molecules do interact or react very quickly in this case, and as a result of very quick reaction, actually they grow in some random nanocrystal kind of fashion. But whenever this is another example of the interfacial reaction process in which the water and organic phase, they are separated to each other. This is very well known, the organic aqueous phase reaction process. So in this case, because the two different kind of reacting molecules are confined in two different media, so they cannot react immediately. They has to diffuse from one media to another media, and because of this diffusion, the diffusion coefficients of those molecules decreases, and they can gives rise to the slow and controlled reaction steps. And as a result, this aqueous and the organic interfacial diffusion can give rise to the controlled nanostructures, which is impossible or hard to get with the aqueous phase. Now we have taken this example of the organic phase aqueous phase biphasic system, and we have posed the question, what will happen if we replace this aqueous phase with some network of the structure which is a graphene hydrogel. Graphene hydrogel is nothing but a soft material made of graphene nanoseeds as shown over here, and within the graphene nanoseeds water molecule are stably bound. So instead of using a bulk aqueous phase, if we replace this bulk aqueous phase and use this graphene hydrogel as some medium, because the water is already entrapped within the graphene hydrogel system, if we do this interfacial reaction, what is going to happen? We anticipated that if we do it, so there will be a further control of the diffusion of the molecules by the graphene surfaces, and there may have some interaction of those molecules with the graphene surfaces which may control the growth of the nanocrystals, so that the hard to achieve the nanostructures of MOF can be done by this simplified process without using any surfactant. Actually, to validate our assumption that whether it is possible or not, we employed the MD simulation study, and we have checked that this is the aqueous phase, aqueous organic phase reaction systems. One is aqueous and another is organic, and these color things, these are some molecules, and we have tested the diffusion of the 2-methyl imidazole, some ligand which is used for the growth of the metal organic framework. We have found that they can actually diffuse very quickly to the aqueous phase, but whenever we employed it, we replace this aqueous phase with a hydrogel phase, then the diffusion of the molecules is actually lowered, and we have checked that the diffusion coefficient is actually lowered by 1 order of magnitude. So there will be a much slower reaction which allow the nanocrystals to grow with its own crystal habit. And also we have checked that, and this is the interfacial diffusion, we have also checked the diffusion of the molecules through the hydrogel itself, and whenever these molecules are diffusing within the hydrogel, not through the interface, then there is also the molecules have some interaction with the graphene surfaces, and these interaction, the magnitude of this interaction strength we have also calculated by the MD simulation, and we have found that there are two kinds of interaction involved with the graphene surface and these ligand molecules. One is the electrostatic interaction and one is the van der Waals interaction. And we have also calculated, because this 2-methyl imidazole, they react with the cobalt ions which are entrapped within the hydrogels of the graphene, they can produce the ZIF67. This is a cobalt based MOF, and we have also checked that whether this in the generated ZIF67 has also some interaction with the graphene surfaces or not. We have found that it also has some interaction with the graphene surface, and with this we have tested the several strategy like the aqueous diffusion, the two molecules confined in the in the aqueous phase, this is a common methodology. You can see that most of the structure of the material developed, they are irregular in shape, and we have then changed the aqueous diffusion to the aqueous organic diffusion. One phase, the cobalt ion is confined in the aqueous phase, whereas the organic ligand is actually confined in the organic phase. Then these are the different kind of metal organic frameworks. This is first one is the CuBTC, and this one is the ZIF67, this is ZIF8, and this is the trimetallic BDC trimetallic MOF. In all the cases, you can see that some regular and some anisotropic structures can be obtained, particularly for the first one and last one. These are impossible to obtain by the conventional techniques. And with this, out of this, all the MOFs we have, the generic process we have developed, out of this, we have particularly tested the final one, which is the trimetallic MOF. And this trimetallic MOF, here we have used the cobalt, nickel, and iron as the metals. These are some metal nodes are here, and they are connected by some organic ligands. For the organic ligands, we use the BDC, and this particular structure we have obtained, and this is the corresponding the XRD pattern of it. And this XRD pattern, because this material was not developed earlier, the pattern was not available. So we did we actually, depending on its composition, we
Uday, you have muted yourself.
right now, okay?
Yeah, fine.
Yeah. So is right now or from previous? For this,
no, just a few seconds, just few seconds only. This slide. Go ahead. Yeah.
Okay. So because this particular the trimetallic MOF was not available, so so the XRD, the standard XRD data was not available also. So based on this, its composition and this other structural information, we have actually made some structures and find the simulated XRD pattern, and in the simulated XRD pattern actually matching with our experimental MOF experiment, the XRD of the experimental XRD. And we have found that this is actually the triclinic in nature with a space group of P1, and this is a typical such unit cells. We have problem actually. Whenever I'm trying rather, it is actually muting. There is some technical issue.
It's audible now, sir. You're audible, sir.
I'm audible, but I cannot go to the next page. Whenever I am clicking, actually it is not going to the next page. Instead, actually it is...
Try sharing again.
Yeah, sir, you can try sharing again.
Okay.
No, you must press escape. Yeah. Because of this, this pointer, I think that is happening. Anyways.
Is it okay right now?
Yeah.
Yes, sir.
What's happening?
Is it moving? No.
No,
right?
Yeah.
So press escape. Press escape. Escape, go to the cursor mode. Press escape. Now you click on the presentation. Did you press escape?
Yes. I pressed escape. Yeah.
Click on the presentation. But why do we see the cursor? Now you click. Yeah. Now it will change. Yeah. Yes.
Is it okay? Yeah.
Yes, sir.
With these MOF structures, we have checked this oxygen evolution reaction of this particular MOF structure which we have obtained, and we expect that this should give the good the oxygen evolution catalyst because of the following reason. First of all, it has all these metallic nodes, and we expect there is some synergistic behavior between these metallic nodes, and they are coupled with the graphene, and graphene gives some electronic highway so that there is a less energy consumption or the less energy for this catalysis process. Here is the OER activity. This is the linear sweep voltammetry, and here you can see that this voltage, actually the applied voltage is plotted with respect to the RAG, and you can see that the out of the all possible catalysts, this is the TMPG, actually gives this trimetallic MOF linked with the porous graphene, which we obtain from this hydrogel based system after the freeze drying, and this one and another one, this one is the trimetallic MOF, which is not coupled with the graphene structures, and these catalysts are also deposited over the nickel foam as a current collector, so that the comparison with the nickel foam and only the porous graphene is also presented over here. And from this one, you can see that the requirement of the voltage for getting the higher and higher current is the requirement is less for this the trimetallic MOF coupled with the porous graphene, whereas they are much higher in the other samples in comparison here. And to study the kinetics of this high catalytic reaction, we have plotted here the Tafel slope. Actually, this can present and give you the idea that how fast the reaction is going on, and actually it is actually representative of the slope of those curves. And from here, one can see that the over potential, that is to get the 100 milliampere per centimeter square, the extra potential needed to get over the thermodynamic requirement, it is the 255 millivolt, whereas to get the 100 milliampere per centimeter square, it requires only 300 millivolt. And the Tafel slope is also less, so 4.3 millivolt per decade. It shows that this catalyst which we have developed, actually they are performing. And to check that what is the origin of this high catalytic activity, we have checked the EIS spectra, the impedance, electrochemical impedance analysis we have done. From that, you can see that this particular curve, which is actually this one and this one, these last two here at the bottom, these both belongs to the trimetallic MOF, and one is coupled with the graphene and another one is not coupled with the graphene. But both the cases, this trimetallic MOF actually cutting this real axis at a much smaller resistance, it shows that the charge transfer resistance RCT value, that means which actually indicates that how what is the efficiency by which the charge transfer can happen between the catalyst and the adsorbing species, actually can be judged from this charge transfer resistance, and charge transfer resistance is low for both of these trimetallic MOF cases. And we have checked also the stability, as you can see that we have checked up the 24-hour of stability, and it is showing the current density with some constant at a constant potential. The current density remains nearly same, and the stability also can be checked from this LSB curve, linear voltammetry curve. After 24 hours of stability, both the curves are actually exactly matching with another one. And we have also inspected the origin of this high catalytic activity by by checking that what is happening in its structure, by checking the by making the TM observation, and also making the X-phase observation. What you can see that this is the MOF structures, which are trimetallic MOF coupled with the graphene before the electrocatalysis process. But once it is actually the electrocatalysis has been done, you can see that these rod-like structures right now, actually there are some small white spots you can see. This is actually becomes more porous structures. So from here we can expect that there is some phase evolution happens, but the distribution of this the nickel, cobalt and iron remains very uniform throughout. And we inspected the X-phase. From the X-phase we see that there is a significant change in the composition before and after the OER process. The before and after the OER process, before OER, this consists of the cobalt 2 plus and the cobalt 2 plus states is there. But whenever we did the OER analysis, after OER, we have found that actually there are the 3 plus states appearing, and these 3 plus states is actually corresponds to the nickel, the cobalt oxyhydroxide. Okay, and also the same thing happens for the nickel and iron. I have shown for the nickel only here. So all the cases we have also checked the XRD pattern. Also, we have found that this trimetallic MOF is actually changing to the hydroxide and oxyhydroxide phase with a lot of porosity. So in the previous report, whoever reported the MOF based OER catalysis, they actually give the different mechanism. They gave that the catalysis is actually originated from the conductivity of the MOF, all that, and the linker, actually different linker can play certain roles. But we have found and we have reported that it is actually not related to some linker. So whatever the linker is there, which can control its growth, but ultimately it turns into the oxyhydroxides and hydroxide structures with a lot of porosity. So main origin is coming from its porous high surface area structure, not from some ligands. Ligand does not play any role. It actually changes to the hydroxide and oxyhydroxide structures. But in this process, this in situ activation process actually gives rise to the I mean very easily you can get some MOF structures and also the very highly perforated structures you can get it by this electrochemical activation process. Now with this, we are going to I'm going to discuss another catalyst which is actually made for the HER catalyst, not for the OER catalyst. So in this case, instead of using the MOF, because instead of using MOF, we are going to use the HER catalysis because the HER mechanism is different. So the requirement is also different. Here, based on the requirement, we have actually designed the catalyst a heterostructure catalyst, where there is a base structures, and on the this is a this is a base structures, and base structures there are some vertical nanostructures is actually situated over it. So the base structures is the nickel cobalt selenide structures, and these vertically aligned structures, standing structures are the molybdenum selenide structure. But this kind of heterostructure, whatever the people have reported, actually any heterostructure they used to use the two different methods. Like first they grow the structure one, and then they deposit another structure to make this heterostructure. This is the conventional design of the heterostructure. But we have used a different strategy. We have taken a mixed metallic oxide compound which contains this molybdenum, cobalt, and nickel based oxide compound, and we have taken this molybdenum based one because it has actually the larger difference in the atomic radii compared to the cobalt and nickel, and we tried to see that what is going to happen if these particular structures we make some chemical changes. If we do some selenization of this structure, what going to happen? We have found that interestingly this mixed structure actually dealloyed, and the lower structures becomes the nickel cobalt selenide, and the vertical structures becomes the molybdenum selenide structures. This has happened. And here the important thing is that instead of the previous one, conventional structures, here you can have the precise atomistic interfaces. Here is the ACM image which can give you the visual guide that what is going on over here. The first one, these are the some ultra thin sheets of the nickel cobalt molybdenum based oxyhydroxides, and the whenever it is selenized, you can see that the same bigger sheet like structures are over here, but on each of the bigger sheets you can have some crumple of sheets. This it is a higher magnification, you can see that this is the bigger sheet, and there are certain the tiny sheets decorated all over the surface. So we have checked that what is these tiny sheets which are actually erected from the basal sheets. And from the TEM observation, we have found that these erected nanoseeds, which you can see over here, actually these are some kind of layered structures, and the separation of the layer is around 0.78 nanometer. And this one, and also the basal structures, we have also checked with the atomic resolution TEM microscopy, and we have checked that the basal structures on which these kind of the tiny sheets actually erected from the base structure, this base is consist of nickel cobalt selenide. So, and this interplanar spacing corresponds to the nickel cobalt selenide. And also you can see that during this conversion there are some defects arises over here, like a twin boundaries are here. This is the another crystalline domain, and this is the two different crystalline domain, but they are not matching over here. That there is some the twin boundary is present here. To also check that whether these sheets are MoAC2 or not, we we initially thought that it should be MOH2 because the selenium is there and molybdenum selenide also show the layered structures, but this interplanar spacing is little bit larger than the bulk value. So for bulk it is around 0.64 nanometer, whereas for this particular structure it is a 7-8 nanometer. So we have checked the other investigation that whether this is MOH2 or not. So here this is the Raman spectra. From the Raman spectra, the presence of this A1G and this is the E2G peaks are there. So A1G peak, this is the structure of the molybdenum selenide. These are the molybdenum and these are the selenide, this yellow color. So whenever there is an out of plane vibration, this A1G can appear for the MOH2 at this particular position. Whereas the E2G peak can happen due to the in plane vibration, and this one is the out of plane vibration. And not only this one signifies that there is a presence of the molybdenum selenide, it also signifies that the structure of the molybdenum selenide, they are the edge oriented structures. They actually grow vertically, which we have seen in the ACM image as well as the confirmed from the TEM. Because the intensity of the A21G, whenever this is much higher than the E2G, this signifies that this one is that this vibration is the dominant, and this actually corresponds to the vertical growth of the molybdenum selenide over the base of the nickel cobalt selenide. But interestingly, we could not found any XRD pattern. We could not found any the peak corresponding to the MOH2. Then, because of the fact that there are some variation in the D value and the lesser crystallization, so we have actually checked within this region with a very high resolution XRD, because we thought that it should be possibly be here corresponding to, we inspected the HRTM and from there we thought that it should be possibly be there. You can see there is a hump in here. So this hump actually also corresponds to the MOH2. And this is a possible structure which we have shown by this ball model. This vertical one, these are the MOH2, whereas the below one, this is the nickel cobalt selenide. And this particular structure is very interesting because the nickel cobalt selenide actually is known for its metallic conductivity. It can show the metallic conductivity, and over it there is a molybdenum selenide which is vertically oriented. The vertical orientation of the layered structure is very important. Why it is so? If these MOH2 just form over like this one, not vertically, edge oriented, then whenever the charge carrier need to go from one layer to another layer, it has to jump, it has to hop from one layer to another layer. It requires some potential barrier because this is some van der Waals barrier is there between these two layers. Whenever they grow like a vertical case, without hopping from one layer to another layer, the electrons can go to the catalytic active edge sites, avoiding this interlayer hopping. Okay, and with that, and because the MOH2 is already known for the high catalytic activity, and people also predicted that the edge sites of the molybdenum selenide are good catalyst. So we thought that this particular structure can be a good HR catalyst. And according to our expectation, actually it shows very high catalytic activity. You can see from the linear sweep velocimetry curve as compared to this oxide-based catalyst nickel foam or nickel foam. You can see that the current is actually going very faster rate as compared to the other catalysts. And also the Tafel slope is also lower. It also signifies that there is a good kinetics is there. The reaction is happening at a faster rate. And it is also evident from this the EIS analysis. You can see that for this our heterostructures, the charge transfer resistance is much low as compared to its oxide counterpart, which actually indicates that there is a preferential or beneficial reactivity is going on the surface, and it also has a good stability. And here is some parameters which indicates that how efficient our catalyst is. And this eta 10 indicates that the overpotential which is required above the thermodynamic requirement is only 89 milli electron volt, which is much lower as compared to this oxide based one, and obviously corresponds to the corresponding to this nickel foam, which is used as a current collector, or the over which the materials actually have grown. Here is also you can check the performance of our catalyst as compared to some state of the art catalyst. And because there are two important factors for any catalyst. One is not only it can give the current density at a lower over potential, also the Tafel slopes should be higher so that the reaction kinetics is much faster. So in this case, in our samples actually is much better than many of the high performance catalysts which are available in the literature. And we have checked that to the density functional theory and to know what is the electronic origin of this high HER activity. So here we checked that first we checked, as I mentioned, that our molybdenum selenide has a larger expanded interlayer spacing as compared to the bulk value. So first we have checked whether this interlayer expansion is beneficial for HER or not. Now you can see that here is the free energy diagram. You can see that this is for different interlayer spacing, this is the free energy required to have this hydrogen evolution reaction. And we have found that if it is a bulk MOSU2 with a 0.64 nanometer of the interlayer spacing, the free energy change is a large of free energy change is required. That means it requires a very high energy cost. Whereas for our case, which is a 0.78 nanometer, it requires only 0.46 electron volt. It is much closer to the optimized value. Optimized, we inspected the optimized separation. We have found that 0.73 nanometer, it's actually optimized separation. Our separation is very close to the 0.73, so that's why it is showing the much better catalysis activity. So, and this also you can see the origin of this by checking also the density of states. When we have checked the electronic density of states, this is the bulk MOSU2. Here around the Fermi level there is nearly no density of states. But whenever the interlayer coupling is less, the two seeds actually separated to each other. There are some of the states, electronic states appears at the Fermi level. Actually, this appearance of the states around the Fermi level gives rise to the more interaction with the reactants for the hydrogen evolution reactions. And not only just the interlayer spacing of the MOSU2, another important thing is the base, the nickel cobalt selenide. And what is the role of the base? We have checked that from here you see that nickel cobalt selenide actually in the Fermi level there are a lot of density of states, and actually it is a metallic like behavior. So whenever the base is metallic like, so it can actually gives the less resistive path, so electron can come from the current collector and go to the edges, because the edges are most active catalysis activity, so that these particular structures can give the high catalytic efficiency. And we have also checked the different, not only just this is the different heterostructures. This is lower one is nickel cobalt selenide, and the upper one is the molybdenum selenide with a different molybdenum site termination. This molybdenum selenide, the outermost molybdenum does not have any selenium, whereas in these two cases we can actually either can have one or two. It is a fully saturated molybdenum, and we have checked for all the possibilities that which one gives the best catalytic activity, and we have checked that you can see that from the free energy diagram that the bulk MOSU2 or the nickel cobalt selenide, they are not good for the HER activity, whereas this one, this 0.6 and 0.41, these two structures actually they give good hydrogen evolution behavior. And with this, I have already discussed the hydrogen evolution and the oxygen evolution catalyst. Now I would like to switch to another oxygen evolution catalyst, which is a very important one in current scientific development. This is the single atom based OER catalyst. Now why we are switching to the single atom based OER catalyst? Let me give you some basic idea what is the single atom based catalyst, because we are more familiar nowadays with the nanomaterials. Like nanomaterials is a small chunk of the materials which have lot of atoms, and of the order of even 5 nanometers you have lot of atoms. Now whenever you are downing the size and going to some few atoms, a cluster, this is a cluster of atoms. But so whenever you are going in a size from the nanomaterials to the cluster of atoms, you are actually exposing more and more the atomic sites to for making some catalytic reaction, because The inner atoms which are there inside, they cannot do the any catalytic reactivity. So in this case, they can, the single atoms, actually single atom is the only one atom, they can give you the highest exposure, I mean full exposure of its sites. So with a very little amount of the catalyst, you can get a very high activity. But the important thing is that single atom, they are very highly energetic. They try to make the go to the make some kind of agglomeration to go make some cluster. So the single atom has to be actually stabilized by interacting with some base substrates. So in this case, in here, I'm going to introduce some iridium single atom based catalyst, which is an excellent catalyst for the oxygen evolution reaction, because it is for long it is known that the iridium oxide as the state of art catalyst for oxygen evolution reaction, but the cost of the iridium oxide is much. So how to reduce the usage of the iridium? So that with a tiny amount of iridium we can get a high activity. So that this is a answer that we can go towards the single atom case. This is the STM image where you can the heart of STM image where you can see that these white dots, these tiny dots, these are the actually the single atoms of the iridiums, which is decorated over the surface of the molybdenum selenide nickel cobalt selenide heterostructures, which I have just introduced earlier. And in this case, the state of the iridium we have checked by XPS, and it is actually showing that it is in the 4+ oxidation state. And to confirm whether there is these are the nanoparticles or they are single atom, we need to check the X-ray absorption spectra, Fourier transform X-ray absorption spectra. From here, you see that whenever there is a metallic iridium, there is a iridium-iridium bond, and as a result, there is some peak is possible over here. Now, in the case of the iridium oxide, the bulk iridium oxide powder, there is also the iridium-iridium bond is available. But whenever these iridium atoms, they are a single atom, they are separated to each other. So you cannot find the peak of the iridium over here. It signifies that this particular iridium, they are a single atomic in nature. They are not a cluster, or they are not a metallic cluster or the nanoparticles. We have also fitted these particular structures to know its local environment, and it also it's a coordinated. There is a 4 coordination. So out of the 4 coordination, it is actually, I'm going to show you that it's the coordination behavior in the next slides. But before that, let me show you that what happens when we test the the oxygen evolution reaction with this particular catalyst. Interestingly, we have found that previously there are some sheet-like structures on the surface of it. There are a molybdenum selenide, and then we deposited the single atom iridium. Now, once we did this OER reaction, then we have found that there is no sheets on the surface within some only some 10 to 15 cycles. Once it is done, then the entire structure is stabilized for the hours. I mean, even if we did that 24 hours of cycling, 24 hours of electrolysis, it remains the stable structure. So there is it means that there is some surface reconstruction going on over here. So what is going on when we check that this nickel here, that there is no molybdenum selenide. Molybdenum selenide is completely etched out from the surface during this OER process in the highly oxidized atmosphere, and the selenide actually oxidized on the surface. There are some oxyhydroxide structures appears on the surface, and as I already mentioned, that oxyhydroxide structures, they are good for the catalytic application. Now, interestingly, although there is a lot of surface reconstruction is going on, but still the single atom of the iridium, they are not getting agglomerated, which we have checked from the STM image as well as from the EXAFS and X-ray absorption, Fourier transform X-ray absorption analysis. They remains the single atomic in a single atomic case. So we checked that how this the surface evolution happens, the surface reconstruction happens during the OER. Here there are, when the iridium is deposited, there is a certain the cobalt hydroxide phase appears with the selenide, but whenever this is the OER is done, then together with the cobalt hydroxide, there is the appearance of the cobalt oxyhydroxide, and similarly nickel oxyhydroxide can appear over here. So that means the selenide is actually changing towards the oxyhydroxide, which is a good catalyst itself is good catalyst, and whenever the iridium is placed on the top of it, actually there is some boosting behavior. It gives the very high catalytic activity. Now, to know how the iridium situated over the catalytic surface, we have actually deconvoluted or fitted this structure, the EXFA structure, X-ray absorption structures. And from this analysis, we have found that this iridium is actually coordinated with there are 3 oxygen atoms of the nickel cobalt oxyhydroxide, which is there in the base. And on the top of it, there is one OH actually on the top of this iridium atom is there. And these particular structures, when we check the oxygen evolution reaction, you can see that there is a large shift in the required overpotential to get the same current. Whenever we are going from, suppose the molybdenum selenide nickel cobalt selenide structure, this one is the structure. Whenever we have deposited the iridium, immediately there is a large shift in the position. That means to get the same current, you need a very less overpotential. That means it is actually 10 minutes towards a very excellent catalyst. We have given here a comparison chart that that overpotential required to 10 milliampere per centimeter square, 100 and 500 milliampere centimeter square, and you can check that actually for all the even very high current, it requires a very less overpotential to needed overpotential. And also the high its reaction ability is also evident from the very low Tafel slope of the 42 millivolt per decade. And the stability, good stability is evident from here. We also checked from density functional theory that what is the origin of this high catalytic activity of the single atom stabilized structures. And this is the single atom stabilized structures with the one OH. And then the first step is the adsorption of the OH. Then the OH turns into O, then it turns into the OOH. And you can see here, there is a comparison of the free energy chart. This is the iridium containing nickel cobalt oxyhydroxide, which is produced by this surface deconstruction. And here is the nickel cobalt oxyhydroxide without any iridium. You can see that the requirement of the free energy change is much less for the case of a iridium containing compound as compared to only the nickel cobalt oxyhydroxide. And this decoration is actually introduces some of the extra. If you compare, this is the nickel cobalt oxyhydroxide and this is nickel cobalt oxyhydroxide decorated with a single atom iridium. You can see that there are a lot of extra density of states very close to the Fermi level, which is not there in this case. So these extra states which are available near the Fermi level actually allows the reactants to interact with the surface of this catalyst. And here is another comparison chart. You can see that this one is actually this one of the lowest possible eta 10 value reported in the literature. Okay, with this, and this is we have also checked that for sustainable thing, as I mentioned, that this HER and the OER catalyst they can be coupled together to use for full electrocatalytic water splitting. We have done this with using the commercial solar cell as a supplier of the voltage, and here is the corresponding the performance here. So yeah, there is some voltage. Actually, it is not anyway. It is not something I cannot show it here. Maybe some issue is there. We have also done. I am not going to detail of this. We have also done some other heterostructures like metal oxide structures, and there is an amorphous surface over it. So this is crystalline amorphous heterostructures we have also designed because it is known that most of the cases there are some heterostructures of the crystalline heterostructures. But we have also done the heterostructures of the crystalline and amorphous heterostructures, check that what is going to happen if a amorphous material and a crystalline material comes together on the surface, and whether there is some synergisty or not. And we have found the excellent catalytic activity for this. I am not going into the detail of this, but just what I would like to emphasize over here, that this amorphous catalyst which we actually here presenting in terms of some cluster of the molybdenum selenide MoAc3, this is some amorphous structure, and for this structure there are several sulfur sites, and several sulfur sites we calculated their free energy, and we have found that there are certain sites like S2 and S7, these are more catalytic active. But whenever it is actually made some junction with the MoAc3 and the below one is the molybdenum tungsten oxide. Whenever the interface is formed, there is a actually charge transfer between the two layers. So the electrons actually transfer to the top molybdenum selenide layer, whereas there is a deficiency of electrons in the bottom molybdenum tungsten oxide layer. And this actually behavior gives rise to the beneficial hydrogen evolution activity. With this, I would like to conclude. The conclusion is that for water electrolysis is not just to get the hydrogen. It is not just the hydrogen evolution is important. The hydrogen evolution and the oxygen evolution both are important. You have to minimize the overpotential for both the reactions to have the overall catalysis activity. And the metal organic framework can act as a pre-catalyst in a sense that it is actually gives rise to the dynamic evolution during the catalysis process, and it can give rise to very high surface area of hydroxide, oxyhydroxide structures. And these MOF nanostructures can be generated by the molecular diffusion, and vertical MOS2 can preferentially expose the catalytic edges, and low interlayer coupling I have already discussed for the HR activity. And a single atom is actually can be generated and stabilized over selenide structures despite the extensive structural reconstruction. I would like to thank to all of you who have attended it, and I would like to also thank these are the some funding resources which I have obtained the funding for carried out all those research. Thank you very much.
Thank you, sir. Thank you so much for the enriching talk. Now we'll take question and answers from the chat box. So our first question is from Ramesh Babu. He wants to know, sir, for the catalysis study, how the band gap of the material plays a role.
That's a good question. Actually, the band gap seems like some optical behavior band gap is directly involved. Here, what is more important here is that the catalysis happens on the surface, so the higher surface area is more important. Now, also it is also related to its conductivity. Suppose a material is a more resistive, so whenever the electron will pass through this material, there will be large potential drop. So you need some additional energy to pass the electrons through the material. So you need a material with a less resistance, that is the good conductivity. Now, whenever if you compare different materials, if a material has a less band gap, you can expect the more conductivity because the carriers from valence band to conduction band can jump more. But if you have a larger band gap, those materials generally tend to have a less free carriers to take part in the catalysis process. So it has a role, but not a very direct role, but indirect role is there in terms of the energy consumption whenever the electron passage happens through the material itself.
Thank you, sir. We have another question from Shamin. He wants to know what is the role of interfacial resistance.
Yeah, the interfacial resistance, just a minute. Okay. The interfacial resistance, the important thing is that ultimately whenever a catalytic reaction happens, so what is going on over there? You have a catalyst surface, and then some reactive species comes and sit over it. Okay, and then there should have some kind of electron transfer between the catalysis surface and the species which are getting adsorbed over there. Now, if there is a lot of resistance for the charge transfer from the catalysis to this reactive species, actually it is not beneficial for the catalysis. You want that the electron can pass from the catalyst to the reactive molecules very efficiently. Here is the importance of the interfacial resistance.
Thank you, sir. So we have another question from Ramesh Babu. He wants to know why the porosity of the material is important in this study.
Yeah, porosity is mostly important. If you go to like here, maybe any of the discussions which I made, like suppose here, suppose if you go to this this is some nanomaterials, whatever is happening actually happens over the surface. So ultimately, the thing is that if you want to make the more sites available for this adsorption, you have to increase the total overall surface area. Now, how to increase the surface area? One way is definitely if you generate the nanomaterials the thinner and thinner, definitely with the same volume you can have a large surface area. Now, if you can again make some pores within the nanomaterial, yeah.
That's why I have to go anywhere.
Hello. Hello. Yeah.
Sorry, sir, there was some disturbance. You can continue.
Yeah. So if you make some porous structure, so within the same material, suppose you have some rod-like structures and it has some pores. So within the pores, you can also make some. We can also, create some additional surfaces within the pores. I mean, the pore walls are the additional surfaces. So you can expect some more catalytic activity.
Thank you, sir. So we have one last question from Professor Arun Tej. He wants to know what is the difference between DOS and PDOS and what are the methods to measure that?
Yeah, so the density of states and the partial density of states, this is the density of states means, there are some electronic level which is the possible, like a possible chairs to seat the electron. These are the density of states. Now, whenever we just call the simple density of states, it is the collective density of states. So you have the several atoms and they are giving some allowing or they are posing some states at some certain particular level. So whenever we call it as a collective one, the total density of states, we generally represent it, we do not call as a total density of states, that's the density of states. But when we consider that what is the contribution for the individual atoms or the individual electronic level, like now what is the some level, whether there is any level coming from the D level, whether any level coming from the S level. When you consider that, then we consider the partial density of states. Okay, so this density of states actually can be we have not measured over here all those things which I have shown. These are the theoretical calculation only, but those things actually can be extracted from the UPS pattern.
Thank you so much, sir. There are two more questions. If sir you have the time, so you can answer them in the chat box. So we have a few announcements now.
Before we break up for lunch, there's an announcement for participants. There will be 10 minutes mock quiz today at 4:30 p.m. This is furbished in order to check and rectify any issues that may arise tomorrow. All participants are requested to attend the quiz. Poster presentation will presentation will start at 4:45 p.m. today, and the schedule for which will be shared soon. Please note that attending the main quiz tomorrow is mandatory for all the participants. Thank you.
So
Thank you so much, sir, once again.
Okay, so if there is no other question, may I unshare my screen?
Yes, sir. Yes, sir. Thank you so much, sir, once again.
Thank you very much.
Yes.
Now we'll break for lunch. And we'll return back for the next session at 1:30 p.m. We request all the participants to keep tuning with us. Thank you.
in this tough time. It seems like, we have started the offline things, and it's a time to have, offline gatherings basically. But at least, this is online. I think I can see some people here in the offline mode as well. So maybe it's a beginning. So anyway, thank you so much. I will speak about the terahertz plasmonics and metamaterial devices. So anyway, my name you guys know, Gagan Kumar. We have a lab called Terahertz Photonics Lab in the physics department, where we do our all theory and simulation work, and also several facilities for the experiments in this lab, largely related to terahertz and plasmonics and metamaterial research we do. So terahertz is basically a broad, itself a broad area of research, and we try to combine it with plasmonics and metamaterials to come up sort of devices for future, that can be, could be useful in addressing the needs of increasing population in terms of, coming up with the high-speed devices, highly sensitive sensors. I'll just try to show you guys some of the, experimental work as well as some of the design work that we have done in the very end. But I will largely keep my talk explaining some of the basics about the terahertz and maybe plasmonics and metamaterials. I have very little part in the research, so but I'll try to show, but if there are more queries, I will be happy to address. So this is can I move it? Okay. So this is the outline. I will first introduce about terahertz, what are its applications. I will then discuss where terahertz today stands globally and how it's growing. I'll discuss briefly about terahertz radiation generation and detection. I will introduce you to the terahertz plasmonics and how terahertz plasmonics can be useful in making waveguides, guided wave devices, and they have potential in sensing also. I'll discuss that part. And then another area of research that we have is terahertz metamaterials. I'll just briefly introduce you to the metamaterials and whatever metamaterial research that we have been doing at Iitg Guwahati. I'll just briefly try to tell you, because this is largely, because this event is since related to the nano, probably or micro fabrication aspect as well. So I will just try to tell those designs and structures that we try to sort of fabricate maybe somewhere else, and we can use the facilities over here and in the collaboration with other institutions as well who are working this kind of, or who are having this kind of fabrication facilities. In that aspect I will speak. Anyway, conclusion then. So terahertz is basically a frequency. We all know this terahertz spectrum, this spectrum in fact, electromagnetic spectrum, and terahertz is a narrow gap between microwave and you can optical domain, you can say, your visible domain. Okay, infrared basically. We call it far infrared as well. So there are different ranges as people define as per their convenience. Largely, we do work in 1 to 5 terahertz, 0.1 to 5 terahertz, and this is said to be a terahertz gap because we are still lagging in terms of devices. In like we have in electronics or in the microwave region. So we don't have as such devices. So that's why this has been said to be a gap largely, but efforts have been made in recent times, in last 10 years or so, to fill this gap. And a lot of developments have been made, but I think there are certain areas where, especially like communication or maybe in terms of devices like free space communication, wireless communication, where I think we need to still work. And therefore, we have a lot of future prospects, research scope as well in this area. I'll try to tell those as well. But when I'm speaking of terahertz, means I'm speaking of 10 to the power 12 frequency. And on the time scale, I'm speaking of 1 picosecond. Similarly, you can convert it to wavelength energy as well. So you can see this 4.1 milli electron volt energy is 1 photon energy at 1 terahertz. This is very low as compared to the infrared or visible. So by itself, you can say that, it is very safe also. If it hits your body, it won't cause any harm. And like other sinusoidal waves or other waves, if I try to show you how does the time domain, it's a single time domain pulse basically, it's a single cycle pulse. So narrower the pulse, broader will be the spectrum obviously. So basically, this is a bipolar pulse, and people try to work largely with the broadband, this terahertz. But people do also work with the CW waves, depending upon the requirement. But I will largely discuss my research that we have been doing here in the lab in the broadband signal point of view. If I discuss few of the applications, let me start with the medical diagnostics. So in the medical diagnostics, basically terahertz imaging could be very safe. As I already said in the first slide, that the photon energy is quite low and therefore they do not cause any harm to the body. So efforts have been made to replace the X-ray with the terahertz imaging. Some research has been done on cancer detection, early cancer detection. So these are the few pictures that I have taken from TeraView. It shows that it is capable of detecting cancer at the skin level. Inside the body, it is difficult because it does not penetrate deeply inside the body because of the water contents. But at the skin level, it can easily distinguish between the cancerous tissues and the normal tissues. So that's why it has been quite powerful in that sense. And in fact, we do see nowadays these kind of imaging devices also at terahertz. They have been developed by the different companies and commercially available also. This is another picture in the dental science. It shows that it could be useful in dental science. The interior and outer region of this teeth or this tooth basically can be very clearly distinguished using this terahertz imaging, unlike the visible imaging. Okay, so in other area like virus detection, a lot of being talked about the virus detection in recent times, especially in the coronavirus point of view. So I would like to tell you that terahertz waves could be also significant in detecting or sensing the cancer, virus especially. So these are the metamaterials. I will introduce about the metamaterials. How do they work later on in a couple of slides. But what actually we have because of this metamaterial is one terahertz absorption peak. Okay, that depends upon the shape and size of the metamaterial. And once we have some kind of virus attached to this gap, there is a gap, split gap in this metamaterial, then this resonance peak will shift. Depending upon the shift, we are able to detect the virus. And in terms of coronavirus, also some research has been made. And in the Israel recently, it was found that terahertz radiations can detect the changes in the samples that are caused by the presence of coronavirus. And basically, it was claimed that it can provide early detection and accuracy of more than 90% compared to the RT-PCR reports. So I included this slide basically to emphasize the fact that it could be of potential use in the coronavirus detection also. However, it has not been pursued because there are other related issues. Obviously, how expensive is that, whether it's inexpensive or not when things come at the commercial level. Anyway, the another area is the security screening. The terahertz waves are transparent to plastic, cloth, wood, but not metal. So, for example, if a person is carrying some sort of weapon, like over here, a person is carrying a knife inside this newspaper or a gun, okay, that is hidden inside the clothes. So, without going and manually, checking this guy, we can scan the guy through terahertz, and we can find that whether he is carrying some kind of weapons. For example, here in this shoe as well, you can see that there is a knife. Normally it may be difficult, but unless you manually go and check the guy. But here, if the terahertz imaging is done, and it can be done because this is safe. Even if it hits the body, then it would be quite safe, and that's why without manually checking, you can do the imaging. That's why security screening point of view, this terahertz waves could be very significant. In fact, at some of the strategic airports, such kind of sub-millimeter or terahertz wave detectors are present, where they will make you stand inside a chamber and they will scan the body, and in fact they will try to see if a person is carrying any weapon. So yeah, this is another thing that imaging of the letters, envelopes or small packages, because millions or maybe billions, I don't know, number of packets are being carried from one place to another, and obviously we cannot open them. But if any kind of weapon is being transported or being sent from one place to another, then it can be, without opening the packet, one can do the terahertz imaging. Over here you can see this is a box. We are placing one packet on this box, and this can do the scanning, and right away it can tell us that whether the person, basically whether this parcel has some kind of any weapon hidden inside it. So there also the terahertz could be very significant. The another area I would like to just bring to you guys, that is the explosive and drug detection. So terahertz waves also, radiations also have potential in terms of the explosive and drug detection. So this picture basically tells that some of the materials like TNT, RDX, explosive materials have their spectral features in the terahertz. So imaging was one part that I tried to explain in the last slide, that it can do the imaging. But this tells you that apart from imaging, it has the potential that it can provide the elemental information, content information. So what a person is carrying. So for example, if a person is carrying some kind of, these explosive materials, and if that is, if that can be detected through terahertz, and it can be right away matched, the spectral features can be matched with the, whatever we have in our database, then that way we can identify, if he's carrying any explosive materials, where it can be useful. For example, if we have these kind of devices installed at subways, and without manually going and checking the person, if a person is passing through that subway, and if our device sees that, okay, he's carrying some kind of this narcotic or explosive material, it can sound an alarm, and a person sitting in the control room can easily, that time, follow those instructions, and they can trace that guy. So that way, if we are able to know the image as well as the content information, that could be very useful, unlike the X-rays. And this is one picture where I tried to show, I have taken it from Google, and where I tried to show that the crime prevention can another area where it can be helpful. So in this case, some security people are standing outside. A person has, captured, kidnapped another guy. So a person outside here is using this terahertz gun. Okay, it has strong power maybe, and as I said that, there are if we have soft walls like made of maybe soft partitions. Largely outside India we see those kind of things, and in India also nowadays we are having. So basically a person can use this gun and see that who is actually having this weapon, and they can easily target that guy. So, but only challenge here that we have, the biggest challenge is that we really do need very strong these terahertz gun with a strong power, so that because it may overcome the losses that it will have, either passing through air or maybe through this wall. But this is something where a lot of research, in fact, today is being done to develop really high power terahertz sources. If we can really develop that, some kind of this terahertz gun or this kind of camera, I would see it as one of the great technological advancement in the century. But yeah, it has one of the potential also. Yeah, another area where it is useful is the food inspection. Like you see, this is chocolate, and it has some kind of contamination. It has some glass particle or metallic particle. Although it looks very nice, without damaging, how can you find out that it has this kind of contamination? So metallic contamination it can easily identify because it strongly reflects back from the metal, as I showed in the last few slides. But even if it is non-metallic contamination, then people do process, with some kind of algorithms, and they are able to find, even if it is, some kind of glass or some kind of other plastic contamination. So therefore, in terms of quality control for the food products, terahertz radiations could be very useful, very significant. So one of the area where a lot of research is being done is about the communication, maybe in the terahertz domain. So we have seen 1G, 2G, 3G, maybe we are in the 4G, and in fact 5G has just probably started, and where we are trying to increase the speed of the devices and bandwidth as well in terms of transferring more and more data. And we are entering into a stage where artificial intelligence will play a bigger role, and also the population is increasing. So if you wanna address the needs of the increasing population, so definitely we do need to transfer more and more data, maybe in next 10 years, or maybe also we need big bandwidth also. So in that context, probably we are targeting toward the 6th generation devices. If 6th generation devices we are going to see in the future after 10 years, so definitely it has to work in the terahertz. Okay, so that's why only little work has been done in this area. I would say a lot of efforts are being made in order to get 6th generation devices operating at terahertz. A lot of work is required to be done, and on that aspect I would say we need to develop guided wave devices especially, or some sort of mechanism we have to come where signal can be transferred from one place to another over a chip, or maybe in the free space, or maybe from one place to another. So in that aspect we try to work with some corrugated structures, and we try to transfer data on a planar surface. And I will just try to show some of the work that we have been doing in this direction, basic research largely, and then from there some devices can be made. I will try to show that as well. So there also we have a lot of potential for this terahertz to come up with this high speed and broadband connectivity. So these are some of the areas where terahertz waves are useful or could have potential. Before I come to the plasmonics or the metamaterial part, I would like to just show you through this slide that how terahertz research has grown globally in last 2 decades. This data is only until 18, that's what I could collect only. But you can see from here that where we had only less than maybe 50 publications, okay, in 2000 in IEEE maybe, and today we have until 2018 we had more than 1500 publications being published. And in fact, I can see that being the part of certain committees that we are having nowadays special terahertz conferences, special sessions, and many parallel sessions in terahertz, like even Clio also. We have a lot of submissions we are getting in terahertz nowadays that, separately sessions are being organized in parallel. This is about the market. Obviously, wherever we have things to be developed, devices, commercially, we have to see things, and accordingly, this indicates that in 2012, where the market, terahertz market was of around 280 or 270 crore, in 2022, it is going to be around 2800 crore. So it is seeing an CAGR, compound annual growth rate, of like 26%. This slide basically shows you that terahertz technology is basically a tree, and it has variety of applications. Some of the applications I have discussed, like security I discussed maybe, and maybe imaging point of view we have a lot of applications. In space also it has applications. So it has variety of areas where the research is being done. Largely 4 areas that we work in, that with my students I work here in Iitg Guwahati. One is the terahertz pump probe spectroscopy, okay, where we try to study the ultra fast carrier dynamics. This research basically we could not really pursue much because of the femtosecond laser system, high power femtosecond laser system, but we have been doing it through collaborations. We have done some work here at Iitg Guwahati. Silicon based terahertz devices, we could do some work in recent times, and this plasmonic approach we have been using to make sensors, to demonstrate sensors basically, to make guided wave devices and address the need of high speed communication. That part I will discuss briefly here through a couple of slides. And the metamaterials, I won't be able to discuss in detail, but we have done some work in terahertz metamaterials to come up with the terahertz photonic devices such as filters, switches, modulators. So I will try to slow light devices. I will try to just give a brief flavor of that. So before before coming to the research part, I would like to just show you that how do we get terahertz, because this is very important aspect. Generation of terahertz and detection of terahertz is very important, and there are a number of techniques that we use. One of the widely used technique is photoconductive antenna. Okay, I'll show in next couple of slides what other techniques are. The photoconductive antennas, comparatively, they are inexpensive, and you do not require a really high power laser system. You do need femtosecond pulses, maybe 20-30 milliwatt average power is good enough, but like regenerative amplifier or amplified laser system, they are not required for this terahertz generation. And many labs, in fact, all around the world, whoever is doing terahertz research, they do have these kind of antennas, and they can be fabricated easily in the clean room facilities. In fact, what we have in Iitg Guwahati also. So let me tell you how does it work basically. Normally, a low temperature grown gallium arsenide is used as a substrate, and these kind of transmission lines are designed, can be fabricated. They are of gold material on a low temperature gallium arsenide substrate, and we have a small gap here of 5 micron typically. And whenever we hit here this gap, okay, we can focus our laser beam by seeing through a telescope, and then we can hit it really over here in this gap. So when we hit this gap, then it will lead to the generation of photocarriers here, because the photon energy is bigger than the band gap material here. And then once we have carriers here and we apply the voltage, transient current will be there. So how does it happen? So whenever we have a pulse coming, it is going up, 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 and so and so. So accordingly the current will increase. Okay, the current will increase. And whenever the pulse will go away, okay, the transient current will, this current that is with the time, that will decrease. Okay? The response is such that this everything, this process is happening on the picosecond time scale. So if you take the time derivative of this transient current, okay, then you would get a radiated pulse in the terahertz frequencies because of the picosecond. So that's why this material, low temperature gallium arsenide, is very important, because they have their carrier response in the picosecond time scale. So this is very simple, and you don't need much power, so people can easily fabricate and generate, and very efficient also. Other methods that are being used, not widely, I would say. Whoever has this very high power laser system, they are also very expensive, obviously in few crores. Then they can use this non-linear method. Nowadays we have commercially available these non-linear crystals. They are cut in a right orientation, and what we do, simply we just place our crystal in front of the laser light. You don't need any alignment. Like in the earlier case, you may have seen that we do need alignment. You have to really focus the beam into the gap, and that's a challenging task. But here you simply buy 1 centimeter by 1 centimeter crystal and simply place in front of the femtosecond laser pulse, and you will see that on other side you are getting terahertz. And similarly, there are other methods, like one of them is the semiconductor based indium arsenide. And here photodamper effect, basically the carriers are generated which have their generation and recombination response on the order of picosecond time scale. And they also can be used, and they have been frequently used, I would say. I will also use them many times. And they give quite broad terahertz, broad bandwidths. If you really want to get even broader, like on the order of maybe more than 50 terahertz, then people use this 2-color mixing, or it's sometimes called 4-wave mixing also. So they simply come with the amplified laser beam, and then they place one lens, and in front of that they place BBO crystal, that is a second harmonic generation crystal. And when we mix 800 and 400 in the air, or maybe by creating this plasma, we do get terahertz pulses through 4-wave mixing. There are detailed research articles you can follow from there if needed. But there are few more techniques also, but they're quite expensive, obviously. Now, detection part is also very important, because terahertz waves are far infrared and you guys cannot see it. With your eyes, they are not visible. So how do we know that basically they are there? So detection is very important in that aspect. And again, the detection in many labs is done through photoconductive antenna, because they are inexpensive comparatively as compared to the other approaches. So how does it work with the photoconductive antenna? So we have again these two transmission lines on low temperature gallium arsenide substrate. So what happens here in this case, now we come with the terahertz and femtosecond pulse simultaneously. They are hitting this gap. So if this time this femtosecond pulse, that is of very low power, maybe less than a milliwatt power, average power. So that it is just able to create some carriers over here. Okay. Now, since terahertz wave is also being hit simultaneously, so what happens that depending upon the electric field of this terahertz wave, a current emitter is connected to these two transmission lines, and a change in the current will be displayed here. So in order to see what was the electric field of this terahertz, accordingly the current signature will appear, and we can, by measuring the current, you can know that what sort of terahertz or terahertz profile actually has hit this antenna. So basically this is an indirect technique, but we do get we are able to nicely detect it. Other methods that are used for detection, they are electro-optic sampling. Largely zinc telluride crystal is used for this electro-optic sampling. And then air breakdown coherent detection, also said ABCD method. It is basically mixing of terahertz with the 800 to generate 400. This is very sensitive and very difficult to work, I can say. But this approach is very useful, especially when we try to get more than 50, or maybe people have even reported, I think, nearly 100 terahertz bandwidth. So from broadband point of view, that aspect, so this is useful. So there are incoherent detection methods where we can know the power directly, right? What is the terahertz power? Bolometer is quite sensitive. Gole cell, bolometer, they are quite good and comparatively more precise as compared to the pyroelectric detector. But if you want to just measure the power, and then these techniques are used. So this is about the generation and detection. Like other spectroscopy techniques, we do have a terahertz pump probe or time domain spectroscopy. It's a time resolved spectroscopy. How does it work? So normally we have a femtosecond laser. We get the femtosecond pulses, and then we place a beam splitter over here, and then one beam that is going toward this receiver is said to be a probe beam. Normally the power is split into 80-20 average power. So very low power is enough. In fact, I would say 10% power is enough if we are using and sometimes it is reduced further using some neutral density filters, because we do need only less than a milliwatt. And then another pulse is said to be the pump pulse or the pump beam here, and this is delayed through this mechanical delay. Why do we need mechanical delay? Because terahertz pulse is a picosecond pulse, you can say, and it's quite broad, and we are detecting it using a femtosecond pulse. So you can see that it's quite big, 1000 times larger. So if you want to detect it step by step, so we delay the pump pulse or the probe pulse. This can be on the other side as well, so that we can map out the entire terahertz pulse. So anyway, this delayed femtosecond pulse is made to hit this terahertz emitter. This could be any of the method that I discussed. Here it is just like a photoconductive antenna. So from photoconductive antenna, we get terahertz beam. Okay, it is quite broad. So this is then focused and collimated through this parabolic mirror. And if we are having over here sample, the sample is placed over here, and then again it is collected by the parabolic mirror, another parabolic mirror, and this is then collected by this terahertz receiver. So if we are having this transmission thing, we place the sample like that. But if we are having some waveguide approach, then normally we do use two more lenses, silicon lenses, basically confine it to this waveguide gap and detect it on the other side. So these two antennas I have tried to show here. Basically they are photoconductive antennas. I already explained how do they work. What is the advantage of this spectroscopy technique compared to maybe the FTIR, you can say, or other absorption or other techniques? The beauty about this terahertz spectrometer is that we are detecting over here electric field, unlike the intensity. So when we detect electric field, we detect its amplitude and phase, both. So amplitude can be helpful in calculating the absorption property, and phase can be useful in knowing the refractive index, maybe real and imaginary part, and content information, you can say. So that's why, and this is one of the setup that I had built, and this shows that, we are using 2 photoconductive antennas. I will just try to show this part here. How does it work? Normally, when we characterize the samples, we have, first we don't place the sample. So we try to measure the electric field, and then we place the sample, and then we measure the electric field. So what is the difference? The difference is over here. This N, refractive index, or maybe the complex refractive index. Okay. So this complex part has the real and imaginary part, and by comparing their phases, you can easily calculate refractive index. It's quite easy. You can easily do that. It's 2-line calculation. And by comparing the amplitude, okay, you can easily calculate the absorption coefficient, or entirely you can say the extinction coefficient. Okay. So this is a standard technique that any spectrometer, any terahertz spectrometer anyone is using, and we do these standard calculations to know about the refractive index as well as the absorption features, and accordingly the content information. Once we know the refractive index, you guys know that we can have a lot of information about its group velocity, phase velocity, and so on and so. Now, this is all about terahertz, what I have discussed so far. So now I would like to come to the terahertz plasmonics. So before I go to terahertz plasmonics, I would like to just briefly tell you what is plasmonics. In the plasmonics, we deals with the propagation of surface plasmons and its applications. And what are surface plasmons? They propagate. Okay, they are collective electronic oscillations, you can say, and they do propagate along the interface between a metal and a dielectric. It may be a vacuum also. Okay, this is maybe dielectric or vacuum, and here we have a metal surface. And they propagate, it's like, if it's surface plasmons or surface waves, obviously even if this is bending, so they should follow that path. It should not just leak out in the air. So they should remain confined to the surface. And the amplitude of surface plasma wave, sometimes we also call them surface plasma waves, they decay exponentially in both the regions, in the dielectric region as well in the metal region. The depth, penetration depth is little less in the metal. Okay, in air it is high, or vacuum it's high. So what is beauty? That we have this electric field here, the field is really high compared to if we had a wave that was directly hitting at the metal surface. So if we have maybe an order of high magnitude, then it can be useful for variety of applications, whether it could be, material ablation on some kind of non-linear applications, maybe in LEDs, they have been found to be useful. So if I discuss further, if one try to just calculate by solving the Maxwell's equation, applying boundary conditions, this is very straightforward analysis, and it is available on the YouTube also. Some lectures are there. If we try to work out the dispersion relation, okay, then you would see that it will have this kind of dispersion relation, K versus omega, and if you plot it, then this red one is the dispersion relation of this surface plasma wave, and this black line, this is for the simply light wave in the air. So what is difference? That if I compare at a certain frequency, for example at 3.5 frequency, normalized frequency, to see that the wave number is higher for surface plasma wave, and for light wave number is lower. So what does it tell? That if I am able to convert my laser light into surface plasma wave somehow, okay, there are different techniques in different wavelengths, but somehow if I am able to convert my light into surface plasma wave, I can get a same frequency light, but with the higher wave number. higher wave number means lower wavelength. If wavelength is lower, obviously it can help us to overcome the diffraction limit. Okay, it can basically beat the Moore's law, you can say. Or it can reduce the diffraction losses. Or you can say that it can further help us to miniaturize the devices. What we are making with whatever the light is available, if we first convert it to the surface plasma wave and use that surface plasma wave, then we can make even small feature sizes, and also we can reduce the diffraction losses when things are working through the surface plasmons. So this is something about the plasmons. But now, how do we get surface plasmons? In the different regimes, there are different techniques, like in optical or near infrared, people try to use Craftsman configuration, auto configuration. I'm not going to discuss that part because of time constraints. But in terahertz, one of the technique that is used for surface plasmon excitation is the periodic corrugations of the metal. So, otherwise, you see, I told in first few slides that metals do reflect, they strongly reflect terahertz. But if one can corrugate these metals in a periodic fashion, okay, they help us in providing the additional wave number that is required for surface plasmons. In fact, Sir Pendry had used, first time he had reported this idea, and he tried to calculate the dispersion relation. And this is the dispersion relation from him, and it mimics the surface plasmon's behavior. If you go back to last slide, you see this was on a planar surface. But here if you see, otherwise, it was reflecting back completely. But if you corrugate in a special way, then you can mimic the surface plasmon behavior. Basically, sometimes people call it spoof plasmon also. Basically, you can excite surface plasmons at terahertz frequencies by corrugating the metal. Okay? And the beauty is that if you change the shape, or maybe you can say, feature size, their dimensions, you can change the properties of these surface plasmons. If, for example, if I want to propagate or slow down a different frequency, then I can basically, accordingly, as per my requirement, I can go for different parameters. And in last couple of years, we have tried to fabricate different structures. In my postdoc and later on here also, we have tried to design and fabricate different variety of structures to study different aspects. Like, for example, this is one of the waveguide that I had designed and then characterized after fabrication. So this is basically stainless steel, 600 micron deep, 635 micron deep, basically thick. And here we have these small corrugations. As you can see here, this is actually the waveguide. And the dimensions of these corrugations are given here on the order of few hundred microns. So what is happening that if I somehow can couple my light, maybe I can bring my broadband terahertz. For example, over here, what we had done, that we made this semicircular groove. Why semicircular? Because, if we make this semicircular, we found that in this semicircular groove, if the focus is right over here, the center is right here, then, if we are bringing the light, hitting it from the top, then a lot of light basically was being concentrated over here. So what we did that we started making our waveguide from here itself. So right over here, so we started fabricating these corrugations. So we are coming with this broadband light, hitting this semicircular groove, and once it focus over here, there we have our corrugation starting, okay, in a one-dimensional single state line. Okay, then these corrugations, as I said, that if they are periodic and properly chosen with the dimensions and parameters, they can now lead to the surface plasmon excitation. Okay, so what will happen? They will start propagating along this pattern. So in a highly confined manner, they will propagate to the other side. On the other side, we detected it with some crystal technique. I already explained electro-optic sampling we used. So for this, some special arrangement was done. Basically, because you have to bring your terahertz from the top. You had a femtosecond laser, then we have amplifier, and then this was splitted. It is same technique, but the only thing is that there is a little change. This is a modified terahertz spectrometer, because here we are coming up with this terahertz from the top. And it is hitting over here, although it is hitting here, but now it will couple to this corrugation, and then it will propagate to the other side, and here we will use this electro-optic sampling method. So this is one of the setup that I had built. So what is happening now? If we are coming with this broadband signal, it is quite broad. So ultimately what we are getting on the other side, we were getting few wavelengths, few spikes, you can see here. Simulation experiment. So what does that mean? We are actually calling them modes. We are saying that, okay, we had a broadband line, but we have 3 frequencies only. Okay, they are quite broad, they are comparatively broad, but largely we are saying that there are 3 frequencies it is supporting. They are propagating to the other side. One is over here, another one here, another one here. Means 0.3 terahertz, 0.36 or 0.52 terahertz. If we are calling them modes, if they are really modes, so we went on seeing their mode profile in the simulation. Obviously they match with these or cavity modes also. So this is fundamental mode, we are calling it a plasmonic mode, and these are higher order modes. They are comparatively lossy also. So we were coming with this corrugation. So we are coming this broadband light, and through this corrugation we were able to transmit only selected frequencies. And if you change, if you do change the corrugation, probably you will transmit different frequencies. So this corrugated pattern basically behaved like a waveguide for us and helped us in transmitting information from one place to another on a planar surface. It can be useful in terms of making chips if we are working with the terahertz radiations or waves. So these are just properties, because we are saying it's a waveguide. So when I'm saying it's a waveguide, so a couple of properties that are very important to examine. One of them is that it should remain confined. So we, what we did that, we put here the detector at different places, we put the detector at different places along this path, and we see that we have highest field in the center. This is the one, if we place the detector in the transverse direction. And if we place the detector at different positions, starting from here, here, till the end, then we see that, the more this electric field was higher here, and it will reduce. But then we calculated, what is the 1 by Iitg length. We found that basic propagation length, it was nearly 14 centimeter. Basically, after going to 14 centimeter, still we had our 36% of the signal there. And now this is one that is showing that our field is confined to the surface. Like, we are moving our detector away from the surface. So field is highest near to the surface. As we are going away, we found that it was on the order of wavelength. That is quite good, because if we don't corrugate, and when we compared, it was nearly 5 times of the wavelength. So that way, it is said to be a quite good waveguide. So in that, this was one of the work that I did earlier, initial work. Then later on, we made some effort to replace metal with silicon, because silicon is present in abundant amount in the nature, and also we want to explore the possibility of tuning the properties by creating additional carriers, maybe, instead of going passively that you change the dimensions. So in that context, this is another work that we had done, and we basically made these pillars, okay, and we examined their dispersion properties through simulation. And then why I brought this slide, this is a bit old work, because we needed fabrication facilities for this purpose. So the way I did the fabrication, that I took a doped P-type silicon. P-type silicon I took because it was heavily doped. The idea was that basically it can behave like a metal. Otherwise, it may not behave like a waveguide. But at the same time, we have some flexibility here. Okay. So we had this silicon and we deposited silicon oxide by PECVD of like 1 micron, if I remember correctly, half of micron or 1 micron. And then on the top of it, we had this photoresist. And then we did the patterning, okay, in such a way that, it was, the photoresist was removed from the other sides, even silicon oxide was removed from the other sides. And then we went on to etching it through deep reactive ion etching we used, and to make these pillar structures. This is one of the micrograph that you can see here, and these pillars were made. I actually made them in my postdoc a few years back in Maryland, and then we examined these pillars and compared those results with the simulation also. I found that if the height of these pillars is different, we found that basically their resonance properties, the resonance that we were getting, that was also shifting. And they were found to be, and this was the input signal, and these are different modes we are seeing, and they were found to be in exact match to our simulation as well as theory. This is altogether theory, simulation, and experiment. So this is one such waveguide we were trying to demonstrate, and we could really prove that on silicon as well you can make these kind of structures and use the clean room facilities. And then we fabricated different structures with different periodicity and different width also. And with the theory also, these results were found to be matching, because there was already a theory in this regard. Theoretical paper was published by Serpentary group, and we were able to experimentally show these results that they do follow. And especially on silicon, we were able to fabricate and characterize. These were a few properties that we tried to show, that how does the 1/e confinement, 1/e length, basically that is on the order of wavelength. Because when we are going away from the surface, we were able to show that the field is much, much higher at that frequency, at the fundamental frequency. And as we are going away from the surface, it is exponentially decreasing. And this 1/e decay length was on the order of 1.1 millimeter. Similarly, this is the confinement in the lateral direction. We were able to detect this confinement by placing the detector at different places. And we were able to show that the full width at half maximum in this case came out to be nearly 450 micron. That is quite good, half of wavelength. And because always waveguides cannot be straight, so what we did that in one case, we tried to make a bend at 45 degree, and through simulation it is clearly being shown that we have these corrugations along this line, and when we are launching light over here and it is being coupled to these structures, then it is taking the path of these corrugations. So if we had made these corrugations in some other directions, then obviously it will take the path of that corrugation. And in that direction, we were able to demonstrate some of the 3 dB coupler, Y splitter, multiple Y splitter, and we were able to show that basically the wave can be made to propagate through this corrugation in a highly confined manner. And then we also calculated the losses also. The loss was obviously increasing because as you are going through a band, the loss also increases. But over the 14-15 centimeter, I think straight waveguide case, we were able to get nearly 36% of signal. So there are some trade-off, but you can use this technique very nicely to make the waveguides. And just I want to give you a flavor of the things that we fabricated, the structures basically we fabricated in the clean room. Like pillar structures we fabricated, this is micrograph here. These are inverted pyramids. This was a bit of challenging task, how to fabricate these inverted pyramids. Actually they were fabricated by making use of the crystalline properties of the silicon, crystalline silicon. Because one particular side can be etched faster if you properly design your structures on the silicon substrate. So that way we were able to make these inverted grooves, inverted pyramids, and these are long grooves. We also showed that, how do they behave in terms of the guided wave properties, and these details can be found in my publications that I did earlier in IEEE and Optics Express. And here recently, although we could not do the experiment, but this recently appeared in Journal of Light Wave Technology. So we showed here that if we have these grooves, and this is basically being used as a waveguide, and now if we fill these grooves with different refractive index analytes, and then we found that because the ambience refractive index is changing, properties are changing accordingly, so then it will show a shift in the resonance, and based upon that shift you can actually calculate the refractive index of that material. So basically we tried to show that terahertz plasmonic waveguides can be used as a thin film sensor. So this is in one slide I just trying to show here. This is the dispersion properties, but we did some of the measurements. I'm not showing that here, but this is already there in the New Journal of Physics. If someone wish to see the details, please can go through it. And these are few more waveguides that we recently demonstrated, and we tried to discuss different aspects. Like for example, this is inverted pyramids, trapezoidal shape, and we also tried to study higher modes, more confinement. This is near field coupled plasmonic structures, because near field coupling gives us extra degree of freedom to modulate the waveguide response. And these structures we recently used to show the electromagnetic induced transparency. But we could not fabricate those structures because we don't have, here we were struggling, we don't had much of this flexibility, but hopefully we can do this, these things here, maybe now onward in the future, near future, in the NanoFab lab. In next couple of slides, I will just, time is also running out, I will take further 5 minutes. So another research that we are doing is on the terahertz metamaterials. Just to tell you that what are metamaterials? Metamaterials are artificially engineered materials similar to the plasmonic structures that I have shown, and they have unusual optical properties, and they are usually made up of these split ring resonators, from where they started basically. The research started, but now people use different variety of kind of structures, artificially designed structures, to get the manipulation of the light they are hitting to these structures. But they are quite good in terms of controlling the optical response, by careful designing of the structures, or maybe changing the dimensions of the structure. And this was also came through Serpentry's group in 2000. And these are few pictures of 3D metamaterial structures. They have been used in variety of applications like modulators, absorbers, filters, low light devices, in sensors, negative index materials, optical cloaking. And in terahertz, we try to make them. We could do some of the experimental research here, as well as some theoretical or design work in our lab. I'll show in next couple of slides. And in terahertz, we have to be careful with their design parameters. Normally, they are of the sub-millimeter dimensions. And they can be fabricated easily through photolithography. We don't even need to go to the E-beam lithography. And we are designing them or fabricating them here in the lab. But before I go to that part, I would like to show that how does it work. The single split ring resonator, basically you can think of like an atom. Okay, it has some natural frequency of oscillations. Okay, and its frequency is given by this formula. Okay, this is this behaves like a LC resonator, like this simple harmonic oscillations. If we have an atom that it is oscillating, similarly you can have this atom, and then we make an array, and then entirely it will make like a lattice. Okay, so the only difference between natural materials and this artificially designed material is that here you are forcing them to respond at a particular frequency. Okay, so accordingly we can make the resonators and make them to behave or at a particular frequency. So just to highlight here, we are working with the metamaterials. We are trying to make broadband modulation device for mighty polarization devices. We are working modulators. We are working with 2D materials in SCRB project. Toroidal metamaterials, electromagnetic induced transparency, another SCRB project. Sensing devices, optical devices in C-band in ISRO project. And this is one of the, I'm not going to discuss the work here, but this is one of the design. Recently we were trying to make broadband devices for terahertz. And these are few different aspects, like here polarization conversion we tried to demonstrate recently. And electromagnetically induced transparency, modulation, as well as then we independent control. We try to demonstrate in our recent articles. Again, some of them are experiment, but some of are only design. We look forward to fabricating them here in future. These are toroidal metamaterial structures, different toroidal response that we were able to show through these designs. I'm just giving a flavor so that we can later on. These are all structures that can be easily fabricated using the clean room fabrication that is available here. And hopefully some of them we have to publish only through theory and simulation. These are again few structures that I'm trying to show here. And they can be fabricated. We could not do the experiment of these, but hopefully we will fabricate them here. In summary, basically I would say that terahertz plasmonics and metamaterials do have a lot of potential in building modulators, filters, or devices for next generation at terahertz frequencies. We need to develop terahertz technology, and obviously in that direction we have been working, and we do need support obviously of fabrication. Especially here, we do have characterization facilities, but if we can use also, and we are anyway using also, I really appreciate that part, and hopefully we can now onward producing experiment from here, our institute itself. And this is my group. In fact, the strength has increased. I would not get more photos. This is, and these are acknowledgements. I would like to just acknowledge our funding agencies, the projects that we are handling. And my colleague has, I think, next talk, and my collaborator, Sikdar, Professor Sikdar. But thank you very much. I took a little longer, so sorry for that.
I hope Sikdar won't mind.
Yes, if Sikdar is there, then it's fine. Okay, Sikdar?
Hey, no problem. You have actually given a good introduction to my lecture as well. So, thanks.
Okay, so I also got the permission. Thank you.
Thank you, sir, for your valuable insight on this topic. So with that, we will go ahead and take some questions. So our first question is from Jay Sinha. What is BBO and what are the simulation techniques we can use to simulate this terahertz?
BBO is basically a beta barium borate. It's a second harmonic generation crystal, and a lot of information may be available. They are commercially available also. We used to use it for second harmonic generation at 800. Other lithium niobate kind of crystal can also be used depending upon their availability and the market value, like cost. And for simulation, we are largely using CST Microwave Studio, and with the help of Professor Sikdar, maybe Comsol also. And yeah, I mean largely CST Microwave Studio.
Thank you, sir. Our second question is from Rajan. He would like to know the dimensions of photoconductive antennas, the separation gap, and material of use for the context.
Yeah, I mean they were gold strip lines you may have seen, and the gap is typically 5 micron, 4 to 5 micron. That in fact I fabricated with 5 micron. They work nicely, and the gap between these two transmission lines could be, it may change. Then your center wavelength will change, because then the resonance will change. So that is typically on the order of, if you remember correctly, 20 to 50 micron. I fabricated with 20 micron with a gap between two transmission lines.
Thank you, sir. Our third question is, what are the materials, for example, metals or semiconductors used for terahertz pulse generation?
For terahertz pulse generation, I told, like, we use low temperature gallium arsenide. I have seen several people using silicon on sapphire, something like that. and only gallium arsenide also. The only important thing here is that you should have the response, the carrier response and picosecond time scale, because your carrier should generate accordingly in the picosecond time scale and they should recombine. If you can get this transient response in picosecond time scale, then you can have this oscillations at a conic radiation being coming out at terahertz. That is the requirement. Low temperature gallium arsenide is widely used, and in fact but I think some companies and some people use different materials also.
Thank you, sir. Thank you so much, sir, for answering all the questions.
There are a lot of questions, but running out of time. So
please email, and thank you for giving me the opportunity. Thank you so much.
Thank you so much, sir, again.
now we will proceed to our next technical talk on plasmonics and nanophotonics technology for next generation devices by Professor Debabrata Sikdar from Indian Institute of Technology, Guwahati. He is an assistant professor in the Department of Electronics and Electrical Engineering, Iitg Guwahati. He has completed ME in Communication Engineering, BE in Electronics and Instrumentation, and MSc in Physics from Birla Institute of Technology and Science, Pilani. He has received his PhD from Monash University, Australia. Professor Sikdar was a Marie Curie postdoctoral fellow and postdoctoral research associate in the Imperial College London, United Kingdom. He has an international patent with more than 60 journal publications and more than 20 conference articles. He is currently working on emerging areas of photonics, plasmonics, and metamaterials, with the primary focuses on smart tunable optical devices of plasmonic metals and semiconductors, RF metamaterials for MRI applications, graphene assisted tunable broadband metamaterial devices, and so on and so forth. Now I would like to request Professor Sikdar to take over the session. Over to you, sir.
He is taking care of this. Yeah, thank you so much for this generous interaction. So I'll share my screen, and from there we can get started. So I'm sharing my screen. Kindly let me know if it is visible to all. Just a second. Yeah. Yeah, you can see my screen?
Yes, sir. Yes, sir.
Okay. So I welcome all of you to my lecture on plasmonics in nanophotonics technology for the next generation devices. So what is nanophotonics? So when we talk about nanophotonics or nano-optics, it is basically the study of the behavior of light on the nanometer scale and also of the interaction of light with nanometer scale objects. Now, this is a branch of photonics, electrical engineering, optical engineering, and nanotechnology. So it is truly a multidisciplinary area where a lot of things are happening right now. So it often, but not exclusively, involves metallic components that can be used to transport and focus light via surface plasmon polaritons. We'll come across this new term very soon. Now, when we talk about some technology, we must have this clear idea in our mind what frequency range we are talking about. So this term nanophotonics, just like photonics or optics, we are dealing about the ultraviolet, visible, and the near infrared range. That is, we are talking about the free space wavelength range of 300 to 1600 nanometers roughly. Now, what is the motivation behind going into this technology? So if you have a look at the global internet growth and the trend, that you can see that by 2022, there will be a huge jump in the number of internet users. There will be more number of devices which are also connected to internet. The IoT applications are taking up. We require more broadband speed, and also the data traffic requirement has increased because there is much more video viewing So if you compare like in 5-year scale from 2017 to 2022, how things have changed, you can clearly see the trend or the pace at which the demand is growing. So we really require fast data processing as well as compact and light devices. So what are the challenges that current technology is facing? So if we think of current communication systems, they're either based on electronics or photonics. So if we look into this particular diagram, so here we have critical device dimension on the x-axis. On the y-axis, we have operating speed. So semiconductor electronics, as you all know, because of the VLSI technology, we can actually pack in billions of transistors in a very small chip. And that is all possible because the active device dimension has been in the order of sub 10 nanometers. So it is really good towards packing a lot of transistors into one, so you can have a very compact device. But then semiconductor electronics face a problem of the RC delay, the resistance capacitance delay that is at every node for charging or discharging of the particular node. And that actually restricts the speed at which semiconductor electronics can work. So you cannot reach typically the gigahertz speed using semiconductor electronics unless you use some kind of multiplexing technique around. But there is an inherent speed limitation by the RC delays in your semiconductor electronics. Now if you look into the alternative, if you go into photonics, there you can actually go at much higher speed. That is where you can take advantage of dealing with photons instead of electrons, right? You can work almost at the speed of light, and you can transport much more data, or you can actually have much more speed or bandwidth that you can achieve. But what is the problem with dielectric photonics? Typically the diffraction limit of light, which tells you that you cannot focus light at a spot below lambda by 2. So that is where the critical device dimension comes out to be of the order of 1 micron when we are talking in the visual and infrared range. Okay, so that is the problem coming from the dielectric photonics. So what we need the best of both the worlds. We actually need high speed, we also need compact devices. So this is where we want to be. And who is going to help us in achieving that? And that is where, you need to have a mechanism that allows you to transport huge amount of data at high speed along with miniaturization. So you want the best of both technologies, but currently both these technologies individually, they are facing limitations. And that is where plasmonics come into picture. And this is the way ahead. Okay. So if you think of extending, light, or if you think of extending optoelectronics into nanometer regime, as in the form of light, you cannot do it. So you have to convert light into plasmons. Plasmons are again what? These are surface electron waves. So you're coming back to the electronic domain in a sense, where you are converting from light to plasmons. And this particular technology, we'll talk about it in more details. And this technology we are calling as plasmonics. To be more specific, we can call it as metallic nanoplasmonics or metallic nanophotonics. So what are these plasmons? These plasmons have much shorter wavelength than light, and they are able to propagate electronic signal. And that is where they are very nicely positioned in the domain where we want them to, because this metallic nanoplasmonics, they naturally interfaces with the similar size electronics. So it is easy to couple these two technologies together. Similarly, plasmonics also naturally interfaces with the similar operating speed photonic networks. So plasmonics actually shows and very improved his synergy between electronic and photonic devices. And this is the major attraction of the research domain right now. So if you look into plasmonics, this basically merges photonics and electronics at the nanoscale. So obviously it has to be one of the most important growth areas of the century. And typically what it does, it investigates electron oscillations in metallic nanostructures and nanoparticles. So these nanoparticles can also work as nanoantennas. You can actually make nanoscale devices using these metallic nanostructures or nanoantennas. Now, plasmonics deals in generation, manipulation, and detection of surface plasmon polaritons. So what is surface plasmon polaritons or SPP? These are basically quasi-particles which are formed due to the coupling of light and surface plasmon. And surface plasmon is nothing but the electron oscillation at a metal surface, or you can say at metal dielectric interface to be very specific. Fine. So this plasmonics, as you understood, is a very young promising topic of research, and it is basically a branch of nanophotonics. So if you want to visualize plasmon is basically like a density wave in an electron gas. So this is very much analogous to a sound wave, which is basically a density wave in a gas consisting of molecules. So the way the sound wave propagates, you can think of plasmon propagation also in the same way. It is basically a density wave. And where do they exist? They exist mainly in metals where electrons are weakly bound, to the atoms, and they are free to roam about. So the electrons in a metal can be imagined or visualized as if they can wobble like a piece of jelly. So if you take a piece of jelly and try to poke it with your finger, you will see that the piece of jelly is wobbling, it is going back and forth. And that kind of,
You are not audible, sir.
now,
Yeah, now you are audible.
I did nothing basically, just pressed an escape button. How about now? You can hear me?
Yes, sir. Yes, sir.
Okay, amazing. So, okay, so coming back to where I stopped. So plasmon is basically a collective wave where billions of electrons basically oscillate in sync. So where are plasmons found? As I mentioned, they can be found in metal. Now, when we think of metal, first thing we can think of a bulk metal, right? So bulk plasmon is basically a longitudinal wave, right? So it is an oscillation along the length of the metal in the same direction of the excitation, right? So this is basically an oscillation of free electrons along the bulk of a metal. Now, light being a transverse wave, it cannot excite bulk plasmon. So bulk plasmon is a natural thing that happens in every plasmonic material, and this is the resonance condition. So at which frequency the permittivity of the metal approaches zero, you get a resonance, and that frequency is also known as bulk plasma frequency. You can write it as omega p, which is square root of n e square over m epsilon naught. What is n? Electron density is the electron charge, m is the mass, and epsilon naught is the vacuum permittivity. Now there is something amazing that happens before or after the plasma frequency. So if you shine a light with a frequency larger than the plasma frequency, you will see that metals are actually becoming transparent. So that is where if you take a bulk metal and shine some electromagnetic wave lesser, having a frequency lower than the plasma frequency, that bulk metal is going to reflect all of that radiation back. But when you actually increase the frequency, beyond beyond the plasma frequency, you will see that the metal actually gives up. It will allow all the radiation to pass through. So metals actually become transparent at or above plasma frequency. Now there is another type of plasmon that can be excited using light. So that is surface plasmon. As you can see, this is basically a surface wave that is propagating along the metal dielectric interface. And when you do the maths of the conditions at which this wave can sustain, it is found out that now it has to be a transverse magnetic wave. And importantly, this is how the field profile will be. So the field will be more extended towards the dielectric and less into the metal, but the wave can propagate along the interface. Okay, so another important thing to remember here is that this surface plasmon is a surface wave that can propagate along this metal dielectric interface under certain conditions. So what are the conditions for this to happen? So the condition for plasmon resonance to happen is that permittivity of the metal at a particular frequency plus epsilon d, that is the permittivity of the dielectric, should be 0. Okay, so once you find out what is the surface plasma frequency for this, that is omega sp, you can find out to be following this particular formula, which is omega p over square root of 1 plus epsilon d. So as you can see, omega p is the property of the metal and epsilon d is the property of the dielectric. So you can choose a different dielectric to tune this plasma frequency, and you can actually have surface plasmon propagation at a different frequency of your interest. Now there is a problem, because I have mentioned here that this surface plasmon propagation happens under certain conditions. Now what are those conditions? First condition is that there is a problem of phase mismatch. Phase mismatch because you have free space light that is falling onto your metal dielectric interface. So what is the dispersion relation? So the dispersion relation for light in air will be omega equals ck. So this particular black line that you can see, straight line. However, if you look into the SPP propagation constant beta, okay, that particularly follows this equation. I'm not going into the derivation of all this. I'm just telling you the basic concept and the trend. So you see the beta is basically following this particular dispersion relation. So you can say this is the dispersion relationship of the surface plasmon polaritons. Now at a particular wavelength, you can see that the momentum of the plasmon, surface plasmon polaritons or SPPs are larger than that of the photon that is incidenting. So how can a photon with a lesser momentum can excite a plasmon, surface plasmon with a larger momentum? That is not possible. So this kind of problem needs to be solved. So there has to be some kind of phase matching done, and one very popular scheme for this purpose is called using of prism. So you put a prism, and on top of that you have a metallic film. So basically you here get two particular metal dielectric interface. So one is this metal and dielectric, which is the the material of the prism, which is the glass prism typically, and the other one will be a metal air interface. Now here what you actually have the control on the incident angle of the light. Now whatever is the k naught is the wave number. So n k naught will be the wave number, n is the refractive index of this glass medium, and if this angle is theta, so the component along this will be n k naught sine theta, right? So the component of that wave number, okay, should match the beta. That is the whole idea. So how do you do it? So as we have seen here, that the same diagram you can put it here, and now we will see that this particular slope is actually too steep, so you cannot tune it. So when we put it, when you allow light to go through this particular glass medium, there the dispersion relationship changes to omega equals c by n k. So n is the refractive index of glass. And that is how the slope of this particular line is reduced. And now you can have this blue line. Now, this blue line, at certain frequency, it is actually directly meeting the propagation constant or the beta of the surface plasmon polar atom. So that is one point where you can directly excite surface plasmon polar atoms. The other thing is that if you want to match at any other frequency, say you want to match at this frequency, what you have to do, you have to reduce this value of the momentum of the photon. And how you can do it? How you can do it? You can change this angle so that n k naught sine theta, this component will be same as the value that is given here. Okay. So this particular line here is showing you the dispersion relationship of metal air SPP. What about the other one? The SPP at this particular interface of metal and dielectric, this is metal dielectric SPP. But as you can see, this metal dielectric SPP has got a much larger momentum at a given frequency than the photons. So at any condition, you will not be able to excite SPP at the metal dielectric interface. But you will be able to excite SPP at the metal air interface. Okay. So this is something very important to remember, that SPPs can be excited and you will be able to convert light into surface plasmons under certain conditions, and these are the conditions where you can have a phase matching done and you can allow this kind of excitement to happen. Now these things look bit messy. There are these bulky glass prism need to be put into place to do the phase matching. So is there any way around it? The answer is yes, and that is where the localized surface plasmons come into the picture. So localized surface plasmons are basically nanoparticles. So they have this curved geometry. So when light is falling on them, depending on the electric field of light, okay, at a particular time instant. So if the electric field is in this direction, the electron cloud of that metallic nanoparticle is pushed down. Then what happens? You have some negative charges. You can think that there are more negative charges here and there will be some positive charges here. So these basically behave like a dipole. Again, with time, when the electric field reverses, this dipole also gets, upside down. So this particular nanoparticle basically work or behave like a dipole antenna, which is also oscillating with electric field. So here, the curved surface of the nanoparticle is basically providing that restoring force, okay, and the electrons are kind of oscillating with the electric field. Now the resonance will take place when this frequency, so as you keep on increasing the frequency of the electric field, this wobbling of the electron cloud also increases, and when this matches the natural frequency of oscillation, you get a resonance, and that resonance allows you, and that resonance is called localized surface plasmon resonance. And what is the benefit of this localized surface plasmon resonance? First thing is that you do not need any extra geometry to excite it. You do not need to worry about any phase matching condition. You can directly excite it. Second thing, you can get a resonance, enhanced absorption and scattering of the incident light. So whatever is the geometrical cross section of this particular nano antenna, you will basically get many times larger radiation cross section or absorption cross section for the same particle. And all this are happening because of a high Q resonance. Moreover, there is a very strong electric field confinement in and around the nanoparticle, and this resonance is also very sensitive to the size, shape and composition of the particle as well as the permittivity of the surrounding. That makes this particular nanoparticles very good candidates for behaving as a sensor which can quickly sense the change in the refractive index of the surrounding media, and it can change its high Q resonance to a different wavelength, so you can detect it very quickly. Okay. Now, important thing is that this real plasmon, these particle plasmons are not new. They were there with us from the 4th century AD. Okay, so if you look into this Lycurgus cup, which is basically kept in the British Museum, for its unique feature. Why it is a unique feature? Because when you shine light on this cup from outside, you actually see the reflection profile and the cup looks green. And when you put light source at the back, you will see the cup appears red. And all this happened because of nanoparticles, plasmonic nanoparticles. Basically, they were like gold and silver mixed nanoparticles in this glass when it was made. And these nanoparticles typically have their scattering and absorption peak around blue and green. So what happens when you illuminate from outside, you actually see the scattering resonance of the scattered light, and that comes out to be bluish or green bluish color. And when you have light source inside, you are actually seeing the transmitted light, which is white light minus whatever light is getting absorbed, and the absorption peak is again in blue-green. So white light minus blue-green, you are getting red. And that is how the same cup appears red. And these are basically the practical demonstration of this amazing feature of nanoparticle plasmons. Now, why I'm going into all these details? Because we can apply very simple theory to understand how these plasmonic nanoparticles can be modeled, and then we can show how they can be implemented into different devices. So first important and easy theory that can be used for understanding the responses, optical responses of this nanoparticle is to use quasi-static theory or quasi-static approximation. And this is valid for nanoparticles which are very sub-wavelength. So the particle size should be much smaller than the wavelength of the incident light. And there we can assume that the phase of the harmonically oscillating electromagnetic field is basically constant over the particle volume because the particle is very small in size. In that case, we can assume that the interaction is happening under electrostatic approximation. So this is the nanoparticle with a permittivity of epsilon m, surrounding medium is epsilon d, a is the radius of the particle, E0 is the incident electric field. And in that case, instead of solving Helmholtz equation, you can simply solve Laplace equation for the potential. You can apply the azimuthal symmetry and solve for it, and you can find out the electric potential which is inside and outside the nanoparticle. And the potential outside is basically the potential from the incident electric field, plus there is a contribution from this nanoparticle. And this polarization P can be also defined as, epsilon D. Epsilon is the material permittivity, epsilon D is the dielectric one. Alpha times E naught. Alpha is the polarizability of this nanoparticle, or you can say polarizability of this dipole, induced dipole into the matter. So how do you estimate polarizability? So from this expression, you can see that this particular term we are defining as polarizability alpha. Now, what is the good thing about this? That if you look into the polarizability and you look into the expression, you can find out where resonance will take place. So the condition for resonance will be epsilon m plus 2 epsilon d equals 0. So when this condition satisfies, you get a resonance. And in this particular graph, it is shown that when you take metal permittivity using a simple Drude formula, 1 minus omega p square over omega square plus I gamma omega, where gamma is the damping constant, and epsilon d is taken to be 1, that means the nanoparticle is in air. And what are the different plots here? Which is gamma over gamma p. It shows that when the gamma or the loss is increasing, the resonance is getting lower and lower, and the Q factor is also coming down. So once you consider metal with less losses, you get a better resonator, and that is true because if you make nanoparticles made of silver, you get a much stronger resonator than that of a gold. Okay, and good thing about this theory is that once you know alpha, you can quickly calculate the scattering cross section using this very simple formula, and also you can calculate the absorption cross section. From that you can find out what is the extinction cross section. This also tells you that scattering cross section is proportional to the radius to the power 6, whereas absorption cross section is proportional to radius cube. So smaller particles will absorb more, and when the particle size grows, scattering will start dominating. Okay, and this is what is an example how the nanoparticle, this is a 50 nanometer gold sphere, extinction cross section has been plotted when the surrounding media is air, water and silica. So as you keep on changing, the resonance wavelength keep on getting redshifted, and all this basically follow this particular resonance condition that we discussed before. Now if you compare the three things together, the bulk plasmon, surface plasmon and particle plasmon, these are the conditions we have highlighted. Now what is important here to note that bulk plasma frequency is not in our hand. For these materials like silver, gold and copper, these are naturally occurring and the plasma frequency is also fixed. The surface plasmon, depending on the choice of epsilon D, okay, we can actually bring down. So if you take epsilon D, omega sp is actually omega p over square root 2. So you see you can reduce the frequency, so you can actually bring the wavelength more towards the visible range, so which is say 400 to 800 or 780 nanometer. And in this case you can even further reduce the frequency of resonance, and in that case you can actually have particle plasmon frequency working at that visible and infrared range. So you get much more flexibility to tune particle plasmon resonance. Okay. So another aspect of tunability, as I mentioned, is the size. So if you take gold nanoparticles and you change the size from 20 to 150 nanometer, the resonance wavelength will change from 520 to 660 nanometer. Whereas if you take silver nanoparticles, it will change from 380 to 600 nanometer. Fine. So this is another diagram that tells you the different shapes. Like you can consider silver nanosphere, gold nanoshell, nanoeggs, okay, then nanorod, triangles, cube, rise, and these are the different wavelength range they are covering. So you can take one particular geometry and try to tune the resonance. One simple example is that if you take a silica core, gold shell, and if you take the shell thickness to be 20 nanometer, you get a resonance something close to 740. And if you reduce the shell thickness to simply 5 nanometer, you can move that resonance to around 1050 or somewhere. So it's a huge tuning range that you can get. So you can tune the resonance of these particles by changing their size, shape and other things. So what are the different methods for calculating these optical responses? One thing, very simple theory, that is May theory. It's a popular one proposed by Professor Gustav May in 1908. And that theory is applicable for spherically symmetric particles. So you can use that theory. That gives you exact calculation of absorption and cross-section, scattering cross-section. For multi-layer particles, you can use T matrix, transfer matrix. Okay, you can use discrete dipole approximation for different shape nanoparticles, but there is a convergence criteria that mod n kd should be less than 1. There are other simulation softwares based on FEM, finite element method, and FDTD. They can also be used for calculating the scattering and absorption response any particular shape nanoparticles. Okay, so these are the different methods that can be used for calculating the plasmonic properties of these nanoparticles. Now, what are the applications? As you can think of, you can use them for nanoscale devices and circuits. You can use them for plasmonic solar cells, where nanoparticles can be used as much efficient absorber. Okay, you can use them for biomedical applications like cancer therapy, where you have absorbing nanoparticles delivered to your bloodstream that can reach any cancer cell in your body, and then you can shine near infrared light so that these nanoparticles can absorb those light, get heat up, and then that can locally destroy the tumor. You can use them for biological and chemical sensing because they have very strong electric field near them, so they will be very good substrate for surface enhanced Raman sensing kind of Raman scattering kind of sensors. You can also use them for optical data storage because you now have control over very sub wavelength areas, so you can have much more dense packed optical storage. You can use them for optical nano antenna, so you can make them scatter in one particular direction. And you can also use them for maskless fabrication technique, where you do not need to you can make wires or wires by simply lining up the nanoparticles together and then shining light on them so that they can heat up, absorb light, heat up and melt and form that connectors. So you do not need to use masks for your fabrication technique. Fine. So with all this, let us look into some of the applications, how you can design optical nanoswitch using plasmonic nanoparticles. So one example of that would be to take a gold dielectric gold nanosphere. So this is basically 3-layer nanosphere. And as you can see, the radius R1 material is epsilon 1. Next material radius is R2, epsilon 2, R3 and epsilon 3, and the surrounding media is epsilon 4. So this is a very generic description of this structure. So you can again use quasi-static approximation provided this entire structure is much sub-wavelength. And then you can solve for the Laplace equation by using the continuity of the electric field. So the tangential component of the electric field and the normal component of the displacement field will be continuous. So you can apply that at each boundary, and then what you obtain here would be the final expression for the potential which is outside this nanoparticle, and from that you can find out what is the polarizability of this particle, which is basically behaving like a dipole antenna because there will be oscillating modes. So this is a expression of the polarizability. Don't get scared looking into the terms, but this is pretty simple. And what it helps you, this alpha will allow you to calculate the scattering and the absorption cross-section. Here we are more interested in the scattering cross-section part, and that can be obtained using this simple formula. And in the scattering part, we are also interested, because this will be acting as a switch, so we are interested in the conditions where the switch will act as a high scatterer, so you will have a scattering resonance, and also where the switch will act as a low scatterer or a cloaking condition. So these are the conditions. Okay, as you can see here, so when the numerator of this alpha will go to 0, so or very low, then this switch will act in off mode. When this denominator goes to 0, you'll get a resonance, scattering resonance, and this entire device will act as a high mode or on mode. So when you plot this, you can see the red one shows the scattering resonance, the blue one shows the cloaking conditions, and you see there are wavelengths where these two regimes are getting very close to each other. Okay. Now, one important thing here to note that here we assume that the dielectric, the metallic layers, the gold layers are lossless. But then when you incorporate losses, you will see that these sharp features are not that sharp. It means the resonances are not that very strong, and you are not getting high quality factor resonances. So what you can do, you can put some organic dyes or semiconductor quantum dots into this particular dielectric area, and you can compensate for the metallic losses to some extent. And this is the case where semiconductor quantum dots are used in the dielectric, and you can see that you are able to restore those high and low scattering states which are very close to each other. Okay, and when this happens, you can see this particular case you are getting a scattering cross section of 0 dB, and where you here you get almost like minus 88 dB. So that much is the difference between the scattering states at this particular wavelength, which are very close to each other. So we are considering these H2 and L2 states, and you see you get 88 dB difference in the scattering. And this is what it means when you look into the electric field profile at these two wavelengths. So this is where the scattering resonance takes place. So this particular particle, nanoparticle, which is the size of the particle is only 20 nanometer, the outer radius. So the entire particle is only 40 nanometer in size. Okay, and you can see that this is behaving like a scatterer. This is the on state of the scatterer, and this is the off state, where entire electric field is confined in the dielectric region, and there is no change in the surrounding electric field. So entire region behaving in such a way that there is no nanoparticle present there. So this is the cloaking state or the off state of this particular nanoparticle switch. Other applications, what Professor Gagan Kumar also told, that there are many metamaterial devices where we can have lot more properties which we cannot see in the nature. So we can look of nanoplasmonic metamaterial devices as well. So these are basically 2D arrays of sub-wavelength metallic nanoparticles. And what is the task here? To come up with some extraordinary optical responses. And what is the best way to do it? We need to make sure that they can self-assemble very efficiently to form these particular metamaterials. And why we want this kind of dynamic, this kind of metamaterials which are static, they do not allow any in-situ control, and that is a problem. So when you do things from a top-down approach, you fabricate using E-beam lithography or other techniques, you get something that is done once and that's all. You cannot change it. But how about devices that can be dynamically changed? So that is where smart optical metamaterials comes into picture, which allows you first adjustable and reversible in situ control. So there are many applications like fast switchable window mirror or mirror absorber devices. You can use them as programmable optical filters and cavities. They can be used for energy harvesting, and they are always good hotspot generators for surge-based sensors. So again, this particular field of smart electro-optic metamaterials is basically driven by nanoplasmonics, but it brings together physical chemistry, electrochemistry, optics, and engineering. So this is a truly, a multidisciplinary in nature, and this is the dream of that particular discipline, to bring together these nanoparticles, and they should form any shape. Just like if you remember this scene from Robo, that all this Robo can actually form any shape. So these nanoparticles can also be instructed to form any shape, and that is how you can actually have a in situ controllable nanoplasmonic device. So what is the crux of this? You can take nanoparticles and have some ligands that can dissociate to acquire some charges in the electrolytic solution. So let us assume that these nanoparticles are now capped with negatively charged ligands. Okay, so now if you actually put these nanoparticles at an interface between, say, water and oil, they will self-assemble when the water part is negatively charged. So negative electrode in a water phase will push all the nanoparticles towards the interface. Okay, and that is where they will get trapped and they will form a 2D array. Now if you swap the polarity, if you make the water side positive, all the nanoparticles will be attracted towards that particular electrode and they will come out of this interface. So when they leave the interface, they actually make the interface transparent, so light can get simply transmitted. But whenever they are forming a very dense array, they are actually making a mirror. So that is how you can have an electrically controlled reversible mirror and mirror on and mirror off kind of a device. So this is basically a real image of the mirror that has been realized by assembling gold nanoparticles at water and oil interface under this polarity, and then once you reverse the polarity, you can actually make this particular thing disappear as well. Okay, so this is how one particular example shows that when you have a banknote at the bottom, so you can see the transmissive state. You have also kept a coin on the top. But as you keep on increasing the voltage, nanoparticles will come and assemble and form this particular mirror, and then that is where you'll start seeing the reflection of the mirror coin that is kept on the top. So that is how you can have switching from window to a mirror state, right? So how to model this kind of systems? So there are different ways of modeling composite media. One is Maxwell Garnett, another is Brugman, and the third one is layered approach. So if you look into the Maxwell Garnett, that is basically for separated grain structure. So what happens here, if you have nanoparticle dispersed in a particular solution, you can basically use Maxwell Garnett to approximate the effective permittivity of that particular medium. In Brugman, you cannot actually have, this is for aggregate structure. It means you are not sure whether one particular area is like occupied by material A or B. So if you have probability F for a particular area to be filled with material A, and there is probability 1 minus F for that same area to be of material B, then this is the formula with which you can calculate the effective permittivity. The other one, the layered structure one, that can be used also. So that is for this kind of multi-layer of thin films being deposited. You can use this kind of calculation where you have electric field along the interface, or you can have electric field perpendicular to the interface. So when it is parallel, you can actually see that these can be modeled as two parallel capacitors, and this is how you get the parallel permittivity. And for the perpendicular case, it will see capacitance is in series, and this is how you can calculate the effective permittivity. Now, where this can be used, they can be used for hyperbolic metamaterials, where you have alternating metal dielectric layers. But this is not our main objective today, but so I'm just giving you an overview of what all different methods can be used. Now, this is what our geometry is typically looking like. So you have, say, oil, and you have water, and you have a nanoparticle array. So how do you model this kind of system? You can take this two-dimensional hexagonal closed-pack array of nanoparticles, and you can try to use effective medium theory to model this as a uniform fictitious film which has got a permittivity that could actually emulate the response of this array. And how to obtain this? You can obtain this by calculating the polarizability of each particle that is now getting influenced by the particle which is next to it, from the adjacent rows, and also from the image charges, okay, from the same row, adjacent row, and the neighboring rows. So when you take into consideration all these different effects and then do a lattice sum, you can come up with the effective permittivity along the plane of this particular 2D array and along the perpendicular direction, which is given as beta parallel and beta perpendicular. And this tells you the typical lattice sum that you need to take over this entire 2D lattice, hexagonal lattice. And once you do that, you can have the idea of how to convert this array into a fictitious film. And then you have a problem of multi-layer thin film that is stacked. So you need to find the optical response of that multi-layer thin film. And in that case, reflectance and transmittance from Fresnel theory, age-old theory, can help us. So if you consider the Fresnel reflection theory and you consider the S polarization case first, so this is the S polarization case where the electric field is striking out of the plane of the screen. And what you can do, you can apply the tangential electric field components, which are continuous, and also the magnetic field components, continuity. And then you can come up with the ratio of the reflected electric field over the incident electric field, and that will be your reflection coefficient. Similarly, you can also find out what is your transmission coefficient. So this is a summary of the S polarized and P polarized light. So S polarized light will have electric field perpendicular to this plane of incidence, and P polarized light will have electric field along this plane of incidence, and for them you will see that there is a difference in the reflection and transmission coefficient. But at normal incidence they will have all, they will turn out to be same, and this is the transmitted wave condition from the refraction theory, that is for both the polarization. From this you can also find out what is the reflectance, that is the reflected power over the incident power. So you can obtain that as a, it is basically the square of the reflection coefficient. Whereas when you have the transmitted power, you need to take care of the refractive indices that will change the beam width. So here the beam width changes as a function of the refractive index of that medium. So you can get a transmittance that is given by this formula, where you have the transmission coefficient square times nt, that is the refractive index of the transmitted medium, times cos theta t over ni cos theta I. Now, after you know all this, you can apply that on a transmission matrix method that you can use for multi-layer system. So if you have a multi-layer system, so you have different refractive indices at different points, just like this. So what you see here, that you are actually hitting the interface between two different materials, and then you are going inside that particular material. So there are two different effects that is taking place here, and one will be the reflection and transmission coefficient for the interfaces between Ni and Nj layer, and another thing, what will be the change in the electric field due to propagation within a particular layer. So once you consider these two things together using transfer matrix method, okay, you will see that transfer matrix method basically brings in the Fresnel reflection coefficient and transmission coefficient and try to estimate what happens for each interface and also for each layer. I'm not going into the details, I'm just telling you these basic theories can be applied, and you can actually find a multi-layer system. You can multiply all their different T matrices and come up with a final matrix, and from that final matrix you can obtain what is the reflection and transmission coefficient by taking the ratio of these two terms. So this ratio of these two elements of the final matrix gives you reflection, and 1 over T11 gives you the transmission coefficient. So using these two basic and fundamental theory, you can always calculate what will be the reflection and transmission from this complex system. And you can also do COMSOL modeling, where you have this 2D hexagonal array. You can define this unit cell, and because of symmetry you can take half of it and simulate it, and you will see that there will be very close match between the theory and the COMSOL simulation. Another kind of nanoplasmonic metamaterial device you can design at solid liquid interface, where you will have a silver electrode that can be polarized negative, and then you again have this negative nanoparticles in solution, that is water. So when it is negatively charged, there is no nanoparticle on the interface, so silver will act as a mirror, so you get perfect reflectance of 99%. But when you change the polarity, you bring all the nanoparticles and make them form a very dense packed array on top of your silver substrate, and that will behave like a perfect absorber where you get reflectance of 0. Okay, so this is what has been theoretically predicted. So you see from 100% to almost 0% by changing the size and the shape between the nano and the gap between the nanoparticles, you can change the wavelength at which you want to achieve this feature. This is an experimental realization of the nanoparticles coming and getting deposited. So here you can see with positive voltage, nanoparticles are much more populated on the silver film, and you see how dark it looks like. So it behaves like a complete absorber from this reflecting state. Another example, and this will probably be the last one today, I would like to discuss. So we can also make smart nano-optical devices, something like electrically tunable Fabry-Perot cavity. So all of you might be knowing about these Fabry-Perot cavity resonators, which are very useful in many devices like laser resonators, and they are also used for filters. Okay, so let us assume that we have Fabry-Perot cavities where the mirrors are basically made of TCO or thin silver electrodes, and they are also having some nanoparticle solutions in between, and nanoparticles are again negatively charged. So when you change the polarity, you can attract more nanoparticles on them. So what will happen? This reflectivity of each mirror of the fabric cavity can be tuned by changing the applied potential, and that will allow you to change the wavelength of light that can come out of this cavity. So usually people, what they do, they have to either manually alter the cavity length, or they have to change the refractive index of this cavity medium to get this tunability. But here you can actually change the reflectivity of the mirror surfaces using this mechanism and get that kind of electrically tunable fabric cavity. So these are the results you can think of. So you can see here that theory and simulation. The theory I discussed before, that you can use effective medium theory with multi-layer Fresnel reflection scheme, and you see the theory and COMSOL simulation, they are perfectly overlapping. And this is the case when no nanoparticle is there, and when nanoparticles like silver nanoparticles of radius 10 nanometer, and they are forming a 2D array with a gap of 6 nanometer is there, you can see there is a shift in this particular resonance wavelength. So the same device can be used to get, obtain multiple wavelengths depending on the resonance conditions where it is getting satisfied. So this is how you can change the polarity, you can attract more and more particles, and that is how the gap will get reduced, and you can shift your transmission wavelength more towards the red in this kind of devices. So this particular electrically tunable, electrochemical fabric cavities can be used for fast in situ electro-tuning of the optical transmission spectra. And what good thing about here is that, besides electro-tunability, what you are using here is the basic feature of surface plasmon resonance in a collective array, and that's why they are also subject to their shape, size, and composition, whereas the overall physical structure doesn't need to be changed. And this is basically a bottom-up approach for designing this kind of electro-tunable devices. So you have the ease of application, programmability, and also they are very energy efficient. As you can see, they all work with sub-volt range potential. The other application of this could be in enhancing, the light extraction from light emitting diodes. So here again, this nanoparticle arrays, which is basically plasmonic nanoparticle arrays, can be placed on top of the LED chip.
Sorry to interrupt you, sir. We are running out of time, so kindly
I'll just take 2 minutes.
kindly wrap up. Thank you, sir.
So this is the last application I'll be showing you. So for LEDs, we have this particular critical angle problem. So where the light is going from a denser to a rarer medium, and light that is incidenting at a larger angle than critical angle will be internally reflected. Even light which is incidenting at an angle lower than critical angle, because of Fresnel reflection laws, there is reflection. So that is also coming back to the LED chip, and it is getting reabsorbed, and the chip is getting heated up. So what you can do, you can place nanoparticle array here at a particular height from this LED chip into the epoxy layer. So this nanoparticle layer will basically act as a matter grid that allows you to bring out more light by allowing some destructive interference between the light that is reflected from this layer and from the interface. So this is again another application of plasmonic nanoparticles that can find a lot of applications in LED market, where you can improve the light extraction efficiency from LEDs by not only making the LEDs brighter, you can also make them live longer because the unnecessary heating from the reflected light is reduced. Okay, so this is particular some simulations and results. So this flat dotted line shows you the LED extraction without any nanoparticles, and this line shows you simulation and theoretical results when nanoparticles of gap 10 nanometer is placed, 10, 20, 40. Here different height, they are placed at different height. In all cases, you can see that they are basically able to, outperform the benchmark. So this is another possibility where plasmonic nanoparticles forming a metagrid can be used for light extraction. Okay, so with that, I will stop here and I'll be happy to take some questions. Thank you.
Thank you, sir, for enlightening us about the topic. Now we will have first question. So recently, a lot of press reported about your work on smart window development.
Yes.
So Professor Arun Tej sir wanted to know, could you please elaborate the work and its future prospects?
Okay. That smart window work is basically a electro-tunable color filter, and that is basically based on multiple layer of metal dielectric films where you put a electro-optic polymer between two metallic electrodes. Now, why I didn't show that thing here is that in this particular theme of plasmonics, we are talking about the surface plasmon resonance. But in the smart window, we do not specifically are interested in surface plasmon resonance, because resonance typically is the narrowband feature, and smart window works over the entire solar spectrum. So we are basically interested in a wideband application. So in the case of smart windows, we have tried two different geometries. One is metal dielectric metal, and another one is dielectric metal dielectric, this kind of orientations. And in each case, what we have done, we have put metallic layer, thin metallic layer, so that light can be allowed to enter the device. And then you will have Fabry-Perot kind of resonance happening in this particular cavity, but the resonance wavelength can be tuned by changing the polarity or the refractive index of that electro-optic material which is kept in between. Okay, so that is one particular application. One particular application is that smart windows. So there you can change the resonance from visible to near infrared to selectively choose whether you want light or heat to enter your room. Okay, so that is one particular application. What I wanted to show here is slightly different. That I want to show here the power of plasmonics, in the sense that you can actually have a completely tunable device where the structure of the device itself can be changed by using these electrochemical methods. And as you can understand that if you change the size and shape of the electrode on which the nanoparticles will assemble, then you can actually make any particular form. So that is another big aspect where a lot of people are working towards, and that has got a lot of future. I hope the question is okay.
Thank you, sir. We have lots of questions, but for the time foundation, we will move to our next session. Once again, thank you, sir, for your valuable time. And participants are requested to contact him through email if they have any further queries. He will try to answer if time permits.
Also, chat box he can drop.
Yeah. Also, you can drop in the chat box.
You can write in the chat box their answers.
Yeah.
Okay.
Okay.
Yeah.
Acha, Devasis, yeah. Devasis, you can in the chat box you can give all the answers. Okay.
Okay, sure.
Yes, sir. Thank you, sir. Once again.
Thank you.
So now we will move towards our last talk of this session. The last talk of today's session is on the topic from spin to sprintonics by Professor Tanmay Datta. Professor Tanmay Datta is an assistant professor in the Department of Electronics and Electrical Engineering at Iitg Guwahati. He joined the institute in January 2022. He has earned his PhD in Electrical and Computer Engineering from National University of Singapore in 2018 and BTech in Electrical Engineering from NIT Durgapur in 2011. He led successful collaboration with NTU, Yonsei University, Middle Eastern Technical University, research institutes such as IMRE and IME, and industrial collaborators such as IBM, HGST, etc. He has co-authored more than 19 international and national journal articles, 12 international conference presentations. He is a recipient of prestigious Marie Curie Postdoctoral Fellowship 2019 and Fallingwall's Emerging Talent Winner 2022. His research area mainly includes developing thin film solutions for future data storage and computing, processing, energy, and biomedical applications. With this brief introduction, I would like to welcome Professor Tanmay Datta for the talk on From Spin to Spintronics. Requesting sir to take over from here. Over to you, sir.
Thank you so much. Am I audible?
Yes, sir.
Okay, thank you so much for the nice introduction. Hello, everyone. And I'm really glad to be here. And I will not further delay and start with the presentation. And let me share my screen first. So, can you see the screen?
Yes, sir.
Okay. All right. Yeah. Thank you so much. Thank you, everyone, and thank you for this opportunity. So, before my talk is titled "Spin to Spintronics." So, we will begin with the spin of electrons in this case, and then we will end at spintronics, where we will discuss about different spintronic devices and technologies. Now, in the middle, we will go through a journey of different concepts. At the same time, all of these concepts will be introduced mostly through practical devices and or let's say computing or memory technologies. Okay, so this is how the talk is designed, and you will see that this whole, how this whole journey from spin to spintronics integrates with different fields of material science, material engineering, chemical engineering, electrical engineering, physics, it's nanotechnology, all coming together to make these things happen. So let us begin. So the first thing is spin. So we start from spin. So here in this case we will talk about the spin of electrons, and no, electrons have two different spins that we will discuss. Okay, so we have the spin moment and the orbital moment. The spin moment arising from the movement of the electrons on its own axis in a classical sense, and also the orbital one arising from the moment arising from the movement of the electrons around in its orbit, right? So it's the orbital moment, and these two moments can act individually. At the same time, they can also couple together and present something called spin orbit coupling. So they can individually give rise to magnetic moment or magnetization. At the same time, they can combine together and have very exotic effects, which we'll see later, and through spin orbit coupling, and also therefore give rise to different forms of magnetization or different magnetic effects. Now, so single electron will have the spin moment and the orbital moment, and the interaction of these electrons can have different kinds of interactions among themselves. These magnetic moments can interact with each other in different ways and manifest in different ways. So the first one is the exchange interaction, which is quantum in nature, and what it basically does is it makes the spins or the moments align parallel or anti-parallel to each other. So as you can see here, there are two neighboring moments being aligned parallel, while in the below one they are aligned anti-parallel to each other. So this is the kind of orientations of adjacent moment or adjacent spin that nature favors through exchange interaction. And the second interaction here is the anisotropy, in which this is more coming from not from a single or two electrons. It's more of a collection of electrons that come, for example, an electron cloud. And very often in some materials you will see that there is an anisotropic distribution of this electron cloud, like in crystals, and that can therefore lead to anisotropic magnetic. So that's why you call it anisotropy or magnetic anisotropy. And the third one is a purely bulk phenomenon, that is magnetostatics, in which there will be magnetic, in a classical sense, if you think magnetic flux or magnetic poles will be there, and the poles will try to be as far as away from each other, like two magnets, right? The north of two magnets would not like to face each other, so that kind of a thing. So this can be understood in that kind of a bulk interaction. So these are three different interactions I am saying here. There are more interactions. Some of them we will also see later. Now, these three interactions and maybe a few more of them can come together and combine, and their combined effort will result into some classes of materials. The most common that we all know is a ferromagnetic class of material, where all the magnetic moments are aligned parallel to each other. And this is example is like iron, cobalt, and all those, or nickel, for example. These are normal ferromagnets that we have encountered in our daily lives. Then the second class of material is antiferromagnetic, in which the adjacent magnetic moments are all aligned opposite to each other, antiparallel, and the net magnetization of these materials is zero, capital M, as indicated to be zero. The third class is a ferrimagnetic material, where the magnetic moments are again aligned opposite to each other, but the magnetic moments are not equal, and therefore the net effect is not equal to zero. So capital M, in this case, the net magnetic moment is not equal to zero. And the fourth class that I am showing here is a paramagnetic material, where the individual moments or spins are randomly organized, and therefore we do not have any net magnetic behavior of this material. Now this is a very let's say crude definition of this kind of materials, but at least gives us an idea of the different variety of materials that these magnetic interactions can create. And very often magnetic materials are characterized or directly observed in terms of domains, for example. So these are some magnetic domains. When you see yellow and red, they're basically two different polarities, let's say north, south, or 1 or 0 if you talk in terms of storage, or if you talk in terms of a normal magnet, let's say the magnet we generally know, then it is a north south, for example. So two different colors represent two different orientations or domains, right? So domains, basically each domain here, each color here is one domain, and each domain is consisting of a collection of different magnetic moments. So this is again a macroscopic collection of a lot of individual magnetic moments, right? But this is a direct view of the magnetic moment. Now we have already discussed about the one of the exchange interaction, which is a direct exchange in which the magnetic moments align parallel and anti-parallel to each other. In addition to this, there are two other exchange interactions which we will just we will not discuss in detail, but only thing is that you can understand that they are indirect. So both of them are indirect, so they are not directly working between two adjacent neighboring moments, but between moments where they are far apart. So there is a distance, there is a finite distance in few nanometers maybe between them, and yet the moments are interacting with each other. And that's called the indirect, and there are two different or at least here I have mentioned two different indirect exchanges, the super exchange through example through oxygen orbitals here, and the indirect RKKY which happens through in non-magnetic layer. We will look into the indirect RKKY in one of the applications in the following slides. In anisotropy, as I already discussed, that it results from the anisotropic distribution of electron charge clouds, for example, in crystals, and therefore gives a preferential axis, let's say in this direction or in this direction, for the magnetic moments to align. The third one is magnetostatics, as we discussed, and this is a more macroscopic one, and can be imagined as two big bar magnets, as like shown here, for example, where the magnetic poles wants to be far apart. So this works on pole avoidance, and to minimize energy of the system, the magnetic poles wants to be far apart, and if in some cases they will form a domain, like you can see here, to break and to create more poles, so that the energy is minimized. So this is the third interaction that we talked in the first slide. Now this is like a hysteresis loop. It's a schematic of a hysteresis loop. So any magnetic material will have hysteresis. So and this hysteretic behavior actually gives rise, or is the reason why it can be used for storing information and memory, because you do not return to the same state as you start from in absence of an applied field. So when a field is applied, you can change the magnetic moment from one direction to the other. But if you let the field go, you will not reach to zero, and your information will not be lost. Rather, you will still have a net moment left, although less than the saturation moment ms, but you will have a net moment left, mr, or remnant magnetization, which gives to because of which property it can be used to store information and without losing them. So so now, in terms of devices, or in terms of real-world application of magnetism or magnetic devices, if we see, so we have a memory hierarchy, for example, and we all are familiar with, let's say, our computers, and our computers have hard disk drives or solid state disks, and also you have the cache and the registers and the RAMs. So these are all different kinds of memory technologies, and all of them have a hierarchy. Now here you can see that the highest ones, the registers, are the most costliest and also are the fastest, and the lowest ones are the most cost effective ones, but at the same time they're the slowest ones, right? But they have the highest capacities. Okay, so hard disk drives, for example, would belong here in traditional disks, and RAM would belong here, right? So now if we look at this memory hierarchy, we can see that there is always a trade-off between different parameters. You cannot have all of them at the same time. You need to optimize, and depending on the application, therefore we use what we need. Now what is the challenge? The challenge is to, therefore, we need everything, right? We need to make the system faster. We need to increase the storage capacity, that is, make them smaller and smaller. At the same time, we need to also reduce the cost. So these are all conflicting, and therefore needs a lot of work and optimization and new discoveries in terms of physics and chemical engineering and so on, to really make these things happen. So we will revisit this memory hierarchy once we have gone through all the technologies we discussed, and we will end this this session on this slide itself and see what we have discussed. So this is where we begin on the memory technologies. Now we will first talk about the hard disk drive. This is the one that has the advantage of storing more information, but being slower, right? And so far we have been able to really push the density of, or the areal density, or the density of storage till so far. I mean, by making different technologies, making incremental changes, sometimes very huge disruptive technological changes as well. So we are still using hard disk drives, and it will probably still stay here for at least another decade or two, and we will be our mainstay for storing information. Now and SDDs are soon catching up. As you can see here, the green curve is slowly merging with the blue one. So very soon SDDs will merge with the areal densities for hard disk drives as well. But the advantage that hard disk drives still have is the cost per bit, or cost per GB, let's say, and HDDs are still quite cheaper, a lot cheaper compared to solid states. So that's the major reason why we are still using HDDs, or hard disk drives. Now in hard disk drives, okay, we will first begin with the first thing, the first hard disk drive that we had. And here you can see something that was built in 1956, and you can see this man, his head through this hard disk drive, and this was the first hard disk that was built. And today, the hard disk we have is in our palm, in the grasp of our hand. So it's so big, and the storage capacity actually has come from 5 MB to 4 TB, and look at the size, right? So you can imagine the kind of development that has happened in the past 6-7 decades, right? And because of the emerging needs and the ever increasing need for hunger for data, we really need to boost up our capacities for data storage, and therefore all of these technologies are very important. Now, as I said, this was the 24-inch hard disk that was created. Here you can see there is a stack of them, all 5 MB disks kept together, and this is the storage capacity for the IBM 304 RAMAC that was built in 1956. And yeah, so you can imagine, right, how big this huge system would have been, right? So it took almost half of a room to accommodate this system. Now, since then, we have been constantly increasing on the areal densities, and as you can see in the red text here, at every point there has been new technologies that has been introduced. Some of these technologies we will now go through this curve and see what are these technologies that have made this happen, right? So we have now reached very high densities, and therefore we are able to get this or keep these hard disks in our hand at like even a 4 TB or 5 TB hard disk, right? So we began with longitudinal recording where the magnetic moments were aligned in the plane, or let's say if it is a table and it is on the table along the plane of the table, the moments are along the plane of the table. Now I will come to it later why this is important, but we need to remember that in longitudinal magnetic recording the moments were planar, and going ahead it changed, but we will see why and when. Now the reading is, so here it's a TEM cross section of this kind of a magnetic layer, and you can see the top layer is a recording layer, and then there are under layers, and there is a substrate, maybe a silicon or a silicon oxide substrate, right? Now how is it read? It is read by a magnetic pole which generates a flux, and then the magnetic flux is affected by the magnetic signal that it reads, and therefore the current is also affected, and similarly it is also written by generating a localized magnetic flux here, right? Okay, the first one, the first disk that I showed you, 1956, that was built by something called like this, where magnetic particles, they were not nano, they were really big particles, and in few hundreds of nanometers or microns, these particles were then spread out through a binder, and these particles or ferrite oxide, basically these are oxide particles, and these particles were used to store information, and therefore the density was very low, and it needed a huge volume or huge surface area to store information of only 5 MB. Now since once deposition techniques improved, we started depositing thin films like you can see here, and the size is reduced to, let's say, a few tens or hundreds of nanometer of this grain. So instead of now having disoriented particles, what we had was a continuous film, but the film would break into grains, and these grains would, a collection of these grains would then be used to store information, forming a domain, right? So for example, here you can see these are grains, all these grains. Now there is a domain boundary here. So on right hand side there is one domain, on the left hand side there is another domain, and therefore the magnetic moments are in different directions, as you can see, right? So these are two different domains on two different sides, each domain consisting of a number of grains. Now a lot of research was needed here to optimize. I mean, I'm just putting one slide here, but there was 5 decades of research to really make these things happen. And we were using this kind of technology or this kind of hard disk, and a lot of structure, metallurgical, chemical engineering had come into effect to really make these things happen. Now, what was the challenge here? The challenge here, we wanted to make the domain smaller, therefore the grains also smaller and smaller. And when you make smaller, what happens is the volume, the V, reduces. Now the information is stored or is kept stable by something called the thermal barrier. So if these are two different states on two different stable states, let's say, or low energy states, they are separated by an energy barrier KUV. Now this KU is the crystalline anisotropy that we discussed in the first slide, and V is the volume. Now the volume, therefore, as it is reducing, so lower the volume, the bits will become unstable. So this barrier will become lower. And if the barrier is very low, then we will have information flipping from one direction to the other by even probably in thermal fluctuations, right? So our information will not be safe. So therefore, we need the thermal barrier to be much higher, so KUV to be higher. So this technology was no longer working because we could not make it smaller and smaller. So we had to shift to something called the perpendicular magnetic recording, and here now you can see that we began with the moments in the plane of the disk, let's say. Now the moments are perpendicular to the plane, so they are aligned top and bottom, right? So this was a new technology that now started, and it was a disruptive change actually, because everything had to be changed from the reader to the writer in the early 2000s. Now again, perpendicular magnetic recording had the advantage of letting us reduce the size of the domains of the bits, right? We could store the bits or information in smaller dimensions. This was because now the bits could be smaller and be adjacent to each other, but not affect each other. Why? Because in the longitudinal sense, you can see they are opposing each other, or in some cases, for example, they are opposing each other, like in transition, right? They are opposing each other. Now this is unstable, so if they get too small, that they will start changing each other and influencing each other. Therefore our information will not be stable. But here you can see these magnetic moments are aligned parallel or anti-parallel, and therefore they do not have this effect of destabilizing the neighboring bits, and therefore they can be shrunk smaller and smaller, even without or much smaller, like even till sub 10 nanometer without problem. So therefore we had to shift to perpendicular magnetic recording. So so as I mentioned, this pole avoidance, the poles wanted to be as far as possible, and therefore here you can see the poles are getting closer, right, when the bits are getting smaller. Here the poles are in top and bottom, and therefore even if you make the bit smaller and smaller in dimension, the poles will still be apart, right? The north and south will still be apart, because that depends only on the thickness of the film and not on the width of the bits. So okay, so this is the main reason why we shifted. Now what happened was we shifted, but the problem was that now as we are getting smaller, the conventional material COCRPT, this was the conventional mainstay for all hard disk drives till early 2000s, even let's say till 2010. The problem was that as it was getting smaller, it was now the V problem was gone, but the KU problem remained, because the KU was still low for this material. So therefore people started to look for materials with higher KU or higher anisotropy, and we can see that iron platinum was a material which was discovered, or not discovered but known to have very high, at least one order higher than COCRPT, right? So therefore people chose this material, and started making hard disk drives with this material. And of course a lot of work had to be done on optimizing these thin films for hard disks. Now this is the roadmap in which the grain sizes would be reduced, and we are really now very small somewhere here, and the projection is to reduce the grain sizes to even higher, but we do not know really when we get there. Now even with perpendicular magnetic recording, there were many problems, because as the demand goes higher, the areal density that needs to increase, the bits need to be smaller, so it is still a problem. Now what was the problem? The problem was the conflicting requirement between the writability, the thermal stability, and the signal to noise ratio. Now I will not go into the details of why this happened, but let's just say that there were these three conflicting requirements. And because of that, people came up with different, these companies and research institutes, universities, now they started researching on advanced memory technologies. And two of them I am presenting here is HAMR and BPM. So HAMR is heat assisted magnetic recording, and BPM is bit pattern media. Now what happens in HAMR? In HAMR you can see like near field transducers, this one made of gold for example is used, and plasmonics is actually utilized to generate a localized heat, and the localized heat that is generated is therefore used to reduce the anisotropy of this material temporarily, so that we can then switch the magnetization or write the information on it easily. Okay, so here you can see it is heated, so the field that is necessary to write the information is much lower, and so it's within the available head field, so we can therefore write it and then let it go back. So once the media cools, it goes back to the original state, and the information is securely kept there, right? So it made writing easier at lower applied fields as well. Now this is one design of how heat is applied. There are other designs as well. So here this is right from the previous one. So this is this uses a NFT and this is a paper where they developed this NFT. So I'll not go into this one. Yeah, so the other system that they use for heating is called a VCSEL. So here this vertical cavity surface emitting laser is used. Again, very few tens of nanometer of spot is generated to heat up the disk or the magnetic material locally, and then write the information on it. So this is a TEM cross section of a hammer media, and as you can see all these circular things, as you can see here, these are the grains, right? So this is the iron platinum grain, and there are different layers below this, right? This is from a Western Digital picture. So this is a real hard disk, and this is how the cross section looks, and this is how the top view looks with different grains. So this one is the top view with all the grains, and there is an insulating silicon oxide or some other or maybe carbon which is separating the two grains, right? So this is how it is. Now here what I'm presenting is a problem that was addressed in one of my works in hammer media. So in the last slides I just discussed about the mechanism of hammer media, how hammer media works, right? So what I am now presenting is a solution that was provided to solve one of the problems in hammer media. It has some problems, and this work was solving one of them. Now, what was the problem was that you can see there is a localized, as I said, there is a localized heat. So in A, for example, the gun is or the laser is off, so there is no heat. In B, you can see the laser is heating the grain, and we are making these magnetic movements random. So basically, the field that will be required to switch this magnetization will become lower, and then the field, the south pole, for example, shown here, is trying to switch this magnetization. Right, the south pole is trying to switch this magnetization. So it will now switch it. However, what happens is because there are adjacent magnetic grains, they will try to adjust magnetic domains, let's say, they will try to influence the applied field on this hot region. And because now it is very weak, or the anisotropy is very weak locally, it will easily switch or switch to a state which probably we don't want. So therefore, in other words, there is an exchange coupling from the adjacent domains, and we don't want that. So that was a problem in hammer media, and what that would cause is corruption and bit error rates. The bits would not be written as we want them to be, so there will be error in writing them, right? So therefore, what we had to do was, what we did was, we introduced this concept where so here what we did was that instead of having a single layer, we had a top layer on it of cobalt platinum. And what it does is, this additional layer of cobalt platinum does is that when it is when iron platinum here is the storage layer is nearly paramagnetic, let's say, and all the anisotropy is lost, but the top layer of cobalt platinum maintains its orientation, and therefore it negates all the, or it protects like kind of a shield from the adjacent domains, and therefore it doesn't let the adjacent bits to affect the writing process on this desired or target bit, and that's how it protects the intended bit. And this is because of the difference in the Curie temperature of these two bits, of this two material. For example, cobalt platinum has a much higher Curie temperature than iron platinum carbon. So this way we managed to solve this problem of coupling from the adjacent domains or bits, right? So this was the experimental structure that we had designed, and with the COPT layer on the top, as you can see here, and this was used to then shield the iron platinum carbon layers during the writing process. So these are the TEM structures. I will not go into this one, and here you can see that so here you can see that the switching field distribution therefore was much lower for this green curve you can see here. So when the cobalt platinum 6 nanometer thickness was used to cover or to shield the iron platinum storage layer, we could see that we could achieve the lowest switching field distribution by using this. So this solves the problem of bit error rates during the laser writing process in Hammer, right? So the second thing that I mentioned there was bit pattern media. Now here bit pattern media is completely different from what is the so-called conventional media. So in conventional media, as you can see here, many grains form one single domain and therefore is called one bit. But in bit pattern media, each bit is patterned separately and each bit is one domain. So there are no grains inside these bits. So you imagine a continuous film and then you use different patterning techniques, etching, lithography, all patterning techniques that can be used, and you can then make these shapes out of or islands out of a continuous film. And this is how a bit pattern media can be visualized. So here the cartoon shows let's say all these bits. So these are isolated bits, and it's very different from the conventional recording, let's say. Now, what were the challenges in bit pattern media? Now, of course, as everything has challenges, bit pattern media also has its own challenges. The challenge in bit pattern media was that how to pattern these huge discs, right? It takes a lot of time. People who are familiar with patterning will know that it takes a lot of time to pattern these big areas, right? So to pattern a whole disk, it would take a very long time, and therefore a way had to be found to do this. So one way was that is practiced is to have self-assembly. So the mask basically so the green one is a film, and then a mask is self-assembled on top of the film, and then it is etched to create islands, right? So for example here, so here you can see the top one shows all the AFM images of the films, and then after creating a self-assembled mask and then iron milling, let's say, or doing some physical etching, you will have this end up with these islands, right? Now what is seen here is that as the roughness of the surface of the film is increasing, you will have distortions and non-uniform patterns, and at 8.2 angstrom of RMS roughness, you see that almost all the patterns are damaged, right? So it is very important to have smooth films to have to work with self-assembled masks. So that's why this was not possible, because self-assembled masks, to have such a very high level of smoothness in films with such tens of multi-layers in a medium, in a magnetic medium, is very difficult. So this was not possible. The second method that was used was ion irradiation. So what you do is you take a film and then you use ions to physically etch away, or not physically etch away, but to damage the magnetization in certain local places. And this magnetic damage that is done by incoming ions, that creates basically these non-magnetic spacers, right, between in a continuous magnetic film. So this was also then studied. So for example, you take a continuous film, and then you have in the green regions, for example, right, which is not masked. So the orange ones are the mask. And when you introduce the ion irradiation, the incoming ions will damage the crystalline structure in the green regions, right, the exposed regions, and this will become non-magnetic. So you will basically have islands of magnetic material M separated by non-magnets green, right? But what was the problem? The problem was here again, you had the problems of lateral straggle. The ions that would come would not be going straight into it because of different kind of collisions that will encounter, electronic and mechanical both. It will therefore create this kind of craters which are isotropic, and therefore you will not have the desired islands that you wanted to have like this originally. So we started to use low energy irradiation, and with that we could achieve bit patterns which were very stable, and where the magnetization was also very nicely, when you start with the original film, the reference one, the unpatterned one on the left, and on the right you see the patterned films. So there is not much change actually. The change is much lower compared to when it is damaged, right? So therefore we could achieve very bit patterns with very low energy irradiation, and so we could see that low energy was the way to go ahead. However, that still had some problems. The problems was that of patterning itself. So what are the problems of patterning? You have sidewall etching issues, for example. So there is shadowing issues, there are trenching issues. So these are all standard known patterning issues, right? So this will be faced in any field where you need to make sub tens of nanometer devices or hundreds of nanometer devices. You will face all these standard patterning problems. So therefore, and finally was the planarization problem, where all of them had to be in the same height. They cannot be raised physically like this, because a hard disk read, the read head will go near and read it, and the distance between the read head and these raised portions will be less than 10 nanometers. And therefore in that situation you cannot have it raised like that, because it will crash on this disk. So it's a physical thing, you can imagine. It's like in the industry they define it as like a flying a Boeing just like 1 centimeters away from the surface. So it's something like that. So therefore you cannot have these raised structures. So what we did was we took a different route. We created it in a different way. So this is on the left side, you see the destructive transformation, as I had shown before, as I had said before, that you create the masks and then you expose it to ion beams, and the exposed areas become non-magnetic. However, what we did was we started with a non-magnetic or a paramagnetic material. So this is a paramagnetic material of cobalt oxide, and what we could do is we then we masked it, right? Standard photolithography process. But here we then used hydrogen ions, and by using hydrogen ions, we chemically changed it instead of physically. We changed it chemically from cobalt oxide palladiums to cobalt palladium. So therefore, once the mask was removed, what we had was this alternate areas of cobalt oxide and cobalt palladium. And cobalt oxide is paramagnetic, but cobalt palladium is magnetic. So we had magnetic islands which were chemically created by phase transformation and not by physical etching or by physical transformation, right? So that's why this was much better way to go, and it could circumvent all the problems that I had shown before. So this is a cartoon which shows the same thing. And on the right hand side you can see, so here this is the cross section. You have these magnetic moments which are paramagnetic, all aligned randomly, and when the irradiation takes place through the openings in the opening region, all the magnetic moments now align parallel to each other, let's say, and they become magnetic. So on the side you have non-magnetic, and then you have magnetic islands. Now I will just skip through these ones and I will come to the second part of the talk. Sorry for okay, so maybe we can start from here. So on the third technology that is used is called MRAM, right? Here microwave is basically used instead of the laser heating. Microwave is used. Microwave energy is used to reduce the writing field. Now here what happens is you use spin torque oscillators. So when a magnetic field is applied, the magnetic moment is trying to align with the applied field. But when a current is passed through it, it applies an orthogonal torque to it, the spin transfer torque. Okay, and this torque will therefore have the two different torques that it is facing, right? So one is along the up direction, the other is towards the orthogonal to it. This will make it precess. So it will precess around the point, and the more this red thing, the spin transfer torque, the more it will try to become bigger and wider precisions, right? So what we in spin torque oscillators, we operate in this regime when it is not so big that it will switch completely from one direction to the other. Rather, it remains precessing here. So this is where you can have spin torque. The moment is precessing around a certain axis, right? Now here what it is used for is then when this frequency matches the natural frequency of the system, there is resonance, and that transfers the maximum amount of energy to the media that is being written, and we can achieve writing. So I'll just show you the demonstration here. So you can see here that these are different lines which are written at different frequencies. So basically the frequency defines the energy that was provided through the microwave, and you can see how at different frequencies different lines can be written. As it gets very low at 8 gigahertz, for example, the magnetization, you can see it's very blurred. So basically the writing was not very proper. Using the proper microwave energy, we can write this information easily without applying much higher fields, right? So that's why it's called microwave assisted. Now, because we talked about the spin transfer torque, right? So here we talked about spin transfer torque. So this one. Now, spin transfer torque is now used for, so far what we have discussed is all about the disk part of the hard disk, where the disk is there. Now what we are discussing is about the reader part of it, right? The middle part we discussed the writer, and now we are talking about the reader part of it. So if in the reading part we used magnetic tunnel junctions, right? Magnetic tunnel junctions are used which can be in the readers. Now these magnetic tunnel junctions can also be used as memory itself, as units of memory, and they are used in RAM, for example, and which is called magnetic RAM. So we are all familiar with RAMs, the normal or conventional RAMs, but this is magnetic RAM. So here they are connected with read and write lines, and you can see there are two magnetic layers which are separated by a insulator or a insulating barrier. And you can imagine this is like a water flow. So there is a gush of water coming on one side, but there is a barrier. So only very few of it will pass through sieves and crevices that is existing in this barrier, but it is not overflowing it, right? So it just a little of it is leaking. So that is like tunneling. So it's a very small quantity of electrons, let's say, or spin dependent electrons tunnel from one side to the other, and that's magnetic RAM. I mean, that's the functional, that's how MTJ functions. We'll see the other functionalities of it in the next slide. So now it can have two states, as you can see here, depending on the mutual orientation of these two layers, the two green layers. They can have two resistance states. So the current that is flowing through this structure will face two different resistances depending on the mutual orientation of the two layers, and therefore we have two different states, 0 and 1. So here, as you can see, the effective field is applied, let's say, in this direction, and there is a damping torque in the that is trying to take it back to take the moment m back to the applied field direction. But there is a field like torque as well, which is acting in this direction, and these torques basically make it precise if not enough energy is applied. But if enough energy is applied, then it will also make it switch. But in nutshell, when it is passing, it will face a torque basically on the moment, and this torque that it faces will depend on the orientation of the magnet. So for example, as you can see here, when it is passing through, the current is, or the electrons are passing through this, if there is a parallel state like this here, if they're in the parallel state, both of them are in the same direction, then the resistance is much lower. While if they are aligned opposite to each other, if the magnetic layers are aligned opposite to each other, the resistance that it faces is much higher. So therefore we can have something called and the difference between them when taken as a percentage is called the tunnel magnetoresistance, or the TMR, right? So this TMR is what defines the two states, or defines, let's say, how good your device or your tunnel junctions are. And based on this functionality, what is designed is the STT MRAM, right? So earlier what we had was field driven MRAMs, right? The magnetic MRAMs were switched using field, HX, let's say, is an applied field. But with spin transfer torque, this process of spin transfer torque, what we have are STT MRAMs, right? Now STT MRAMs can have planar like this, where the magnetic moments are planar to each other, and perpendicular where they're aligned like up, top, down like this, and then they are selected by a select transistor. Now in a spin transfer torque MRAM, the write current and the read current both passes through the entire stack. Okay, so this is an important feature of STT MRAM. And so here you can see, for example, these are two different on the two different sides of the yellow. The yellow one is the insulator, and the red one on two sides, or the red and blue on two sides, these are the ferromagnets, or the magnetic material. And depending on the density of the density of states of the majority carrier and the minority carrier on each side, the electrons or the spin carriers therefore can transmit from one direction to the other from either side when a current is like passed through it, right? So that how much of the or how much of a certain spin passes through will then depend on of course the tunneling barrier, and then the density of states as shown here, the density of states on either side, and and also the amount of current that you are passing through. So these all factors will come into determine how much of electrons actually tunnels through this barrier. And this is called the magnetoresistance, right? So because this is magnetically dependent resistance, so it's called the magnetoresistance, and because of the tunneling layer, it's called TMR, or tunneling magnetoresistance. Now, in development of MRAM, there are two different layers, as you saw, reference layer and the free layer. The reference layer is a thicker layer whose magnetization is the reference, serves as the reference, and the free layer is free to switch. And depending on its orientation, we know the state of the MRAM. So is it in a parallel state or anti-parallel state? Depends on which direction the FL or the free layer is. So okay, so the free layer, how do we develop the free layer? To develop the free layer, we need to first decrease the size of it, right? We need to decrease the area. But the thermal stability is given by this relation. So if we need to decrease the area of these devices, the thermal stability will go down. So we need to therefore increase the Ku effective times T, so this factor, right? So the anisotropy needs to increase. So if we want to increase the anisotropy, the writing current, the current that is needed to write this, write information on them, that also increases. So how do we now increase this? Increase delta, that is the thermal stability, but still keep the current low. Now we can do that by reducing alpha. Alpha is the damping factor. The alpha is a damping factor which is intrinsic to the material itself. Now that is done by choosing the right material. Now here different materials are not useful for different reasons, as mentioned here. So the best candidate we chose was let's say, or we can choose, is cobalt iron boron MgO. Cobalt iron boron is a magnetic material here, MgO is the insulator. Now here what we did was we studied the compositional variation effect of cobalt iron boron layer, and so this is again a TEM structure.
Sorry to interrupt you, sir.
Yes.
Sir, we are running out of time, so kindly if you short it up.
So how long do I
have? 5 to 10 minutes.
Okay, sure. Thank you. So I will wrap it up in next 10 minutes. Okay. Okay, so this is the cross section as you can see here, and on A you can see the schematic. So anyway, we will not go into the schematic. The end point I would like to show you here is that we could see that for a cobalt composition of around 35%, we could reduce the damping to the lowest, as you can see here, but still have very high anisotropy at this composition. So therefore, in the end, when we this basically gives us what we needed. So we needed high anisotropy and low damping. So this is how we design the free layer, or we choose and design the free layer of a STT MRAM. Next, so I talked about the field based MRAM, then the STT MRAM. Now third is a SOT MRAM. Now SOT MRAM, there are so STT MRAM is already used in the market today. We already have devices based on STT MRAM, but SOT MRAM is still something that is still studied at the research level in the universities and other institutes. Now what is the difference is that in SOT MRAM, the current based switching is still current based. However, the right current is not passing through the stack structure or through the entire device, as in case of a STT MRAM. Here it is passed along the underlayer. So it's like, as you can see, if you follow the line here, the white line, so the current actually is passing under here instead of going through the device. Now why we need this? is that because a very high current is actually needed to switch devices in case of an STT-MRAM, and this high current can sometimes burn the STT-MRAM devices, right? So therefore, or maybe even damage the select transistor at some point. So what we therefore wanted to do was to find a way in which we don't need to pass the current through the device, but yet change the magnetization as we want to, but without passing current through the device. So the read current is still through the device, but the write current is parallel to this device and doesn't flow through the device. So here you can see one schematic here again. So this is the device, two ferromagnets separated by an oxide. So this is the MTJ as we had seen before, but the way this is now used is different. Here the current, the read current goes through the structure, which is much lower because we do not need very high current to read it, but the write current goes just adjacent to the ferromagnet here. So that the write current here is, so this is a charge current, as you can, as indicated here, the JC charge current. The charge current creates a orthogonal spin current, which then flows up the structure. So if the charge current is going in this direction, the spin current will go in this direction and will try to manipulate the spin here, and therefore we'll see a resistance depending on the orientation of the two devices. And if the current is increased much higher, then it will switch the weaker magnet in the direction as we want, right? So that's how this will operate. Now this spin orbit torque is generates from mainly two different effects. So one is a spin orbit coupling that we had discussed in the first slide, and the second one is a spin Hall effect. And spin Hall effect is dependent on spin dependent scattering. Okay, so certain spins, up spins or down spins in some material will be selectively scattered, not equally scattered, and therefore it creates this biasness or difference, and therefore we have this spin based current. Now this is another work we did where we studied a hafnium underlayer for generating spin current here. So in spin orbit torque we talk about the spin torque source. Okay, so spin torque source in this case is the hafnium. The hafnium layer through which the current passes generates the spin current. Okay, and here we found that with the as we increase the thickness, if you can see here, as we increase the thickness, the strength of SOT, this gives the efficiency. Okay, so the strength of SOT increases. So we can see that SOT is thickness dependent. So we know that it's a bulk. So we know that it's a bulk effect. And second is that the thickness increases the strength of it. We also studied another one which is called topological insulator. It's another exotic material that is used for spin orbit torque source. Here you have a 2D topological insulator as we have shown in a schematic. What are topological insulators? These are very exotic materials again, where the current flows only on the boundary and not in the bulk of the material. So the bulk is insulating, that's why they are insulators, but their boundaries are conducting, and therefore they are a special class of material. Now we developed something called bismuth selenide material, which could be used for spin orbit torque generation. So this again serves as the source. So I will just show you how this works here. So this is just imagine that the black and the white are up and down, two different polarities, right? So we start from the black state, the dark state, and when the current is passed through the layer below this, right, the magnetic layers can be switched from black to white by the current that is passed through the non-metal, that is the bismuth selenide underlayer, or that's the spin orbit torque generation source. Okay, so this is my final thing that I'm going to share. I will just run through this. In addition to all the three interactions that I mentioned before, which were very collinear, there is a fourth interaction which is non-collinear, which I want to just mention to you. It's called the DMI, or the Zoloshinsky-Moria interaction, and it happens at the interface of a ferromagnet with a heavy metal, or any kind of a special metal, let's say. And this is difference because this is orthogonal to the other three. So the other three are collinear, but here this interaction is orthogonal to the magnetic moments themselves, and therefore they give rise to some exotic, beautiful objects called skyrmions, where the magnetic moments whirl around like this, right? So this is very beautiful. That's why I wanted to show you this, because nanotechnology can be really beautiful as well at the same time. So this is a MFM image. magnetic force microscopy of many skyrmions like this. So each of this single circle that you see is something like this, where the magnetic moments are in very beautiful, arranged in a very beautiful fashion like this. And we use skyrmions for racetrack memories as well as for neuromorphic memories. So these are the two applications where skyrmions are used. Unfortunately, I cannot show you much today because of paucity of time, so I'll just show you this, that skyrmions, when they are trying to move like this, for example, they get stuck at defects. So that creates data latency, and it also is like a car which is trying to move but getting getting bumpy road. And the second one is like it is trying to move and it gets crashed on the side like a race car like this. Why I cannot go in detail today, but what we did was we created we used it on a separate kind of a material like ferromagnetic material. In the beginning I told you that ferromagnetic materials are a different kind of material than ferromagnet. So here in ferromagnetic materials we were able to address those problems. So I will just skip through this. Okay, so we will end on this slide. So we talked about memory hierarchy, and in memory hierarchy we discussed about the hard disk drives, right? We talked about the hammer technology, the bit pattern media technology, and the magnetic microwave assisted recording technology. So this is where the work is being done for this traditional storage track. Then I talked about the skyrmions. The skyrmions are used for something that is between flash and main memory because they are much faster compared to the current flash. So they can extend a bit into the main memory, but their primary purpose will be to replace, let's say, flash. And SOT and STT based MRAMs that I discussed in few slides, that is basically targeted to replace this segment, which requires very fast change, and it will be very expensive and will not need huge storage capacity. So these are the three different hierarchies that we discussed, different technologies of these three different hierarchies we discussed today. Okay, so I am sorry I could not I could not go into detail of a lot of things, but thank you so much. Thank you so much for your attention. Thank you.
Thank you, sir, for giving your insightful talk. Now we will open for question answer session. So our first question is from Rajan. His question is how to protect these magnetic film-based devices from environmental noises. What is the standard way to package them?
Sorry, so to protect them from standard, okay. So from environmental noise perspective, generally, if you talk about, let's say, thermal noise or something, as I said in one of the slides, I showed you that the KUV needs to be increased, or basically the energy barrier needs to be kept high. So if the energy barrier is kept high enough, then these devices will automatically be protected from unwanted noises like thermal noises or any other kind of energy that is floating around. So it can be done like that. So that's one of the ways. It's a very brief answer, but if you want more details, please drop me an email. We can talk or something. But if you want something more detail, but this is the brief line about it.
Thank you, sir. Our second question is, can Liga be an efficient method to consider for this fabrication process?
So sorry, I am probably unsure what someone means by Liga. Let me just check. Can anyone tell me what is Liga?
It was in short.
I don't know.
Written in short.
It was written in short form, sir.
Okay. So well, any nanotechnology process can be used depending on the size, for example. So if you want micron sizes, then of course many processes which is let's say optical lithography based can be used. But when you want very small sizes, you will need to really use things or technologies which can create smaller structures, but at the same time be scalable. So for example, just an example, let's say electron beam lithography can be used to make very small nanometer dimension structures, but you cannot use that to make a memory device really, because there's not something that is scalable. You cannot make gigabytes of memory using electron beam lithography. So something that can be done scalably yes, sure. If Liga can be used for scalable patterning, then it can be used. And of course, the dimension, it needs to be able to do very small dimensions.
Thank you, sir. Our last question is, what is spin Hall effect?
Okay. Sorry, I did not mention that. So, spin Hall effect is so as I said that when you pass current through through certain materials, what happens is that it faces or let's say certain structures or certain individual materials, it faces spin dependent scattering. So there are top and down spins or up and down spins, let's say, and some of the electrons will have up spin, some of the electrons will have down spin, but the scattering or the resistance it faces may be dependent on the spin. So for example, in material A, the up spin faces less resistance as compared to the down spin. So the up spin will have more conductivity compared to the down spin. So this can be so this gives like the splitting of two different spins in two different ways, and you have a potential developed between them. So that's the spin Hall effect that you see in the end.
Thank you, sir. Thank you for giving your insightful talk and addressing the queries. Thank you once again, sir.
Thank you.
As we have come to the end of our today's talk session, I would like to thank once again Professor Gagan Kumar, Professor Dababrat Sikdar, and Professor Tanmay Datta for their insightful talks in this session. Now we have a short mock quiz session. All the participants are requested to actively participate in this quiz. The poster presentation will begin shortly after the quiz.
Arun is not.
We can see.
Yeah. Link for the mock quiz is posted in the chat box. Kindly go through this.
Just they can share their troubles. Huh?
So all the participants are requested to go through this quiz so that we can know what are the problems you are facing, and also submit the form, feedback form through the WhatsApp group, and we will take short leave for 10 minutes, and we will get back to you.
You please join in your respective groups for poster presentation. All of you are requested to join in your respective groups for poster presentation. Okay. So we are closing this link. You please join the link which is given to you.